Oh, okay. Looks like we've lost access to LinkedIn streaming, so that's not good. Well, I think most people are coming from YouTube anyway, so no big deal. Let's go live. All right. Hello, everyone. I see that some of you guys are coming into YouTube, so hopefully the people who are watching from LinkedIn can find this. The LinkedIn StreamYard integration broke this morning, which is really unfortunate for us, but hopefully that everyone can find their way in. In about 5 minutes here, we'll start with our first talk. And in about 2 minutes, I'll give a quick intro into what we're doing. But for now, if you are here, I'd love to just have you tell us where you're coming from, what city you're from, what you're doing, anything like that. Just tell us a little bit about you, and we'll get started here in just a few minutes. Okay, so the time is 8:01, so we're going to get started in just a minute here with an intro, and then in a couple minutes we'll hear from our first speaker. Portland, Oregon, building custom solutions and workflows for SMEs. Okay, that's cool. That's fun, Ryan. Welcome to the stream. Okay, so it's 8:02. I'm going to start my intro, and then we're going to get into the talks. So, hello, everyone. We're so glad that you're here to join us, OSS for AI, for the chance to learn about all sorts of generative AI tools in the same place. OSS for AI is an organization dedicated to providing developers with the resources to understand, use, and contribute to the development and direction of AI. So we're super excited to have all of these innovative leaders with us today. Today, we'll hear from 12 speakers pushing the boundaries of what's possible in AI. We'll start with a set of 6 15-minute talks from Mohak Sharma, Xander Matheson, Arvind Putravu, Viraj Ratnelekar, Frank Liu, and Fabiana Clement. Then we'll take a quick break before a longer talk on how to pick your LLM stack and how to think about the different pieces in that application. After another quick break, we'll get 6 30-minute talks from Zain Hassan, Danny Bixon, Jay Raj, Aparna Dinakaran, Jason Estragian, and Vishaka Gupta. We've got a great lineup of a lot of tools and a lot of companies that are building in eval, in LLMs, in LLM architecture, and vector databases, and all sorts of different data tools and aspects of the LLM stack. Please feel free to drop any questions you may have as the presenters are speaking, and we will prompt the speakers at the end of their talks with any of the questions that come through that they have the time to answer. And if your questions aren't answered, please join us in the Discord, find us in the Discord, ask the questions there, and you may get the chance to speak with one of the speakers and ask them your questions yourself in the Discord, which I will drop a link to once we get started with the event. So as many of you are here, we're going to get started, and our first speaker is from Honeyhive, is Mohak Sharma from Honeyhive. Honeyhive makes it easy and repeatable for modern AI teams to test, evaluate, simulate, and observe their AI applications and make them safer, trustworthy, and more reliable for their users. Honeyhive simulates real-life AI applications to detect bugs before they reach production. And today we'll hear about how from one of their founders, Mohak Sharma. Mohak, welcome to the stage.
Hey, thanks, Sujia, for having me. Let me just start sharing my screen.
Great. I'm going to remove myself from the stage now.
Perfect. Okay, hopefully everyone can see my screen. And yeah, thanks for having me here today. Today, I'm going to be talking about techniques for building LLM evaluations that actually work in the real world. We've heard from a lot of users that LLM evaluations are a net new way of testing AI applications. They're more scalable, faster, and cheaper than human evaluation. But one of the issues that we really hear is they're quite unreliable to actually be able to use in production. So today I'm going to be talking a little bit more about what are some techniques that you can actually use to build LLM evals that really work for you and your specific domain and your use case. So a bit about me. I co-founded Honeyhive in late 2022 to build evaluation tooling for AI applications. Previously, I built the data and ML platform at Templify, which is a SaaS unicorn based out of New York. And at Honeyhive, I've really just had a chance to work with hundreds of teams building AI applications, from your major builders and researchers like OpenAIs and Anthropics of the world to Fortune 50 enterprises to app layer infra startups. And in the chance, I've really had a chance to actually look at what kind of applications people are building, what are the evaluations that they are setting up, and how they're actually making them work for their use case. So let's dive in. Today, we're going to be answering three simple questions. What are LLM evaluations? Can we actually trust them? And if so, what are practical strategies that we can use to actually align them to your domain and use case? So what are LLM evaluators? The basic idea really is using large language models as a judge to be able to evaluate the outputs of other large language model applications. This concept was first introduced by Anthropic with the constitutional AI approach, and also adopted by OpenAI with the super alignment team, where they use weak to strong generalization. And the basic idea is a smaller large language model can effectively govern and evaluate a larger large language model. There have also been other papers that came out in the last year, like NLG eval is an example, SPADE, which demonstrate really high correlation with human judgment and LLM scores. In terms of sheer efficiency gains, our internal findings indicate that LLM evaluators are roughly about 10x faster compared to mechanical Turk graders. They're also 10x cheaper, and they have roughly about the same accuracy and consistency compared to mechanical Turk graders as well. And so the promise of using LLM as a judge to evaluate the outputs of other LLMs really is faster, cheaper, and scalable assessment. And the end outcome, I think every team is trying to drive with LLM evals, is automating white checks, manual iteration that people are doing today in spreadsheets and in the playground. But if you're building an LLM application yourself, you may actually have a very less rosy view of this whole space. The reason is we see two key challenges if you're actually building LLM evals in production. First is criteria drift. Really what we're seeing is LLM evals and LLM applications themselves are dynamic in nature. So your inputs are constantly changing. The failures that their application experiences also shift over time. And if you're using an API model like GPT-4, Anthropic's Claude, these companies are bringing constant updates to these models. So the models themselves shift over time. So a lot of users, which might be relying on frameworks like RAGAS, GEval, LangChain, et cetera, and which often rely on generic criteria definitions and they're static in nature, those evaluation criteria fall short because the evaluator's notion of good or bad no longer aligns with your domain expert's notion of good or bad. This is something which has been corroborated by the EvalGen paper that came out earlier this year by good folks at Berkeley. And they found that LLM evaluation criteria cannot be static. It needs to constantly evolve over time. And the assertions that you're defining within your code to test these LLM applications must actually adapt and evolve as the failure modes are evolving over time. And the main challenge really then comes down to how do you optimize and maximize the true positives from your LLM evaluator while minimizing the false positives? So this is just the first challenge that we see, really, criteria falling short of what users actually see in production. The second bigger challenge, in our opinion, really is the evaluation data sets themselves lack test case coverage. So what I mean by that is when you start building an LLM application, most users start with 20 to 50 handcrafted examples of test cases that they test their prompts against. But the problem is, as soon as you put your application in front of your users, the kinds of user queries that you're going to see from your users might be widely different from what you had planned and actually tested your application for. And so the static data sets themselves fall short because the manually generated data sets, the test cases, are not representative of the kind of user queries you're actually seeing in production. And the result is data set drift. Your eval data set no longer represents actual user scenarios. And that ultimately renders your entire eval meaningless. We see a very common example of this when it comes to things like grammars, where a lot of users might have perfect grammar when they're crafting their 20 to 50 test cases. But the users in production are actually, perhaps they're on a phone, and they're actually inputting these queries in lowercase, using abbreviations, using incorrect grammar, perhaps even using different languages if your application is global. And so, again, if your test cases are not representative of those kind of user queries that you're actually seeing, the entire evaluation is rendered meaningless. A second example I've seen, particularly in financial services, is when you're trying to do, let's say, question answering over 10K SEC reports. And you might have designed your entire application for tech companies, tech public companies, and their valuation methodology in mind. But now suddenly your users start asking about companies in healthcare or manufacturing. You might not have the relevant data in your vector database to actually be able to answer those questions, or simply the valuation methodology is different. So if you're not accounting for those sort of scenarios that your users are actually seeing in production and your data set itself is static, your entire evaluation, again, is rendered meaningless. So how do we actually solve this? How do we get past this problem of static evaluation criteria, static data sets? Well, the answer really, we believe, is moving to a more dynamic and adaptive LLM evaluation system. The way you actually do that is by treating LLM evals as not static tests, but as dynamic systems. I think all of us coming from software engineering world have been used to defining tests in a static manner because the outputs are constrained in nature, so are the inputs, and the sort of errors that you can see in a particular function, they're very constrained. But when we're working with LLM applications, the inputs are completely unconstrained, so are the outputs. And so we need to actually treat our LLM evals as a dynamic system that requires continuous tuning and alignment with the evolving user needs. And how do you actually do that? Well, the answer really lies in your domain experts and users, right? Domain experts are the experts in what should be the right answer for a particular user query. And your users have their own expectation for the correct answers, what they should be. And so what we find is if you're building an LLM evaluator and you want to align that, the best way to align that is with your domain experts themselves. And the way you do this is you first run the LLM evaluations, the automated metrics, which is great. But then don't abandon manual evaluations. Whenever you have an automated score, actually look at the score, reason over it, perhaps critique the score yourself using thumbs up, thumbs down. Some companies even we have seen actually edit the end score. And that allows you to have a ground truth data set of what the correct score should be and what was the LLM generated score. And now you can use those two things to actually measure alignment between the LLM evaluator and the human domain experts. So you can use metrics like F1 score if you're capturing binary judgments like true or false. Or you can use Pearson-Spearman correlation if you're capturing things like on a scale of 1 to 5, how hallucinatory is the output. And this will help you quantify how well your evaluator is actually aligning with human judgments over time. The second thing that we found really useful is actually including a lot of good and bad few-shot examples into your evaluator template itself. This just grounds the model, gives it more fine-grained context for it to be able to evaluate both the positive scenarios as well as the negative scenarios over time. Now, coming to the data set alignment problem. Here, we believe the best data sets actually come from the real world. So whatever your users are actually inputting into your system, that should be representative of your test cases. So as an example, what we've seen that really works for users is if you have some sort of automated metrics or you're capturing feedback from users in the form of thumbs up, thumbs down, you can use all the data sets, all the test cases where users gave positive feedback as a regression data set upon which you want to make sure as you're iterating, you're not regressing over time. And all of the test cases where users were not happy, you can use that as an improvement data set to make sure you're actually continuously improving your application as you're iterating over time. Some of the more advanced companies that we work with, we've also seen them use things like simulations, where they might design a end user simulation using the large language model itself and create different personas. So as an example, there are companies in the edtech space who use simulation for, let's say, a child, a fourth grader in India who's really interested in mathematics, as an example. And you can use those simulations to actually go out there and red team your application to make sure you're not regressing or you're continuously improving over time. So if you take a step back, the key idea really is to build reliable LLM evals. We need to treat them as dynamic human-in-the-loop systems instead of static systems and static tests, which is like an idea we really need to abandon from software engineering. And this is very much like how you build your core LLM application, right? You continuously collect the ground truth, iterate over time, and make sure your application is continuously improving. So how does HoneyEye fit into all of this? Well, we are a unified AI evaluation observability platform. Our main goal is to create a robust test-driven development and iteration workflow that really just ensures that your AI applications are reliable by design. The way we do this is by logging all of your real-world examples and scenarios from production through OpenTelemetry. So you have a sense of what exactly your users are actually inputting into this system. Second, we allow you to build LLM evaluators within the in-app eval console. And you can actually align those evaluators with those real-world scenarios that you are collecting from production. So you can iterate on the evaluator prompt, you can add few-shot examples, and really make sure the scores that your LLM evaluator is outputting are actually aligned with your domain expert's preference. Third, you can actually supplement LLM evaluations and those automated metrics with human review. So users can actually go into the trace view, give thumbs up, thumbs down on the evaluation results, even correct them over time. And that allows you to measure alignment over time and actually improve your evals as you add more data sets, as you change the evaluator prompt, add more few-shot examples, or perhaps even fine-tune a binary classifier yourself. So yeah, that's my talk. Thank you for joining. And if you're interested in staying in touch, please connect with me on LinkedIn by just scanning this QR code.
Cool. Thank you very much, Mohawk. We'll leave the chat about a minute or so to ask any questions. If there's no questions that come in, there might be some questions that are going to be private questions that are going to be asked directly through the Discord. If you see those, please answer those. If not, I will try to route those to you as they are asked. Someone has said that you have had an awesome presentation, so that's really good.
Thanks, Mike.
Okay, so I think we can bring up our next speaker in the next minute or so, and I will actually let our other host do that. You're muted.
All right. Next up, we have BiteWax. BiteWax maintains an open source data streaming system built entirely in Python. You can use BiteWax to build streaming data pipelines, real-time apps with everything that you need, including recoverability, scalability, windowing, aggregations, and connectors. So today we are going to be hearing from Xander Matheson, the CEO of BiteWax. Xander, I will let you take the stage.
Excited to be here. Thanks for having me. Cool. Let's get started. We don't have a ton of time and there's a bunch to talk about. So thank you for the introduction. I won't repeat what was just said, but a little bit more background on who I am. So currently the founder and CEO of ByteWax. I've been working on ByteWax for about 3 years. The company's built around the open source project, which you can find on GitHub, ByteWax/ByteWax. Prior to that, I worked in data science and machine learning. That was last at GitHub, pre and post the Microsoft acquisition. And then before that, I was at Heroku as it was a part of Salesforce. And not listed on there, but before that, I worked at a speech technology company working on all sorts of things, but they did speech recognition, speaker verification, text-to-speech, and NLP stuff. Before there were chatbots, we were building chatbots there. Or before there were like very sophisticated generative AI chatbots, we were building chatbots there. But today we're going to talk about something else. We're going to talk about how stream processing fits into RAG. So we'll do a quick intro to RAG. We'll go into a real life example of a real-time RAG architecture and talk about the components there. And then we'll dive into the ingestion pipeline, which is where you might encounter stream processing in your work. And then I'll leave you with a working example. It's actually a full workshop that we ran a couple of weeks ago, we being ByteWax, and the code that goes with that. So we all know what RAG is probably here. It's a waste piece of cloth. You might use it to wipe down your furniture. No, I'm just kidding. RAG stands for Retrieval Augmented Generation. So I like to try to minimize the amount of terms you might not have heard before. But RAG, in my mind, is really just taking as much information and context as you possibly can and shoving it into the prompt and specifying that the generative model should return an answer that uses the information that you've shoved in that prompt. So the retrieval part is pulling that information together, whether it's using some simple retrieval from a database or something more advanced, and then the generation and augmented is that shoving in the prompt part. So today, RAG is probably the most efficient way to reduce hallucinations and provide accurate and up-to-date information in AI applications. The key being they're up to date. So how do we keep information up to date? Because as you all know, nobody likes stale data, just like you don't like stale bread. This is absolutely disgusting. The stale bread, that is the image of it. Your customers don't appreciate when you return answers that are out of date using stale data. And so it's increasingly necessary if you're building a generative AI application to provide the most up-to-date information. In most applications, not always, but in most applications, because the world around us is always changing, and the data that we generate, which is in the terabytes per day, is always changing, and there's always new information that we need to provide. So where does stream processing fit into all this, and how do you manage to keep that information up to date? It might seem a little overwhelming, and this architecture diagram that I'll share next might not even help that. But I think it's helpful to walk through a working example with the architecture diagram and all the pieces that are included. So let me walk you through this diagram a little bit. The workshop, this is from the workshop that we did a couple of weeks ago, and I'll share the full video. It's 2 hours long. We did it with Microsoft and Unstructured as partners in that workshop. So what this is doing is this is a financial portfolio advisor. So down in the right corner here, a user would specify some stock tickers that they're watching, and this would generate a pipeline that's streaming data from Kafka, and then based on some signals, it will automatically generate a new report about the stock tickers. The data that's used, the data that's used for the financial portfolio advisor is collected in real time from a bunch of resources that are publicly available. So you have some public and some privately available. So you have news articles, you have filings that are PDFs that are on the SEC, Edgar API. If you're not familiar with finance, it's like a whole rabbit hole in itself. Then you have stock market information. And so that's all being streamed into Kafka via Bytewax. And then over here, we're going to take that information and we're going to process it and structure it in such a way that we can put it into a data store, which we'll talk about in a second, and that will be used in that prompt. So this is the whole architecture of the RAG system. You have an ingestion pipeline on the top, and then you have an application on the bottom, and then your data that you've ingested into this data store, you will be injecting into that prompt. So why is Kafka here? What is Kafka? For those of you who aren't familiar with the whole streaming ecosystem, Kafka is a streaming platform that has many parts to it, but it's most well known for the actual transport/storage layer. So Kafka has an API that allows you to interact with the broker. So you send information, that broker will then store that in a log format. And so the data is stored in order, and it's stored to disk. So it's durable and it's replayable, which are both really important concepts because we don't want to lose any data, because if in some instances your data sources here might be almost ephemeral, like you can't replay them from there. So you want to make sure you put them into a durable layer here, just as you would with a regular database. The difference is here, it's replayable in that stream. So things come in, you care about the order, and you want to be able to replay them in an order, or maybe if you have some failures on the other side of Kafka here, and you want to go back in time essentially to where you have an accurate representation of what's going on and whatever these downstream pipelines are, so you can replay from that. Or maybe you're just backfilling, and that's another reason you'll want to be able to replay that. The final thing is it's multi-consumer. So Kafka can have many producers and many consumers, and that gives you the ability to kind of produce that data into Kafka once, and then have many consumers who are using that same data, which in this architecture we would be, because we're using information from Kafka here the same topics in this pipeline, where we would be like creating some logic to alert and to generate that report from. And then up here, we'll be using that same data to index it and put it into the data store. So the next key component to a real-time RAG architecture is, I should be keeping track of my time here, but I'm not, is the data store. So you've probably heard a ton about vector databases, or at least about the way to search with a vector index. So many databases have the ability to use a vector index and store embeddings, which are the vectors. In this workshop, we used Azure AI Search, but you can really use whatever fits your needs. There's so many options out there, and there are a lot of great options. These bubbles kind of move, but the final piece that I'll talk about here are just the pipelines themselves. And those are powered by Bytewax. We did also use Haystack and Unstructured. Bytewax is sort of the framework and the processing engine. We'll talk about that in a second. But that's what we use to describe how we're going to connect to, process and transform data, and then ultimately write it out somewhere else. So what is Bytewax? Bytewax is a Python native open source stream processor. And you can broadly think of it as this sort of middleware layer where you embed logic, transformational logic or operational logic, using a series of operators into this DAG that you describe how you're changing data, and you're moving it from, most often, you're moving it from one place to another. So you may be doing some pre-aggregation of that data. You may be doing some joining of multiple different sources of data, branching, filtering, enrichment, etc. Bytewax is, well, I'll talk about it more in a second, but the rest of this diagram just basically saying here in the bottom that Bytewax can run almost anywhere. It's cloud native, which gives it an easy deployment story. So why would you use Bytewax for this particular use case? Bytewax is very generally applicable. So why would you use it for RAG specifically? And also I'm going to talk about why did we build Bytewax. So we made Bytewax because the current tools, if you're not familiar with Apache Flink, Spark, Beam, or Storm, Spark is can be used in both streaming and batch use cases. Well, actually, most of them can, but essentially these processing engines are just way too hard to use. Generally, like in our personal experience from people on the team and myself or others, it requires a number of engineers. Even to get going, it can take a long time. It lacks the right interface for AI, so it's very difficult to use Python with these tools. They're quite resource intensive, and they're exceptionally expensive to maintain. So all of this culminates in weeks to months to realize ROI on the project. So that's the reason we built ByteWax, is to move that. I hope you like my hand-drawn little chart here, but to move this into the days from weeks to months. And then also to enable people to use the Python ecosystem of tools, which therefore will enable you to use AI and machine learning tooling. So what are the features that make ByteWax possible? So we have first a Python native API. It's built on a Rust engine. It's actually built on top of an open source project called Timely Dataflow. It gives you stateful streaming capabilities. So that's what you need in order to do joins, windows, aggregations, or have stateful connectors that have an idea of where you are, like track your progress. It's easy to deploy and comes with observability, basic observability. It's easily scalable and cloud native. Cloud native kind of lends to that easily scalable story. So it can run on Kubernetes, running Kubernetes. It can use object storage for backing up state, etc. And it comes with recovery included. So it's production ready. Okay, so we'll quickly, with the time remaining, look at like what is a ByteWax workload. We call those data flows, and we'll look at the anatomy of a data flow, and we'll just look at these two of the pipelines that are part of this ingestion in this overall workshop. Okay, so what you're looking at is two pipelines. One connects to SEC, or you're looking at two diagrams of the pipelines. One's connecting to SEC Edgar API to receive the most recent SEC filings, and the other is a custom WebSocket news connector. It's connecting to a financial news feed from Alpaca, which is actually a wrapper around the Benzinga news. So down below, it's like the most recent financial news, and up above, we have the most recent filings pertaining to different publicly traded companies. So a data flow is a series of steps. Data flow, which is one word, we use it to describe these workloads, but a data flow itself is a programming paradigm where each compute is its own step in a directed graph. So in this case, after we pull the SEC website, we'll get a Atom feed that we can parse, and then from that we'll get a list of filings, and we can deduplicate those filings in a stateful step, because we'll have, if we're polling, we'll have most likely, depending on the interval, you'll have duplicates. We can then enrich this data with some more stock or some more company information, serialize it, and then write it to Kafka. So we're describing in the data flow, we're describing the different steps that we're going to take to move data from this raw Atom feed to something that we can then use downstream, which is going to be the filing information itself. So I'll just quickly show you what that code would look like. Sorry, I have the wrong link here. Maybe I put it here. Sorry. There we go. So this is the SEC filings website. So basically what I want to show, and we don't have a lot of time left, is just it's too much information to kind of grok all at once, but ByteWax gives you the hooks and semantics to describe how you connect to almost anything. Anything you can, there's a Python client library for, you can connect to. There are like some caveats because of depending on what guarantees you want, etc. But so in this case, we're connecting to the SEC Edgar website, and we're just going to pass out the list, or sorry, that Atom XML data file object. So we create that custom input, and that could be literally anything. Then we set up a data flow object, and we specify our input with that input source and whatever parameters that input source requires. And then each successive step, what I really wanted to show is that there's the idea of operators. So each node in that graph that I have shown is an operator. And in that operator, you will write some Python code to describe how you're changing that data. So we have a flat map here, and there's many different operators, and we write those operators. But you can also write custom operators, so you can have maps, windows, joins, et cetera, and then we provide those with some custom code. In this case, it's the code to parse that Atom file and pull out the individual entries. A flat map means I'm taking one thing and splitting it into many objects downstream. And then what we put that, the variable that we provide here for the output of that flat map, that's going to be our stream handle. You can think of it as almost like a generator object. So it's like you're iterating through that stream, and each successive step, now we have our stateful map where we're doing duping. We're going to pass that stream handle, which you can think of it as like, okay, we're passing that generator object. And then ByteWax itself is going to iterate through that. And ByteWax will take care of coordinating everything. I think I'm out of time, so I better wrap up. It will take care of coordinating everything and allowing you to scale, et cetera. So that's it. The whole YouTube video is here. I'm going to put it in the chat, I think. And I'll put this in here too and wrap it up. All right. Thanks everyone for listening. And I'll drop off here and stop sharing my screen.
Cool. Hello, Megan. Hello, Xander. Thanks, Xander.
Thanks, Xander. All right, handing it over to you, Eugene.
All right. Thank you, Megan. So our next speaker is from Fireworks, and LLMs are really popular. They've been really popular for the last few years, but they're still really tough to use in practical ways. And Fireworks AI is building innovative tools to help improve access to LLMs and expand their usage. Today, we'll hear from Arvind Putrevu, who is a developer advocate with a track record of working on many innovative tools. And he will be talking to us about Fireworks' recent development of providing effective function calling LLMs. All right, Arvind, take it away.
Hello, and a quick mic check. I hope I'm audible, but otherwise, of course, thanks for great. Thanks for the opportunity. I'll quickly get started. I hope I want to specifically make sure that each one of us take something back from the session, and and don't want to take more time talking about a lot of slides. So I just have very minimal slides. Maybe if you could bring that up. Thank you. So I think building workflows with function calling is the topic today. And specifically, I'm very, very interested in function calling because you could build a lot of useful, productive things that otherwise impossible and takes a lot of time in your daily life. And that too with all great, say the large language models. So, and also however, if you could fuse two interesting aspects like the function calling LLMs and then also open source or open weights, I think that gets more exciting for the community. So at Fireworks, we're always thinking about how we could potentially help people, help developers and more of that stuff. I work in the developer relations team and then work with the community. And if you have more questions, always happy to help. But otherwise, here is the talk more about the function calling and more details. So we recently launched a function calling model or model open weight GPT-4 quality model. This beats on several metrics. I'm not going to delve deeper on the benchmarks and explain more about how it is different, etc. But then I'll talk more about in general, how we were really doing well on the community side, because I think community has adopted it really well. And say few quick slides, like say there is a while we released the base model and on Hugging Face with open weights, etc. And there are a ton of people who were like kind of like making a GGUF out of it, and then like this is like in the last 1 week we launched, like last week, and then there are a ton of downloads, ton of people doing great work. So super excited about what people could do. And then I'll also try to showcase like 2 demos and see if it is possible, maybe for easier consumption, etc. So first of all, what is function or tool calling? If you are probably not new to LLMs, but then like tool calling is not what many people would try at the first go, like maybe trying to build a chatbot or a RAG. But then I think RAG plus tool calling is also very powerful, in my opinion. And then say more about like functions or tools. Like say for example, it gives the model the ability to go and retrieve something from external services. And we all know that we've been building a lot of a lot of like microservices in the past, just like 2-3 years back, like microservices. And there's a big war between microservices and monoliths, and there are a lot of people building services on Kubernetes kind of platforms, right? I think more specifically, function calling is in step in that direction, wherein you could integrate your legacy services into your LLM workflows and make it more exciting. And then it can also be used in agentic workflows, which is like the place where we are eventually going, which is like the workflows. So tool calling is an essential thing. Like say for example, if you want to plot the stock price of Nvidia over the last 3 years or something, like you could all do that. And this is how it looks like. The tool calls are like function calls that are generated, and this is not like the code, but then the arguments are generated out of your prompt, and then it eventually like takes up a call, and then eventually gets retrieves the real-time value by calling that specific API with whatever you have registered. Similarly, like a parallel call. What is a parallel tool call? Like wherein if you want to retrieve two specific or make two API calls, then that's where I think you could do. You will have to. I mean, the LLM has to generate this uh, arguments or parameters for those two API calls, and retrieving that or making sure that LLM learns or understands that is very important. So this is like how parallel code would look like. There's another level which is also really cool called nested calls, wherein you want to retrieve two real time information from two different services or even one services, but also like parallelly do some sort of plotting and some sort of like you're trying to multiply things, overlay over other. So there's like more nested calls as well. So the complexity would increase as and when you try to like drive up the number of tool calls, like different tools, different services, obviously, right? Because there are beyond just like simply calling and getting the data. There are more things like resiliency, there are more things like handling errors, there are more things like and even generating the arguments, which is also like simplified. It looks very simple for human mind, but then like for LLM to understand and then like generate something really valuable, it's something really difficult. And then that's where the progress is being made as well. So also, like, what is multi-turn chat? Like, I think there are very few models that I have seen also like does multi-turn chat and function calling. In fact, my dream world would be building something that is like a fine-tuned model with a RAG and does function calling, right? Wherein you have a huge corpus of data that is vectorized and then readily available to retrieval over a fine-tuned model that is very domain specific, say healthcare. And then eventually you would want to build something that is more exciting with the function calling, like connecting to other systems, other RAG systems. Again, we are talking about agentic AI, etc. So in the similar course, I think like when you do fine tune for function calling, a lot many models lose out the regular knowledge capabilities, which is like, say, if it's saying like what's in the news today, and then you call the CNN API or something, and then you get the bunch of business news. But then also like uh, and then you kind of like want to get a history of Nvidia, like which is not there in the description, but then the model should be able to chat with you while retrieving relevant information. So that's something that you would probably see in some of these Perplexity and bunch of other players. Like you could also build more of this by the model itself, and that's where we are trying to do with tool calling itself. like preserving the base model capabilities, which I briefly talked about, like making sure that the model has some sort of chat capabilities retained, and then so that you have diversity in terms of like when you're trying to fine tune. I think it's also very important that you do it. So I'll quickly get to the demo, and also want to just quickly talk to you all about, we are doing a Campfire Connect event wherein we want to talk more about these systems, and we want to talk more about features and how we would do probably build large scale production quality LLM systems. So it's coming very soon in a couple of weeks. I just want to put that QR code here as well. But otherwise, like I have a demo and then I want to show it. This is like a specific demo which is more targeted or looked at like the whatever I'm explaining, and another one is like a demo that I built over multiple APIs that I could show. Let's see if we could quickly showcase that. Okay, I'm gonna see if I could. Okay, I hope you're able to see the screen. So specifically, this is like a simple function calling capability demo playground. I hope it is not too small, but otherwise I'll minimize it so for better capabilities. Yeah, I think it's easy. So say for example, if I want to check the stock price of ESTC, because I think why stock price, because we have available functions which are more stock specific, generate an image, render chat, and stock code and etc. More of that sort of stuff. I'll also like give more details about maybe in the Discord, like about the model, the documentation, how you could probably use it, and a lot of that sort of stuff. Um, uh, that way, I think we'll try. I think I'm randomly typing while I'm talking about it, so we'll see how it really works. ESTC is Elasticsearch, so just type it like uh, so let's see the all favorite NVIDIA, and then probably it gets the NVIDIA. Plot it over a chart for 3 years. I even did not try some of this, so let us see what happens if I do it. Oh, looks like it does. Okay, so it still doesn't do the. It only retains the previous context. If okay, there you go. So it doesn't do everything on different manner. Like let me try to regenerate. So this is like a simple function calling demo, wherein you could ask multiple. You could work with multiple tools and get more details. But then I also have another call where another app that I could showcase to you, more of a code specific one that I could also share the code with you all, so that you're also aware of how this would really look like in code when you try to use it. Let me share my screen as well. So hopefully you're able to see the screen. Let me check. Yeah, cool. So I have like two folders here. One is like functions, which is like a Python module, and then like UI, which is built in Astro. Not so much special there, but then it's like I'm using SEP API, which is a very good place to find out like a lot of APIs, public APIs like YouTube search, Google search, etc. And then like I'm using Fast API, popular REST API framework for Python, and then Pydantic. Everyone knows it, like no need to give special explanation about it. So a bunch of stuff like basic, and then I'm registering the tools here. Like one is like a genre generator, like if I want to find out what genre, like I want to see flight detail generator. I have a bunch of tools that are generated here. Like say for example, if I want to watch say movies from action, adventure, and animation, classic, a bunch of genres, and then I kind of like ask, can you generate some recommendations or from YouTube about that, or Netflix about that? I did not have a Netflix API, so I'm just using the YouTube API through the SEP. And then I have the chat API here, and then I kind of like have the a bunch of parameters updated, and it is being given as a JSON response to the UI, and the UI picks it up and runs it. So in the interest of time, I'm just rushing through, but otherwise you start this one on the Python module, and then you start this one on the the Node.js, and and then quickly you could showcase this one. Let me try to share the screen again. Okay. I'm nearly done, so that we have. Oh, good. Okay, so I think something is wrong here, but otherwise, like the idea here is to showcase whatever like the when you do a tool call, how does it respond, and then how it like really looks like. So I'm sorry. I think maybe just give me a moment. Yeah, I think I'm typing the wrong. Uh, yeah, and if I want to watch, like say comedy, and then it should be retrieve me based on the latencies and stuff like that, what are the movies that I do. I could do also more, and then yeah, I think like I'll share the more details about the code and the model and everything. So looking forward to hear other talks and hear more about Mid Year GenAI Zoo, and thank you Yuan and other folks for this talk and the opportunity.
Yeah, thanks for giving us such a great rundown of LLMs, function calling, and RAG, Arvind. I see there's also quite a few people coming in from some other locations, Budapest including. So our next talk, I will let my co-host come up to the stage and introduce.
Hello again, everyone. Next up, we have N8N. N8N is an open source and self-hostable workflow automation tool. It supports multiple integrations and for generative AI, and provides an easy way to test and evaluate different RAG approaches. So today we are going to hear from Viraj, who heads product at N8N.
Thanks, Megan. Excited to be talking, and especially after those great talks from Arvind, Xander, and Mohak. I think one of the things, especially with Mohak's talk that's coming out, is evaluating LLMs and evaluating different approaches to RAG is super important. And what I'm going to do is maybe share some experiences of how I've seen this sort of play out at N8N. And I guess my talk is titled "Evaluating Approaches to RAG," but I've just scribbled on there since speaking with you, Shen, initially, without much code. And I'll jump into why that's important in a second. But first, maybe for a little introduction. So I work across product and go-to-market at N8N. A lot of my time recently has been doing customer success engineering, and of course, the AI features are a really big part of that. In my spare time, I like using saws, taking them to old computers and putting over our modern oversized graphics cards into them. So also have a local AI rig running, and that's what we'll be using, this computer pictured here, when we're testing some of the models running locally, which you'll see shortly. And as for N8N, I think Megan covered it, but essentially it's a low-code workflow builder with a trick up its sleeve. And that trick is LangChain. So essentially, N8N provides this graphical interface on top of LangChain, allowing almost anyone who can read some basic documentation to now build agentic and RAG workflows directly from their browser without writing much code, or in some cases any code, if they're lucky. Since we launched these LangChain features, a lot of my job has been speaking with companies about how they want to use AI. And of course, as I mentioned, RAG comes up a lot. In fact, the two main things that I hear when it comes to RAG is, one, I want to chat with PDFs, just something as basic as that. But if we dive in, really they want to chat with technical documents where it's quite time-consuming to go through and extract very specific information. That's a huge use case. And the second is, given how quickly the space is changing, new models are coming out, somebody comes up with a different embedding strategy and so on and so on. People want to evaluate different setups and just check how they perform with the range of prompts that matter to them. So today we're going to build a very simple RAG workflow. Well, I guess maybe not build, we only have 15 minutes. So this would, I'll show you maybe a pre-built version. And then we're going to see how we can use Notion as a front end to basically, try and store different prompts. Now, this is really important, I think, using something like Notion, which is very accessible and easy, because a lot of people that want to use RAG in a business are, they're on the business side. They're not heavyweight engineers. That said, they have a burning need and they're happy to learn. So what they really want is, just a nice front end where you can type different prompts in, see what you get back, and then put a basic evaluation, and then hopefully pass on to the engineer who's building the production version, roughly what model and what prompts they want in the final application. So all that said, our targets within the next sort of 12, 13 minutes, whatever I've got left, is hopefully to have tested a couple of different embeddings models and different prompts. We'll then record the prompt ideas using Notion as a front end, and we'll get back what the models have evaluated those prompts to. And of course, we can do a quick human evaluation in this case, although I'll discuss some ways of scaling that and making it more automated briefly as well. So let's jump in. Hopefully you will now in a second see my my other screen here where we have a workflow up. There we go. So let me first dive in and explain what's going on here. Now, the first part of the workflow is to generate our embeddings. And for that, in this case, I'm using just a really simple travel insurance policy. So not quite a technical PDF, but actually there are lots of really specific things in here that have exact fixed answers that we need to go and find the answer to. Now with N8N, I'm just pulling it down from just a website. So we've got the PDF of the insurance policy and what it covers and what it doesn't. I then chose Quadrant as a vector store. So nothing crazy going on here. We're just inserting documents. So we're going to get this PDF, we're going to chunk it up, and then we're going to put it into Quadrant as vector embeddings. Everything here, by the way, these are just sort of what LangChain enables you to do. It's just a little bit easier having it in this interface. So things like chunk size, overlap, you're free to play with and test. And then plugging in a model is an embeddings model in this case is as simple as just selecting plus here, putting in a cloud model or running something locally, which is what I've used for some of these these prompts that we'll test. So once we've got our vector stores created, I've created 3, one using OpenAI prompts, so OpenAI's embedding model, one using one from Cohere, and this other one using Ollama running on running locally with Command R as actually not Command R, with MXBy's embedding model and Command R as the chat model. And essentially what we're doing, so I've also got a Notion database that you'll see very shortly. It contains 5, 6 prompts. We're going to get each of those prompts, just take each one in turn. And you'll see that rather than coding a switch node, it's pretty easy here just to put in a low-code node and say we have this sort of Notion property called embeddings. We can select OpenAI, Cohere, or Ollama, and then you can just put that through and it'll route it to the right chain. So each of these chains you see here is for a different kind of different model to be used. Under the hood, the vector store retriever is pretty similar. No settings have changed there. We're just changing the actual sort of quadrant collection based on the embeddings that I showed you earlier, where the embeddings are stored. So with that, let's jump into Notion. And what you'll see here is I've got some basic prompts. So these are all in the left column. I've got 2 of each one because the plan is to test different models. So we've got Ollama or different embeddings in this case. So we've got Ollama and OpenAI, Cohere and OpenAI. That way I can put it head to head and see how these models compare. The prompt response will be filled in by the once the automation runs in this column. I've got the correct response to check it against, and I can evaluate each response as nonsense, partially correct, or perfect. Let's jump in, and hopefully this will work. So I'm going to now run this workflow, and what we'll see is N8N will run. Here we go. It hasn't worked. Let's see what's gone wrong here. So we've pulled in everything from Notion. We have got, let's go here. So we've got our embeddings. We've got some that are empty. So I'm going to delete those and hopefully try that again. And this time that should work. So what's causing the issue here? Here we go. It's this thing. Let's just delete this for now. Cool. Now, if we try this again, second time lucky, let's hope. There we go. So we can see that these are executing now. So we've got each of these individual prompts going through and being answered by different models as we've selected here. That, of course, corresponds to what we've selected in this column, Ollama, OpenAI, whatever it might be. We can see that we have our first response here from one of the Cohere models, and looks like it has come back with the correct answer. So the question being, is the cost of emergency documents covered, and if so, up to how much? Yes, up to $750. I've checked these myself before, so I can mark that as perfect. Similarly, one of the OpenAI models has come back. So you get how, with this, we can just check if the responses are any good and see how, how the responses are different in each case. One thing to note here, actually, so the Cohere API was giving me some trouble. So actually, this has been answered by OpenAI as well in this case. So let's try and find, this will be a good one to look at, where we can compare the Ollama response to the OpenAI response. OpenAI is in with a correct answer already. Let's hope for all the local models here, Ollama does a good job as well. And in the meantime, we can see this is still running, so it shouldn't take too much longer to get the other responses. It's just taking each question in turn, so that it's not an indication of the speed of the model. It's just showing, it's just whichever one is first in queue. So cool. So I guess this is a response where for winter sports equipment, what value the items is paid. So 90% of its value, that's correct. It's quite verbose. So what we do here perhaps in real life is maybe fine tune this prompt a little bit more with Olama and Command R under the hood to say, be super concise, only return a number if that's the kind of thing that we want. Now, just checking for time here. I think I'm kind of okay for time. So what I'm going to do is show you how you can automate this a little bit further. We've got a workflow built out here, but it's a little bit annoying because you've got to hit test and run it manually. Ideally, we would just have this running on its own. So let's have a quick look at how we can modify our workflow and do some hands-on building to see how that would work within n8n. So first of all, I'm going to have this trigger. It's going to run, let's say, every 5 seconds. So we want things picked up quickly. And I'm going to give it a new prompt. So let's say if I take this prompt that we tried with Olama, I'm going to just add this answer concisely, returning only a figure if appropriate. Let's see how, I haven't tested this, by the way, so I'm not sure how well this is going to do with the model, but I'm going to give it a go now and see what happens. So once I set this to active, okay, please let's resolve your issues. I think we've got some problems here. Let's delete this for now. Save this. Okay, we're now active. So within sort of 5-10 seconds, this should be picked up, and we should see an execution where this is running. Another cool thing is, given that this is running locally, you can just sort of see, we'll see when, there we go. So we can see Command R is maxing out the VRAM of the graphics card. So we know that it's doing something. And sure enough, we should see the answer updated pretty soon. Let's have a look. Here we go. So we can see a workflow is running. Once it's complete, it should give us an answer. And let's hope that the answer is a bit more concise than this one, but I can't guarantee. There we go. So this is a way in which you can quickly test different prompts. So this obviously is the right answer. We want something just short like this. So this is a way in which someone who is non-technical can now work with prompts and actually, I guess, get models doing exactly what they want to do all this testing and tweaking without having to go through engineering, which is often the bottleneck in any organization. And even for hobbyists, I think, even for those of us playing with local models, playing with cloud models, whatever it might be, it's a super nice and easy, approachable way with which to play with LLMs and build retrieval augmented generation workflows. Finally, maybe one way to look at how you take this forward would be, so currently, I guess I'm evaluating everything manually. So we're putting a grade in of whatever it might be. Got the answer here. I think a really nice automation, especially for working with numerical data, would be just to have a, either generate these answers with another AI model, and then we can be reasonably sure, if they're right, if 2 or 3 models match up. Or if we do know the answers ourselves, we could just have another automation that checks the answer and does the grading automatically. I think I might be ahead of time, but what I'll do there is maybe just take a pause and open up to any questions if anyone has them. And if not, maybe just going back to wrapping up. So, feel free to connect. I've got my LinkedIn QR code there. We've got n8n is you can download it, run it yourself at n8n.io. We also have a cloud version. You can just get a 14-day trial without a credit card, get it started straight away. And of course, our GitHub as well. We're doing a lot more with local AI. So there's a few more features that'll be dropping pretty soon. We tend to release a new version of the product every week. So there's lots going on, especially within the LangChain and AI space for us right now. Thanks, Megan, and thanks, Ishan. I'll hand it back to you.
Thank you, Viraj, and appreciate you putting the QR code to make it easy to connect with you. I will hand it over to Eugen now for the next talk.
Cool. Thanks, guys. So our next speaker is from Zillis, and Zillis maintains Milvus, which is a distributed open source vector database. And if you've known me for over a year, you know that I used to work on this. And today we're going to have Frank Liu, who is the head of AI ML at Zillis. And he has a rich history of building innovative AI tools and recently published a very interesting article on new architecture for vision models, which he may or may not touch on. Frank is an expert in AI and ML, and today he's here to talk to us about one of the hottest topics in GenAI, which is multimodal RAG. Frank, welcome to the show.
Yeah, thank you for that intro. Yeah, that was quite the intro. But but yeah, as Eugene mentioned, today I'm here to talk about multimodal RAG. I'm actually going to share my screen here real quick. So what I want to do is I want to go through more or less a couple of slides first. Just talk about what RAG looks like today. I think what RAG is going to look like in the future as well. And also I want to go through at the very end, possibly a very, very quick demo showing not the whole end-to-end RAG system just yet, because a lot of the models out there today, they only support images and well, they support primarily text and some of them support images. But I want to demonstrate primarily the retrieval portion. So the R bit in RAG. So without further ado, I'll get right into it. I want to start off with, this is an architecture that a lot of folks here know really, really well. This is just vanilla RAG, and essentially what you're doing is you're taking your documents, you're taking whatever information, whatever text-based information that you have, giving it to an embedding model, storing it in a vector database, and then you do the same thing every time you get, let's say, a prompt or you get a query or a question. You do the same thing. You retrieve the most relevant documents and you add that as context into your generative AI model. So this is actually a diagram that one of our developer advocates put together, and I'm really just borrowing it here. But it's a good high-level overview. It's a good simplified sort of workflow of how RAG works. It looks complicated, but really what you're doing is finding relevant context and giving it to your large language model. There's a lot of other great vector databases out there as well. I know we have a talk from other vector database folks here at the Mid Year GenAI Zoo too. And you're not limited to using a vector database either. You can also use knowledge graphs. In some cases, you can use traditional relational databases or document databases as well. But vector databases and using vector search is a very, very common way of doing RAG. And I think one of the points I like to touch on is answering the question of whether or not RAG is dead. And you'll sort of see two camps here. The first the first camp says that because LLMs, the context window is getting larger. Now we have tools like infinite attention. LLMs are becoming smaller. The cost is going to go down over time, and RAG is going to be obsolete, right? And then you say, there's a lot of hype around the fact that 10 million tokens afforded by Gemini 1.5 essentially pretty much kills most of these RAG frameworks or RAG applications. And I think there's lots of evidence out there to the contrary, right? First is that when you have a lot of documents, or if you have a lot of information in your context window, it tends to make the large language model focus on some non-relevant bits and pieces of information. So that's the first thing, right? The second thing is that each token is also significantly more expensive than a simple retrieval step from a vector database. And that's always going to be the case. So if you're worried about cost and if you're worried about relevancy, you always, always, always are going to want to use RAG, at least with the current generation of large language models. And then, you see, there's all these, I talked about this a little bit already, but there's all sorts of these problems. You have lost in the middle, which a lot of these needle in the haystack and lost in the middle experiments are sort of solved. I'm not going to say 100%, but are sort of solved by a lot of these, by a lot of today's LLMs. But you still have that problem of, you get these large language models to focus on the wrong bits and pieces of content when you have too many tokens in your context window. This is, again, very, very, very similar concept here. And also one thing that I do want to say is that, RAG and large language model, the context window of a large language model, they're really meant to work hand in hand. So just as you have a computer, in a computer, you have, this really, really fast L1, L2 cache, you also have main memory, and then you have secondary memory. And that secondary memory is usually some sort of disk, it's some sort of, or, it could be some NFS. And you want something very, very similar for your large language models, for your RAG applications, right? The computer or the processor itself is the attention mechanism inside of large language models. And the main memory is really the context window. The databases or the data stores that you have, I'm not going to limit it to just vector databases. They are your secondary memory. They really are the disk that you want to use with your RAG application. So I think it really helps to, I really like to reframe it in reframe the whole thing to these traditional computer frameworks, and I think it gives us a better idea of why we need RAG, why it's still relevant today, and what are some of the really, really great things that we can do with it moving forward as well. So again, I'm going to revisit this slide from the very beginning, but this is vanilla RAG, right? You have documents, you feed it into an embedding model, and you store those vectors inside of some sort of vector database. When you do the retrieval, you have you have a search, or you have some sort of question that you're giving to the large language model that goes through the embedding model first. You perform a query to your vector database, you get the relevant context, and then you put the question or whatever the original prompt was with that context into your generative AI model, into your large language model, and you get a reliable answer, right? And what I want to focus on today is sort of the idea that there's now a RAG 2.0. So I imagine a lot of the folks here have seen the I forget when it was, but the GPT-4o announcement. They sort of did a little bit of jostling with Google. So I think Google's I/O happened exactly the next day. They announced very, very similar things. But now it takes not just text modalities, but it also takes audio, visual modalities, and of course, some of the original text as well. So when we think about this, right, what does that mean for RAG? It means that we're going to have to go beyond just text. We're going to have to go beyond just documents. And the reason for that is simply because now we have large language models that support many, many modalities of data, and we want to take advantage of all of them. We would want to take advantage of all of the unstructured data that we have and be able to put all of that rich content, rich information, all of that rich data into our vector database, or again, doesn't necessarily have to be a vector database, whatever data store that you're using, and feed the most relevant bits and pieces of all of it into our large language model, right? So this sort of architecture I like to call RAG 2.0. It is multimodal RAG at its core, and there's many, many ways of doing this, right? The simplest and easiest way is to transcribe audio and have a sort of an image to text and image to text, sort of an image description model, and to have, take all of your unstructured data modalities, represent them as text, and feed them into your vector database that way. I think that's actually not necessarily a great way of doing multimodal RAG. Maybe you could call that RAG 1.5, right? I think the right way of doing RAG is to leverage these really, really powerful multimodal models that we now have. And this one's actually called ImageBind. I think it was released over a year ago at this point. And this is a 6 modality embedding model. So it can take images, videos, audio, text, depth images, and also IMU data, so inertial measurement unit data. So everybody has a phone, and there's IMUs inside of that phone to help track movement. Step counters are based off of that, and it's really, really useful for tracking all sorts of different things that you do with your phone as well. So there's 6 modalities of data that is all embedded into the same space. Now, we're not using this particular model. It's called ImageBind. It's not describing images and turning images into text. It's not turning audio into text via some sort of transcription service or anything like that. It's actually taking the raw data, the raw bytes, and turning those into an embedding. And you get really, really powerful results from it, right? So I'm going to focus on this first box here. This is from the ImageBind paper. If you give it audio of, let's say, the crackle of a fire, and you want to retrieve images and videos that are relevant to it, you get images and videos of fires. Same thing with a baby cooing, right? You get videos of that, you get images of that, you get visual data of that as well. You can do the same thing for depth images as well as for text as well. So if I have the exact same audio on the left and I want to retrieve the most relevant text based on that audio, now all of a sudden I have these sentences that are really, really similar to that audio as well. So cross-modal retrieval across many, many different modalities, that is where embedding models are going as well, and that is what's going to form the basis of RAG 2.0. Again, this is called ImageBind. Actually going to use ImageBind in the upcoming example here, but it's one of the really key, the core ways that we're going to be doing multimodal RAG, not just right now, but in the near future as well. So again, not turning these pieces of unstructured data into text, but what we're going to be doing instead is embedding those raw bits and bytes directly as vectors. So I have about 5 minutes left. Ideally, I would leave a little bit of time at the very end for some Q&A as well. But what I'm going to do here is I'm going to talk about the retrieval portion only. So again, if I go back to this RAG 2.0 architecture, you have this retrieval that goes on in your vector database, and then after that retrieval happens, you insert it as context in your generative AI model. You do some prompt engineering, some tuning. Maybe you go back to the vector database, retrieve some more data, and then you get a reliable answer that way. I'm going to skip this portion here, again, because a lot of models today, the full capabilities of GPT-4o haven't been released. Because that's not there yet, it's hard to tune an end-to-end system and show you what that might look like without those capabilities. But what I will show you today is the R portion, the retrieval portion, how we do multimodal retrieval and how we get images and audio that are most relevant to the data that we're looking at. So without further ado, I'm going to switch tabs here. So I'm going to share this tab instead. So this is, I've sort of run this already once before, but what I'm actually going to do is I'm going to clear the output of all cells here. Make that a little bit bigger. And what I'm showing right here is, again, just that retrieval portion. So I've downloaded the Google I/O pre-show. I've actually downloaded I think the first minute or 2 minutes of it. And what we're going to do is that pre-show has visual data and it has audio data as well. I'm going to use a library called Radiant. This is actually a library that I created myself specifically to help turn unstructured data into vector embeddings. It works with a variety of different modalities. And then what I'm going to do is I'm going to use Radiant and turn this video into vectors. I'm going to store those vectors inside of Milvus. Milvus is a cloud native vector database. And then what I'm going to do is I'm going to sort of retrieve the most relevant bits and pieces of information there. I've already installed Radiant locally, but if you haven't, you can just pip install it. And it will actually install all the dependencies that you need for you. So Milvus now has a Milvus Lite version. It will install that dependency automatically if it detects that you need it. If you already have it, it's not going to do it. So let's just get started right away, right? I'm going to do these imports first. And the first thing that we're going to do is we're going to do some insertion. So again, I want to run you through what's going on here. Basically, I have a path to a video. And this video, again, is the pre-show to Google I/O. It's the first minute of it. I haven't downloaded the full thing. Otherwise, it would take probably a little bit way too long to actually get that up and running. And with Radiant, not only can you just vectorize stuff just out of the box, but you can also create these workflows. And what I've done here is I've created a workflow to actually read this file, right? So the first minute of the Google I/O pre-show from 2024. I'm going to send it into a transformation called video demux. And what that's going to do is going to separate the audio and the images into 1 second audio snippets and 1 frame every 1 second. And then I'm going to vectorize all the audio and all the video with the ImageBind model, right? After I have those vectors, I'm going to store them in Milvus using the insert operation. And again, if you're familiar with Milvus, you'll see this is not the typical way that you interact with it, but I've packaged it all into a single runner to make it very, very easy for you to do. So let's just get running that right away. It's going to take a while. So I'm actually going to sort of introduce a search workflow to you as well. It has all these sort of errors that's popping up, but that's okay. And from here, actually, what you'll see is we have a search workflow as well. And this workflow, we can actually, what we're going to do is we're going to vectorize text right? So that's this modality right here. And then once that is done, we're going to send the result of that into Milvus, but instead of inserting it, we're just going to search the fields, and then we're gonna get output fields as well. And what that's going to do for us is it's going to allow us to, very, very easily in a very simple workflow. I've taken a video, turned it into vectors, inserted them into a vector database, and then from that point forward, I now have another workflow that I'm using to actually search that vector database given some text as well. I'm doing all of this with embeddings, all of this with multimodal retrieval, and all of it with the ImageBind library as well. Again, this insert workflow is still running. Once that's done, I'll run the search workflow. But before I do that, I'm going to go back to this tab, to the presentation here. And I do want to say, if you want to reach out to me while that notebook is running, if you want to reach out to me, if you have any questions, or if you want to interact with me on Twitter or on LinkedIn, these are the links to use. I know I should have put a QR code here. I did not get around to that, and I apologize to all the folks where this is a little bit cumbersome. But feel free to get in touch with me. I'll leave this up for a little bit if any of you want to go to those URLs while we wait for the notebook to finish running. I know I'm getting a little bit short on time here, so
We also have one question from the audience, by the way.
Okay, sure. Let's go for that question then.
What encompasses an embedding model?
Yeah, that's a great question. An embedding model is just anything that takes data that you have and turns them into vectors, turns them into, let's say, turn them into something that represents that input data. And I know this is probably a little bit, for folks who are unfamiliar with RAG or unfamiliar with what embeddings are, it's probably a little bit of a deep dive. But essentially, you can just think of it this way, right? If I have unstructured data that is similar to each other, if I have images or text that is similar to each other, that is relevant to each other, the embeddings are going to be closer to each other as well when I generate those embeddings. This is still taking a while to run. I'm going to share this tab instead. This is still taking a while to run, but I think what I will do instead is if you reach out to me, okay, so it's done right there. I'm going to run these really, really quickly. So you can see what the output of it is like. And again, I know I'm a little bit over time, so I apologize to the wonderful hosts here, Eugene and Megan. But these I will, these should run pretty quickly. And again, it's just loading the model. It's going to vectorize this text here. What was unusual about the coffee mug? I'm actually going to show the results. And again, there's duplicate results here because I have run this twice. I've run the workflow twice. And then we can actually just show one of the images in the results. And you can actually see this is a frame from the Google I/O pre-show, and you can see the coffee mug right here. It's a little bit, it's a little bit strange for sure. And that is that you leave up to the large language model to answer after you do the retrieval step.
Cool.
So I'm going to stop sharing. And again, I want to say thank you to our wonderful hosts here for having me on this show.
Yeah, thanks for coming on, Frank. I think it would be really helpful if you could link us that notebook into
Absolutely.
the chat.
Yeah.
I'm sure the audience would really appreciate that. And I will let Megan introduce our next speaker. Megan, you're on mute.
Thank you for always catching me. Next, we have YData. YData is an OG synthetic data company based out of Seattle. They have been building innovative data solutions since 2019, and now they have a privacy-preserving data solution for RAG. And today we will be hearing from Fabiana Clemente, who is the CPO at YData, on their new developments.
Hello, everyone. Thank you, Megan, for the introduction. I'll be sharing my screen now. Okay. Okay. Okay, awesome. So, hi, everyone. Just as Megan introduced, I'll be showcasing privacy-preserving augmented RAG approach with an approach using synthetic data as a vehicle for privacy preserving in the realm of LLMs. My background is in applied mathematics and data science. I've been a data architect for from startups to big enterprises, and I'm definitely a data geek. Feel free to connect with me on LinkedIn. Happy to know your endeavors along Gen AI and LLMs. I'm passionate about generative models since quite some time. So, as you can imagine, synthetic data does not exist without you touching upon generative models. And that's why I'm bringing you this topic today. Why privacy preserving? Why does it matter in the realm of LLMs? Well, truth to be told, uh, there are compliance and privacy hurdles in order to adopt a generative model inside an organization. Either because you are dealing with sensitive information, for example, you have information and you have data among your text or even images that you don't want the models or the gen models to inadvertently memorize it. Also, on a different topic, it's very hard for you to scale anonymization in a way that you can handle the volumes of data that your organization have, right? So how can you ensure that you have everything really well anonymized, especially if you are dealing with a full database of knowledge management, right? So it's very hard to scale the anonymization techniques. It's very hard to ensure that every single data that you have inside the organization is privacy preserving or is anonymized in a way that is ready to be used for training or even just a RAG approach for an LLM. So all of that done manually is definitely very hard. And last but not the least, you also still have, and even though it seems like they are here for quite some time, there are still struggles around compliance with regulations like GDPR, CCPA, or even EPA, right? So it's very complex to define what is personal data, what is PII. It does depend on the context of your business. It does depend with whom you are sharing your data or how you are using your data. And all of this are the main issues around using proprietary data to train, for example, a generative model. And well, something that I like to say, don't tell anything that you want to keep private to an LLM. And well, here are just three different very public cases of how and where that happened, right? So you see that in Wired last year, it was mentioned that OpenAI GPT was just leaking secrets of private data that was fed into the chatbots. 11% of data employees paste data into ChatGPT, and that data should be confidential. So that's another risk. But of course, that's also a human risk, and about that, it's hard to do something just with technology. And last but not the least, we had the case of Samsung that definitely fed sensitive data to ChatGPT, and that data was inadvertently leaked to public eyes. So those are some things that you should have in mind. So you might think, no, it's my internal data. I'll be using this just internally. There won't be a risk. There's always a risk. So having that in mind, this is the one of the things that especially now with Gen AI, this is more true than ever. So even though you think your model might be your product, might be the thing that you want to put into place, so you want to deploy your generative model, your LLM, or any other type of generative solution, and you think that is your product, it is not. In reality, your data is your product. Whatever you have internally, how is your proprietary data shaped, the information that your proprietary have, the value that that data has, along with the privacy risks, it's in reality the product that you should be worried about building. And that's and that is a reality that we also observe with a lot of the news that are coming out, right? So data scarcity is definitely a reality. And that's why your data is actually the most important thing. How you collect your data, what data are you collecting, how you are processing it. Because after all, and this is something that we probably never thought about before, we are facing a potential data drought. And well, especially since big data, we thought that we were producing more data than ever, we were collecting more data than ever. But the truth is, these models are data savvy, which means that they very quickly build up on all the data that you have. They will need all the data that you have available to train, and they will need variability. They will need variance on your data. And that's why this is something that we were never expecting to have. And for that reason, if it's even more important for you to start building the technologies that you need in order to improve the quality of your data, improve the available data, and have the right variance to train these models. And again, if public information is scarce, proprietary data is the only data sources now available and unseen by these models. So there's something to have in consideration, and that's why adopting a more privacy preserving approach is so important. And well, uh, definitely data quality scales better than any data size. So training on small, highly curated, with high variability, with good representativity, it's a way to better scale your training, your RAG approaches, than just feeding a lot of data into them. This is not something that we are saying. This is Google's sentence of how important can be synthetic data for the future of training generative models. So these data sets that are highly curated can be easily built through synthetic data. Um, and besides ensuring privacy preserving, they also ensure the data quality that you will need in order to have a best performant model. And well, so although I have touched upon a bit on this, the fact is, why go synthetic for LLM? So of course you have the liability and legal issues that you are dodging with the use of let's call it synthetic data as a way of a fake data or data that is not real. Then you have as well the opportunity to fill in the gaps of potential missing data or missing behaviors. You can also synthetic data is also a tool for you to control potential biases. And last but not the least, it comes with the effectiveness, right? So it's easily available if you are using the right methods for synthetic data generation, and it's way cheaper and easier to collect it compared to real world data, especially given that public data uh, is no longer so was already seen by these models, right? So you are dealing with data scarcity anyways. So very quickly, I just want to showcase you what is the solution that YData is proposing here to, and how we are generating synthetic data. I'll be showcasing a very small demo. We do have the full demo available on YouTube. I'll make sure that I'll link that video for you, but let me quickly share my screen here. So as you can see, this is our a flagship product. So this is White Data Fabric. In here, I'm just showcasing two very simple pipelines and data workflows where we have used the approach of generating privacy preserving synthetic data. So in here, the step or the pipeline is very simple and has just two steps. The first one, where we read the text or we read the corpus, and you see this is just a some abstracts of medical publications, and as you can see, the type of language used is very formal and very scientific with very complex terms. And that's important for what I'm going to show next. We want to make sure that our synthetic data still captures exactly this formal language and formal way of describing the different very technical terms that are used, but we want to make sure that any names, anything that might be specific or might be more sensitive is kept out of the newly generated data. Also, our objective is to generate more data so we can feed highly curated data, but that has more variability when it comes to the type of sentences and corpus construction that we are observing. Of course, here is just simple statistics and simple metrics around the text itself. And in this step, the next step, I'm going to generate some synthetic data. What you see here in the first block is definitely the generated data. And one thing that is important for you to assess here is that definitely you can still see very technical terms that are used. You can still read the abstracts. They do make sense and they still are valid abstracts. But in case there are dates or anything that is more privacy preserving, like for example, information that you don't want the model to see, they were kept out and they are not generated. Very quickly, another example, very different, might be Amazon reviews. So in this case, as you can see, um, the the type of language is completely different, is way more unstructured with less technical terms, way less formal. So you might see some slang in some of the records as well, and you want to make sure that your synthetic data still keeps that. Furthermore, you might just want to augment certain type of reviews, right? So for example, you might just want to augment the negative reviews because they are way less represented than the positive reviews, for example. That's what you can build with the synthetic data. Here I'm showing you just a very short synthetic data generated, and as you can see here, you see that date time were removed just because you might be able to re-identify someone based on the dates that they mention. If there are names, they are also kept out, among other types of structure of sentences that might be considered privacy preserving. Furthermore, you see that the language of the synthetic data is still keeps a very natural and more chill out kind of sentences, and that's what we wanted to achieve. So it's not only a way for you to ensure privacy preserving RAG approaches or training LLMs, but it's also a way for you to augment the diversity and variability of your data, or even to control bias that was observed on your real data. As I mentioned, you can see this full demo with time. It's available online. I'll make sure to link that for you. I know this was a pretty fast, but if you want to test for yourself, we have here the QR code for you. You can register at ydata.ai/register, and I hope to see you there. And if there aren't any questions, just let me know.
Thank you for that demo, Fabiana. All right. So next we have our very own Eugen. So I will let him take the stage. But before that, what he will be talking about is how to pick your LLM stack. What goes into an LLM application? At least an LLM, an embedding model, a vector database, some data processing tools, and maybe a couple other things. Today, we have been hearing from the people who have been driving these innovations forward, and we'll hear more after Eugen's talk. But right now, he will be introducing a framework for how to think about these different tools coming together and covering some of the existing options that are available to us.
Cool. Thank you for introducing me, Megan. It saves me from having to introduce myself. So for those of you who have been following along with this series, you know that we've been doing a lot of work with getting the LLM stack introduced to people, as well as talking about what goes into it and what makes the LLM stack and what is so important about this. So one of the reasons why I want to talk to you today about picking an LLM stack and thinking about, the LLM stack and giving you this framework to think about it is because, well, let me get to it. There are hundreds of tools, and there's not really an easy way to figure out how to pick these different tools and how to think about these different tools. So there's hundreds of tools in the LLM stack. And in this specific market map, if you scan this QR code, it'll take you to a Medium article. In this specific market map, you will see that there are at least 100 tools in here. And this doesn't even cover the entire landscape, right? There's new tools that are popping up every day, like every week. Yesterday, I was just talking to someone who has just started another AI quality tool. So there's just tons of different tools that are popping up every day, every week, and I try to keep this as up to date as possible. I'd also like this to be an interactive presentation. So I'm going to ask some questions as I kind of go about this presentation, and I would love if you would respond in the comments and let me know kind of what you think. So the first thing we're going to talk about in this set of presentations is the LLMs. So if you recognize any of these companies, I would love to know which of these companies, which of these logos you recognize as I talk about this slide. Okay, so if you recognize any of these logos, drop them in the chat. We just want to see which one of these logos are recognized. So the first thing to know about LLMs is that here I have 12 logos for the LLMs in this stack. And these logos are definitely not a exhaustive list of the LLMs that people are working on. These are just some of the most popular ones that people know of, or some of the ones that I've been able to encounter during this time, right? So I see that some of you guys are participating, which is great. So some people have seen, Anthropic, of course, ChatGPT. You guys are calling OpenAI ChatGPT, which I guess is fair enough since that is their most popular product. That's their most well-known tool, right? So OpenAI is down here, and then you can see Anthropic as well up there. Mistral is up there. So Mistral is like the OpenAI of Europe. Then there's Symbol next to Mistral. They do conversational AI. So all of these things kind of do something different. Next to Symbol, so Symbol is this like black, I don't know, this polygon looking thing. Next to that is Arcee, which does, maybe it's Arcee, I actually don't know how to pronounce it. They do small language models. And then next to that is Noose Research. So they're a research lab based out of SF, and they do a bunch of research on how you can fine tune open source LLMs and things like that. Some of these other models are out there, like Gemini. We heard Frank talk about Gemini earlier today. Gemini has this huge 1.5 million context window. That was Google's kind of play to be unique in this space, right? Gemini has probably the longest context window out of any of these. And then under Anthropic, we've got Llama. In this case, I have Llama 2, but really we're on Llama 3 now. And if you caught my talk with Mark Huang from Gradient earlier, last month, then you'll know that you can actually fine tune open source models to have longer context windows, and that Gradient was able to fine tune Llama 3 to become a 1 million plus context window model. So I see some of these other people here are, recognizing Gemini. Someone who's not called ChatGPT, not called OpenAI ChatGPT. Someone else is here is talking about Mistral, right? Mistral is out of France. So these are just some of the models that are available. And all of these companies try to do something a little bit different around the LLMs. And maybe this is going to be a hot take, but most LLMs, of course, I will say OpenAI is the leader in terms of LLM functionality, LLM quality as of right now. But we don't know how long that's really gonna last, gonna be, right? LLM innovation and speed of development is just something that is going forward really quickly. And it's great that so many of these people are working on driving this forward. And I really hope to see that the open source side of things starts to take a leap forward in terms of the technology that's used and the technology that is available openly, publicly, right? And so some of these companies that are doing the open source stuff are like, Llama from Meta, and Mistral, and some of these other ones as well. And you'll see that I'll be talking about Hugging Face later. Hugging Face has a bunch as well. Okay, so other than LLMs, the next step, or the next set of tools that are part of this, would be the LLM providers. So if you recognize any of these, drop me a comment in the chat and let me know if you recognize any of the LLM providers. So you should at least recognize one of them, because we had someone from Fireworks, which is the little purple logo. We had someone from Fireworks come and talk just recently. So why is there even a set of companies that are built on LLM providers? Like, why are there a set of companies that are just built to provide you LLMs? Now, of course, not all these if you talk to these companies, they will say they do more than provide you LLMs, which is true. But I will say that one of the most integral parts of what they do is they provide LLMs. And one of the reasons why this is important is because LLMs, open source LLMs even, are difficult to run right now, right? They're not actually something that you can just pick up and put on any laptop, on any old computer, and get it to run, right? So NVIDIA, and you'll see NVIDIA's logo later on, NVIDIA is one of the most valuable companies in the world now. And one of the reasons for that is because they provide GPUs, and you need GPUs and CPUs to run LLMs. LLMs are huge, and they're very, very compute intensive. They're very, very computationally expensive. And because of this, it's not easy for everyone to be able to access and deploy and use LLMs locally. So there's a whole slew of companies that exist to provide LLMs. So there's Martian up in the first corner over here. They provide LLMs. Fireworks provides LLMs, right? So Arvind was just talking earlier about how Fireworks has recently released the ability to natively do function calling with Fireworks, right? So function calling is a piece of LLMs that allow you to build AI agents. And it's not simple. It's not something that you can just pick up any LLM and have it do, right? OpenAI kind of does it out of the box with their API. That's something that they do that they really drove forward, right? So AI agents has been around for a while, but they haven't really worked super well, and they haven't really worked effectively or efficiently or even dependably in production. And so some of these companies are now pushing this out, right? Fireworks, OctoAI. Someone recognizes OctoAI. That's great. So OctoAI is based here in Seattle. So for those of you who don't know, I'm in Seattle. OctoAI is based in Seattle. They have an event tonight, so I'm going to go out and talk to the OctoAI people today. The AI event scene in Seattle is, alive and well. I hope that it gets as fun and as hype as the SF scene, but we'll see. That's part of my personal goals. Other than OctoAI, there's Amazon Bedrock, as Andre noted. AWS Bedrock, Amazon Bedrock. I don't know. As far as I know, so this is more of an opinion take than anything else. But as far as I know, there's not a lot of usage of Bedrock, and it's probably not great. Even internally at Amazon, I've heard that it is not very popular. But we'll see, because technology evolves very fast, and whatever. And then there's Together AI. So Together AI, unfortunately, could not make it today. They were originally slotted to speak today, but they had a couple of speakers who were both out. So it was really unfortunate that Together AI was unable to make it. We could not hear about what makes their LLM special, their LLMs different. Below Together AI is a picture of a llama. This is really cute. I just put this in here because I wanted a cute picture of a llama. No, I'm kidding. So this is Ollama. Ollama is a tool that is used to run LLMs locally. They're a software company based out of SF. They've also hosted a lot of events. They hosted a lot of events last year. And I don't know if it was their event or if it was a Hugging Face event, but there was an event last year where they actually brought in like real llamas to the event. And I heard it was kind of a shit show, but It was kind of cool. Like I would have loved to go to an event where I could like interact with a real llama, right? So also like for those of you who have asked this question about like, llamas, why are llamas so popular for these kinds of tools? Well, LLM, right? So there's an A. If you put an A between the second L and the after the M, you get llama. So that's why llamas are so popular. Okay, next together is a company called Gradient. So earlier I mentioned that I talked with Mark Huang from Gradient, and they were the company that fine-tuned Llama 3 from a 8K context window into the 1 million, 4 million context window. So Gradient is providing not just these fine-tuned LLMs, they're actually closed source. They don't really offer open source LLMs for you to easily use, but they also build RAG applications, as we heard earlier from Frank, from Fabiana, from so many people about the popularity of RAG applications. Gradient also builds RAG tools. They also build AI agent tools. There's a ton of different things they do, but providing LLMs is one of their core competencies as well. Below Gradient, we've got a company called LM Studio. LM Studio is a lot like Ollama. What they do is they provide you a way to run LLMs on your local machine. And LM Studio is powered by this thing called Llama CPP, which is a tool that basically makes it so that you can run LLMs on your machine. Okay, so I see a question here about Cohere. You're right. So I'm missing Cohere from this list. To be honest, it's just because I don't really know a lot about Cohere. I actually met with some of the Cohere people at an event last year, and it seems they're doing a lot of different work in the space, providing a lot of different technologies. I'm actually just not very sure how to classify Cohere as a company. So that's part of the reason why they're not on here. And I also see something about Zillus. Zillus is not on here either because Zillus is not an LLM provider, but they will be in the vector database section. Okay, so we've gone through kind of the LLM providers. These are the companies that are just giving you ways to access LLMs, not just, they are giving you ways to access LLMs and some other things as well. Next, we'll look at embedding models. So someone asked about embedding models earlier. Oh, yes, someone said Ollama. That's the picture of the cute llama that I had on the last slide. So embedding models are incredibly important to the way that you build applications because they determine the context that the semantic similarity is done in, right? So earlier, someone asked a question about embedding models. What are embedding models? Really, in my opinion, embedding models are just any model that you can use to make an embedding. And an embedding is, oh, I totally forgot to say at the beginning of the slide, right? So if you recognize any of these companies, if you recognize any of these logos, drop me a comment below so I know who knows about these things and which one of these things are well known. I think there's 3 logos on this slide that I feel like everyone should get, and the rest of them, maybe not. But anyway, so embedding models are incredibly important because they determine the context in which the relevance of your unstructured data, of your text, of your images, videos, audio is determined. And so earlier, Frank told us about a really interesting embedding model that does 6 types of modalities. I don't have that embedding model on here. I don't have that company on here, but next time I will. It's great to learn about these kind of new things. I even learn about new things in these talks, which is great. But embedding models, the way that they work is essentially you have any deep learning model and you cut off the last layer of that model and you take the output of the second to last layer, and that is your that is your embedding. An embedding is just a long set of vectors, it's just a long vector, a long set of numbers. And why do you cut off the last layer? Why do you just take the output from the second to last layer? It's because as you run data through a model, the model learns new things about that data with each layer that you run. And when you get to the last layer, most models, not all models, right? Generative models are a little bit different. Most models, and even generative models, kind of work this way. So what they do is they predict what the most likely outcome is. So generative models just doing this on a large scale. They're predicting the next few outcomes, the next few tokens, whatever. And so that's what models do. And because models work that way, if you take the second to last layer, then that layer has all of the semantic information that model has, all the information that model has about the input data, all in that second to last layer before it makes a prediction. And that's how it makes a prediction, right? So that's what an embedding is. And this is how we compare unstructured data. We compare the embeddings. We compare the quantitative values of the semantic meaning of these different models, okay? So that's what these embedding models are. And these are just some of the embedding models that are on here. So we have Voyage AI, that comes out from a lab in Stanford. They have a lot of great models that are all hosted on Hugging Face, the yellow face with the two hands next to it, which really is kind of a strange name for an emoji, but Hugging Face is an emoji as well as the logo for the actual company, Hugging Face. Next to that is the Beijing Academy of AI. So they've also produced, oh man, I forgot what embedding model they produced. I think it's GTE large or maybe BGE. Maybe it's BGE. There's these two like very popular, and the other one is produced by Alibaba NLP, which is right below them. There's these two very popular embedding models that are, one is GTE and one is BGE. And I don't really know what either of these stand for, but they're both very popular and they both do very well on the MTAD leaderboards. The other two companies on here are Mixed Bread, which is the M, which is like from a research lab / university in Berlin. And then the other one is Gina, which is a global company that has people in SF, Berlin, Beijing, all over the world. So these are the embedding models. These are incredibly important, remember, because embedding models determine the context in which the semantic similarity of your inputs of your unstructured data is determined. So next up, we've got infrastructure tools. So these are tools that basically allow you to build LLM applications, right? Like earlier I was saying, one of the hardest parts about LLMs is, and why these companies exist that are just basically LLM providers, is because it's hard to build these. It's hard to access these. It's hard to get ways to effectively use these tools. Despite the fact that it's such an advanced, popular technology, it is not something that is very easily accessible. So, of course, I alluded to the idea that NVIDIA would be on the infrastructure tool map, and it is, right? So NVIDIA is up there, and NVIDIA is not the only tool, right? NVIDIA provides the GPUs. They do a lot of things, and later on today, we'll be hearing a talk from Jay Raj from NVIDIA, who works on NVIDIA AI, and he'll be talking to us about how NVIDIA is working with open source. Other tools on here that are important are Portkey. So Portkey is taking the idea of, Portkey is this, I don't know if you can see my mouse, but can you see my mouse on the screen? I don't know. But Portkey is the hexagon with the, I don't know, bash looking thing, hexagon thing. There's only one hexagon on here, okay? So Portkey is the hexagon looking logo. And what they do is they have taken the idea of an API gateway. So those of you who are familiar with software development, who are familiar with using APIs, who are familiar with API development, you'll know that there's this thing called an API gateway. And an API gateway basically routes all of your requests to the correct API endpoints. So Portkey has taken this idea of an API gateway and has taken it to AI, and they've created this thing called an AI gateway, which can allow you to route different requests to different LLMs and through load balancing and all these kinds of different things. So someone has told me that it's a hexagon plus a chevron. So thank you, Andre. I didn't even know that this was the term for that shape there, but I guess it's chevron. I'm thinking like it's the bracket thing. Okay, I'm getting off topic. Anyway. So other of these infrastructure tools, N8N, right? Viraj came and talked to us about N8N earlier today. N8N is up there. That's the fork looking thing that's in the pink square. Next to them is Lamini. So Lamini is interesting in the sense that from what I can see, Lamini is piloting the kind of expanding of allowing you to run LLMs on other GPUs, right? So one of the reasons why NVIDIA has such dominance in this market is because of CUDA. is because NVIDIA has their own specific language that is very efficient, that is very fast, and works really, really well for LLMs. But beyond that, there's other GPU providers out there that may be able to have similar capabilities. And one of those GPU providers is AMD. And Lamini is able to kind of leverage these AMD GPUs. And one of their plays is allowing you to run LLMs on AMD GPUs. Other than that, there's, of course, the usual suspects, right? You've got Snowflake. You guys should all recognize Snowflake. Down there in the bottom right corner, you got Databricks. So Databricks and Snowflake have this huge rivalry that's like a very it's like one of I don't know, I consider this one of those like classic tech rivalry companies. They both kind of have been around for a while. Databricks came from Spark. They came from the processing kind of like compute kind of angle, and they moved into memory. And Databricks was originally a company that wanted to be an AI company, but they were too early to be an AI company. And now that AI is popular and LLMs are popular, I'm sure the Databricks founders are very happy, and they're like playing quite a big role in AI. And someone mentioned Mosaic earlier, right? So Databricks bought Mosaic last year for like $2 billion, like 6 weeks after they started, which was insane. Or maybe it wasn't 6 weeks, but like they bought Mosaic for like $2 billion. Yes, Coke versus Pepsi. This is exactly how I feel like the tech world feels about Snowflake and Databricks. Beyond that, some of these companies, there's a Confidential Mind. They're a small company. They're out of, I forget which country they're out of, somewhere in Europe. They just raised a small pre-seed round. Pachyderm and Determined AI are on the sides of Confidential Mind. They just got bought by HPE like 2 years ago, 3 years ago. They also provide ML pipelines and ML infrastructure like this. Bento ML, Titan ML, they provide you different ways to take your LLM, your pre-built LLMs, and basically put it up and make it accessible. Very, very similar things. Beyond the infrastructure tools, we've got the data tools. So these are, I'm sure that some of you recognize some of these data tools. So please drop me a comment in the chat to let me know which one of these you recognize. So this first data tool here is Pulsar. And really, I don't know if I really should have Pulsar here as an AI data tool. I don't know if they're not specifically geared towards AI. Of course, Pulsar and Kafka, both originally Apache products or projects that do streaming, and they're very popular for streaming. They've been around since before AI, but they do a lot of AI. Oh, apparently I have the wrong logo for DVC. I will fix that. So yeah, please send me the right logo, and I'll get the right logo on there. Earlier we talked about we didn't talk about this. We heard from Xander Matheson from ByteWax, which is this like bee thing, the 4 hexagons, the yellow 4 hexagons in the middle. We talked about ByteWax. They do data streaming. Above them is Skyflow, because Skyflow does privacy for data. Earlier we heard from Fabiana about the importance of privacy, and really I should probably have why data on here as well somewhere. The importance of privacy for your data. Let's see, there's, so the V below Kafka, that's Visual Layer. They do data for computer vision data, basically processing computer vision data. They're very similar to Voxel 51. So thank you, Jennifer. Yes, Voxel 51, Unstructured IO, also both in the data tool section. And Voxel 51 will be, or sorry, not Voxel, Visual Layer, which is very similar to Voxel 51. So Voxel 51, we had Jacob come on and talk about what they were building way back in April, not way back, but 2 months ago. Feels like it was very long ago now. We had Jacob from Voxel 51 come and talk about what they're doing back in April. And today we'll actually have a talk from Danny Bixson from Visual Layer to come talk about what they're doing and how you can process gigabytes of huge amounts of video data on your laptop, which is actually quite incredible if you think about the amount of compute that goes into processing vision data. To be able to work on this on your laptop is really quite incredible. Let's see. Beyond that, there's some other interesting ones on here. So there's Proton by Time Plus, which is the weird circles going this way. I have no idea how they came up with this logo because I don't see a Proton in here at all. But they're a streaming platform. They're kind of like Apache, kind of like Pulsar, that kind of deal. And then of course earlier we also heard about Flink from Bytewax, and then there's Unstructured. Of course, Unstructured is surprisingly unique in this space. They're doing something that's not it's not particularly maybe technically hard to do. I don't know. Maybe I hope they don't. I hope no one from Unstructured is watching this and saying oh, actually, it's incredibly difficult to do, because it might be. But what they're doing is they're taking different types of unstructured data and they're piping it into, and they're creating pipelines to move unstructured data into your data stores. And there's a bunch of tools that do this. It's not just unstructured, but unstructured kind of does this in a way that nobody else really does. And they have all of this together in one library. And then next to unstructured is Airbyte. They also do data streaming. And I think that pretty much wraps up all of the interesting ones here in the data tool section. So part of how I feel about this section is that really data, like we heard earlier today, data quality, incredibly important, right? Data is going to be what drives the quality of your applications. So these are an incredibly important set of tools, and some of them are data curation, like Voxel and Visual Layer, and or data versioning, like DVC. And some of these are data streaming, like Pulsar or Bytewax or Kafka or Flink or Spark or Proton. And some of these are, other ways to move data around, like unstructured. So there's a bunch of different data tools in here, and I'm thinking about maybe splitting this up. But what you really need to know about this is that these are going to be the tools that are going to be the backbone of your application. Okay, so next up, we've got the vector databases. So we heard today from Frank, who's from Zillis. Zillis maintains Milvis, which is the bird, the blue eye thing. And earlier, someone said Zillis when I was talking about the LM. So actually, Zillis is on this slide, and it is the black square logo with the 3D. I don't know, plane dimensions kind of thing on it. Next to Zillis is Weaviate. And so we'll be hearing from Weaviate later today. I think they'll actually be speaking right after the break after this. So we'll be hearing from Weaviate later today. And then next to Weaviate is LanceDB. So if you have been following my channel for a while, if you've been following me for a while, you know that I spoke with Chung from LanceDB. He's their founder. And LanceDB is an interesting play in the vector DB space, in the vector space, because they were not initially a vector database. They were a file format, a file type. And what happened is that they basically took the Parquet files. And if you're familiar with Parquet, Parquet allows you fast, I think it's fast columnar access and maybe fast row access. I honestly get my rows and columns mixed up all the time. It's kind of like left and right to me. But I get these mixed up all the time. But they don't allow you fast access to random points, which is what vector DBs actually need. So in vector storage, unlike in regular storage, one of the most important things is the ability to do random access. And so Lance was able to kind of do a good job on that. And so that's why they formed a vector database out of it. Below them is a Hippo. So the Hippo is Marco. I'm actually not super aware of what they do, but they reached out to me last month. And so I figured it'd be a good idea to just include this on here as a known vector database. Next to Marco is an eye. No, I think it's supposed to be a camera. But that is Aperture Data. So Aperture Data is going to be our last talk of the day today. We're going to be hearing from Vishaka, who is the CEO and founder, one of the founders at Aperture Data. So Aperture has an interesting approach because they're not really a vector. I mean, they are a vector database, but they're also not really a vector database because they're a vector database with a graph store on top of it. So if you remember, if you watched my videos, you'll see that earlier this month I interviewed Jason Koo from Neo4j, and Neo4j is a creating graph database application that was originally made for Java, which is where the 4j comes from. And they're talking about graph RAG, which is one of the most popular, like hip methods of doing RAG. Right? Frank was talking about different RAG things earlier today. There's RAG 1.0, there's RAG 2.0, and there's a bunch of different processes in between. And so Neo4j does this thing called graph RAG, and Aperture Data has gone ahead and created a system that puts a graph on top of your vectors in one system instead of having to use two different types of software to do that. Next to Aperture is Chroma. Chroma is like a embedded vector database. It's kind of like Redis. Redis is below Marco, right? So Redis has been around for a while. They're an embedded database. They're mainly for caching. Chroma, also an embedded database. They may or may not stay that way. They're a very early stage company. Below Chroma is Pinecone. Pinecone is probably, arguably, the most popular vector database. Really great job by James Briggs. He makes a bunch of really good videos. And next to Pinecone is Elasticsearch. This is probably the what I would call the incumbent player in this space. They originally did fuzzy search. They do a bunch of unstructured data kind of search, and then they pivoted into vector search. And then lastly on this corner is Quadrant. Oh, and for you guys, wait, no. This I don't know. Okay, Quadrant is the queue. So yeah, that kind of wraps up the vector databases. Let's go to the next slide, which is orchestration frameworks. So I'm sure that you guys recognize at least two, probably three of these orchestration frameworks. So if you recognize any of these frameworks, drop me a comment in the chat. Let me know which ones you recognize. Okay, so when you're building LLM applications, one of the things you need to do is you need to orchestrate your tools. You need to put them together. You need to pipe data from one to another. You need to connect inputs and outputs. You need to have a way to retrieve data from your vector stores. You need to have a way to do a bunch of these different things. And so there are many, many different ways to do this. You can build your own orchestration tools. You can build your own framework. You actually don't need to use any of these, but these frameworks do make it a lot easier to build these. These frameworks make it a lot easier to get started into the LLM application space. So the most popular orchestration framework is the Parrot and the Link. So if you guys recognize that, drop me a comment, let me know. Next to that is a llama, which earlier, as I was saying, llamas are very, very popular in this space, probably because LLM. And then next to that is a company called, yes, thank you, Jennifer. These are LangChain and Llama Index. These are the two most popular orchestration frameworks in the space right now. Next to that is a company called Boundary. So what they do is they basically, if you think about TypeScript and JavaScript, if you're familiar with these, TypeScript was JavaScript with enforced typing. And so that's kind of what Boundary ML is like for LLMs. They kind of enforce a type of output. Below Boundary is a company called Microsoft, a very small company out of Red. No, I'm just kidding. But Semantic Kernel is not a huge project at Microsoft. Semantic Kernel is their kind of like LangChain play. Yes, someone else recognizes LangChain as well. BML is cool. BAML, I assume you're talking about Boundary. Yeah, it's a pretty cool language. It's really hard. I mean, like I thought it was really hard to get started with. I know they've been doing a lot of work on it. It's been getting a lot better, but it is very cool. Let's see. Also in here is Haystack by DeepSet, which is right below LangChain. That's the green one with the H and the loop around it. So Haystack is interesting in the sense that they did not originally start as in the LLM space. So Haystack was originally an NLP pipeline for enterprise use cases. So they have an interesting kind of like niche or area in here. So they help you with NLP stuff, and they're very enterprise heavy. So they have a lot of enterprise ready features, very good for bigger kind of projects. Then there's also Flight. Flight is by Union AI. They're also based out of Seattle. And they came out of Lyft. So Lyft needed a way to orchestrate some of their LLM, not LLM tools, ML tools, actually, nothing to do with LLMs. And they spun out Flight as an open source framework, which then developed eventually into a company. On this other side here, on your left-hand side, probably is, maybe your right-hand side, is Grip Tape, which is a small company that does something very similar to LangChain. And then under that is DSPy. And so we'll actually be hearing more about DSPy in a few minutes when the Weaviate people come, because I'm not entirely sure if we'll be hearing about DSPy from Weaviate, but I have been seeing them do a lot of events together. And one of their developer advocates has been talking a lot about DSPy on Twitter. And in fact, I pretty much only heard of this framework because one of their developer advocates was talking about it so much on Twitter that I was like, okay, I'll go take a look. Okay. So DSPy is a orchestration framework that I'm sure that I would bet that the Weaviate people will talk more about later on, and I will let them talk to you about it because I don't know that much about it. Next is the quality tuning stuff. So this is really, really important for basically production, right? When you're putting things into production, you need to ensure that they're high quality. And we heard from Honeyhive, which is this like 3 set of hexagons earlier today. They were the first talk today, right? We heard from Mohawk from Honeyhive. He gave a talk about LLM quality tuning and ensuring that your LLMs are high quality in production. And later on today, we'll be hearing from Aparna from Arise. Arise is the, I guess, is that also a chevron? I guess it's also a chevron with a dot, the chevron dot. That's Arise. Next to that is Trera. So Trera is a company that they created this product called TrueLens. They came out with this kind of like triad for RAG quality. And they actually got acquired by Snowflake. So maybe I should just have Snowflake in the quality tuning area. But as far as I understand, they're still kind of operating independently. Some of these other tools here include like, YLabs. So YLabs is a tool that's much like Honeyhive, much like Arise. They kind of tell you like their observability monitoring. They tell you why things are, going wrong if they are in your data and things like that. Many of these other companies are quite a bit smaller. And the reason for that is just because quality tuning is something that's quite new and quite, it's not like quality tuning, the concept isn't new, but like in terms of LLMs are in such an early stage of development. The technology is just in such an early stage of development that a lot of the quality tuning stuff is not super developed. And so a lot of these companies are out here developing some of these things. So actually like Arise and YLabs and Trera and Aporia, which is next to Trera, and Honeyhive, these actually all came out of the ML ops craze from 2018 to 2022. And they've just recently kind of developed or turned into these LLM ops based companies. Okay, let's take a look at the next slide. So these are some QR codes that you can scan that will take you to some code samples. This pretty much wraps up my covering of these tools. I hope that this kind of set of this kind of introduction to a bunch of these tools was helpful for you in the sense that it allows you to understand this kind of framework in a better manner, right? So I gave 8 different sets of tools for you to think about, with the possibility of thinking about data processing or data tools as a completely as one entity, or as split out into 3 different entities. So there's a bunch of different ways that you can think about this, but I hope that this was a good way for you to start thinking about how you can build LLM applications with LLMs, LLM providers, quality tuning tools, vector databases, embedding models, and all sorts of other tools that will help you build large language model applications. And this set of QR codes here, this will take you to two different repos on GitHub, where you can figure out how to build, where you can like just find some code and figure out how to build some of these AI applications from scratch. This is like a proof of concept kind of thing. This is not really going to build something for you in production, but this will help you get into proof of concepts to build different LLM tools. I only have a couple more slides left here, so I will round out probably just at the time that I predicted. So these other two QR codes are for those of you who want to keep up with more events. You can scan that code. It'll take you to our calendar, to the OSS for AI calendar, and you can use that to keep up with more events. And then next to that will be jobs. So if you are interested in jobs in AI, if you're interested in jobs in open source, we do kind of keep sending out these emails to get people into different jobs and things like that. And I believe that's actually it. Oh, keep up with me. Aha, I forgot. This is the most important slide, of course. Yes. You gotta, if you want, if you want to keep up with me, scan this QR code here. This QR code here will take you to my LinkedIn, and you can kind of keep up with all the things that I post on LinkedIn, which is some insights into LLMs, some of the things that I care about. For example, how I think cosine similarity is a stupid similarity metric, and how a paper that came out earlier this April really vindicated my belief of this, and some other things as well. Thank you, Jennifer, for the kind words. So at 10:20 exactly, I've wrapped up my talk, and we're gonna have a quick 10-minute unofficial hiatus break kind of thing, and then at 10:30, or I guess depending on where you are in the world, at 10:30 Pacific time, we will hear from Weaviate. So we'll hear from Zain Hassan from Weaviate. Originally, we were slotted to hear from Philip, but there was a last-minute change there, and so we'll be hearing from Zain. I guess I'll just keep this slide up for a bit, and we'll take a quick 10-minute break, and we'll be back very soon. How do I? Let's see. I'm going to remove myself from the stage. Or actually, I'm going to keep up a series of slides. So here we go. We'll do this. We'll do this slideshow here. Autoplay, loop, play. Okay. So this will get you access to all of the QR codes I just talked about earlier. Oh, so I guess I'm actually here, so I'll just answer some questions while we're here. But we don't really, we're taking an unofficial break, but I guess we'll just answer some questions while we're on this break. Can reducing the dimensions of an embedding model improve accuracy of retrievals for a domain? Can reducing the embeddings of an embeddings, so dimensionality and embedding models don't the accuracy is not highly affected by the dimensionality of the embedding models, right? So actually, if you want better accuracy in a specific domain with your embedding models, what you really want to do is you want to have an embedding model that is trained on a specific vertical. So for example, and I give this example all the time, so I don't know if I've given this example already today. I say this one all the time. It's if you have animals and you have cars, one of the things that people like to do is they like to name cars after horses because of the whole horsepower thing, right? So you have like Bronco, Mustang. These are both cars and animals, but your embedding model may mistake either of these for an animal or a car. But then there's things like Pony and Ferrari, and Ferraris are clearly a car and ponies are clearly an animal. But depending on your embeddings model and what it's trained on, it may mistake Bronco or Mustang for a car or a horse, depending on your embedding model and what you would like it to mean. Thanks for the comprehensive tool overview. Thanks, Roel. Give us a summary of your dislike for cosine similarity as a metric. Okay. So if you've known me for a while, you've probably heard me talk about how I think cosine similarity is a bad distance metric. So I want to preface this by saying it's not necessarily a bad distance metric. It is just so there's a couple reasons. So one is we started NLP, this whole NLP space. So if you have been working in AI for a while, you kind of know about RNNs and one-hot embeddings and all of these different things. And then now we've got bag of words types of stuff like that. And one of the ways that we would measure the distance between some of these embeddings that we've generated for these words in NLP is cosine similarity. And this was actually pretty correct in the beginning, right? We just said, hey, we need any similarity metric. And as long as we're using a consistent similarity metric, and as long as we're training our data on models that are, as long as we're using data in or on models that are trained on the similarity metric of cosine similarity, we will get the same kind of distance between all these things. And actually, so Zane from Weavier might have more to say about this later, but cosine similarity is something that we took from the beginning. And then I feel like people just blindly use it through the space, because you ask a lot of people that are working in the space, why are you using cosine similarity? They'll be like, well, this is what XYZ used, or this is what ABC used. This is what they used in the tutorial, the thing that I saw online. And that's totally it's like you didn't even think about it. Why did you just use that? So cosine similarity is actually, what cosine similarity actually is it is the normalized version of inner product, or IP. Copy paste. Exactly. It is a copy paste. But cosine similarity, what it actually is, it's the normalized version of inner product. And that means that what it is inner product is if you take two vectors and you multiply x1 and y1 and x2 and y2, and you kind of just do that all the way throughout. That's what inner product is. And what inner product is spatially is if you take one vector and you project another vector on top of it. So obviously my hand's the same size, so it's not a great show, but you project one vector on top of another vector. That's what IP is. It measures the magnitude in space as well as the angle of two different vectors. With cosine, what you're doing is you're taking the normalized value of IP. So what you're doing is you're taking IP and then you're dividing it by the magnitude of A and the magnitude of B multiplied. And so what you actually get is you get this measure of this angle in space, right? So A, this is more computationally expensive. You have to do more computations. You have to do IP, and then you have to do magnitudes, and then you have to do divisions. And so it's a lot more compute. And B, you're actually losing information because you're losing the magnitudes. So now you only have the angle, and you can't measure as precise of a distance and similarity metric. You can't measure as precise or granular of a similarity using using a cosine as you can with IP. So it's more expensive to do, and it's a less granular metric. So I think cosine similarity sucks. So there you go. That's my dislike for cosine similarity as a metric. Okay, so I took a long time to rant about that, but that's totally fine because we're about to start with our next talk. So our next talk will be and I'm gonna quickly talk about this for those of you guys who are here. So I will be speaking on July 11th in San Francisco at Shack 15 at Arise Observe. So if you will be in SF and okay, this is not what I thought. Okay. If you will be in SF on July 11th, feel free to scan this promo code and use it to sign up. Or I actually have one extra promo code for a VIP pass. And if you would like that, send me a message. Okay, I'm going to remove this from the stage now. So this is perfect timing for our next talk. So our next talk will be from Weaviate. And our next talk was, I originally wrote this intro for Philip, but we're actually going to have another person from Weaviate. We'll have Zain Hassan. And Weaviate is doing some incredibly innovative work in the generative AI space, in the space of vector databases. So earlier we heard from Frank, who's from Zillis, who also works on a vector database. And now we'll hear from Zain. And from what I hear, Zain is an expert on this generative feedback loop and is an expert on building very robust retrieval augmented generation applications. And so, since Zain is already here, I'm going to welcome Zain to the stage, and I'm going to take myself off of the stage.
Thanks. Thank you so much. So last minute replacement for Philip here, but I'll try to fill the big shoes here. So I'm going to talk a little bit about advanced retrieval augmented generation techniques and show you how you can do that with Weaviate. So like was mentioned already, I work for Weaviate. My background is in engineering, and then in graduate school I went into data science. I've been in the machine learning field for about 9 years now. The most important thing to know about me is that I'm very passionate about AI and the good that it can do for us. Right? Okay, so on to the topic. RAG is a very kind of nebulous, it sounds a lot more difficult than it is term. So I'm just going to ground my talk in this one example. So think about an average human doctor, and we're going to try to build a RAG pipeline that emulates or assists a human doctor. And so the average human doctor, at least in North America, studies for 7+ years after undergrad. So the total study period is about 11 years that they go through. And in their entire lifetime as a doctor, they see about 100,000 patients. And so when you walk into the doctor's clinic next, they're kind of formulating, they're going over everything that they've learned, all the patients that they've seen, and they're trying to understand which of those experiences are relevant to your use case and which ones are irrelevant. Right? So if we're going to build a chatbot that emulates what a human doctor does, it's going to need to be pretty advanced. Right? It's going to need access to a wide knowledge base, similar to a knowledge base that a real doctor has. So 11 years worth of study, 100,000 patients worth of experience. And honestly, the knowledge base can even be larger. It's going to need to efficiently search over that knowledge base to find out which historical patients are relevant, which publications and which information from medical literature is relevant to the patient that's right in front of them. It's going to need to reason or understand the information that it's searched over and what applies and what doesn't apply to the current patient. It's going to need to be explainable, and this is particularly important in the medical domain. And you could take this application, you could kind of strip out the medical component and add in whatever your component is, but at least for medicine, it needs to be explainable. The doctor needs to prescribe the right thing to you for the right reasons. And so the AI needs to give you the right answer for the right reasons as well. And we need to explain that as well. And to complete the circle here, it needs to be real time. So it needs to be performant, and it needs to do this pretty quickly. So if this is the example that we're going to ground the rest of the talk in, let's move forward with this. Right? At Weaviate is an open source vector database. We love everything open source. So every slide in this talk is going to use an open source tool, and the link at the bottom is going to take you to that resource. So whether it's a machine learning model, whether it's on Hugging Face, whether it's a GitHub repo, everything is linked at the bottom. So you can literally rebuild this entire talk and the tool that I'm talking about here yourself if you wanted to. And it's all open source with permissive licenses. All right, awesome. So the approach that I'm going to talk about here is something that I've named the RAG Doctor. And how it works is we're going to take the simplest approach of how people use language models. So a patient walks into your clinic, they tell you they have so-and-so problem. The simplest thing you can do is just provide that over to a language model, and the language model then outputs some form of cheat sheet that the doctor can then read and use. Right? And this doesn't have any RAG. So we're going to add some components to this. Right? We're going to add some form of knowledge base. So this is information about past patients, information from medical literature, and we're going to store that into a database. So I've got here a vector database, but technically this can be any database. It doesn't need to be a vector database. And before we go to the language model, we're going to take a kind of a tangent. We're going to take a detour, and we're going to take the patient information here, and we're going to use that to query the vector database. And the vector database then outputs relevant responses from this knowledge base, right? So this might be millions of articles. It extracts out the 5 articles that are relevant to this patient, and now we can augment that. We can stuff that into the prompt that was going to the language model. Right? And so this is our basic RAG approach. And the rest of this talk is going to be elaborating how you can go above and beyond. How do I improve on top of this? Right? So in this case, we've got our indexing phase, and I'm breaking it down into 3 phases because I'm going to propose at least two mechanisms to improve each phase. Right? So we've got the ingestion and the indexing phase. How do you get your data and put it into the vector database? We've got our retrieval phase. How does the vector database retrieve relevant articles that are pertinent to that particular patient? And then we've got the generation phase. This is where the language model takes that patient's information and everything that you've suggested that might be relevant and then formulates some form of answer. And so this is our basic RAG stack. We've got the retrieval piece, the generation piece, and then we've got the glue that sticks those, integrates those together. Okay, so in our particular example, the data set is all important, right? It forms the knowledge base that we're going to RAG over. In this case, this is an open source data set called the PMC Patients Dataset, and this is a live data set, by the way. They keep adding to it, and they keep increasing the amount of data in here. When I built this application, it had about 170,000 patient summaries. So one patient summary is the account of one patient walking into the clinic, things that they were prescribed, tests that they had run. So you've got 170,000 of those, more than any patient, more than any doctor has seen in their working time in the profession. And then it also has about 1.4 million articles from PubMed. So these are abstracts, and there's also embeddings for all of these that are generated beforehand that you can just start using and insert into a database. The images, the data can also be images and charts, but for the purpose of this example, we're only going to think of it as text. Right? So these are just texts that are going to be embedded using text models. But later on, you can also try to see how you can pass in images and charts for these. And because the data set is a retrieval benchmark data set, we know the ground truths. So given any patient, the data set tells you which 5 patients are the closest. So you can use this to benchmark your vector database as well to see how well your retriever is working based on the ground truths that this data set gives you. So in this data set, you've got kind of relevant article ground truths as well as relevant patient ground truths, right? So the relevant articles come from here, and the patient ground truths come from the 170,000 patient summaries. So that's going to formulate our knowledge base. And this knowledge base is honestly larger than any doctor has available when you walk into the clinic. Okay, and then the vector database we're going to use here is Weaviate, and we've talked about this. Previous speakers have mentioned this, so I'm going to quickly gloss over this. But the main idea here is a vector database allows you to scale vector search up to billions of documents, right? So here we've got about 1.6 million objects. If we had billions of objects, we would still be able to perform in real time and scale this chatbot up. and it performs semantic search. It performs search using machine learning models that embed data, and this is a topic that's already been covered. And so the idea here is the patient tells you that they're having pain in their left shoulder and they have numbness in their thumb and index finger, and that goes into your vector space, and out comes retrieved objects. And so here I'm showing an example of multi-vector retrieval, where I can retrieve from an index of patient cases. These 3 patients here that I've got might be the most relevant to answer this query. And I might also retrieve from an index of articles on the other hand, right? So now I can kind of reason over both patient cases as well as articles. So Weaviate supports multi-vector retrieval as well. Okay, so now for the rest of the talk, I'm going to try to go into the details of how we can do better. Right? Based on this basic RAG stack, what are some improvements that we can add to the indexing, the retrieval, and the generation phase that will take us above and beyond the basic RAG stack? And so the point here is not for everybody to become an expert in RAG. The point is to introduce these techniques to you and to link relevant resources so that after these 30 minutes, you can have jumping off points where if you want to do query transformation, query rewriting, you want to do re-ranking, hybrid search, some of the techniques that I'm going to talk about, you'll have resources that will allow you to introduce those into your pipeline and evaluate those as well. Okay, so let's start with these so-called advanced RAG techniques. So we're going to start off at the bottom, and better RAG starts off even before you've indexed your data into a vector database. Some of the choices you have to make are, how do you chunk your data? And so typically, the reason why this is a difficult choice here is because depending on your domain, depending on what your data is about, you want to extract out text that is semantically coherent, right? You want to have kind of one trail of thought in one chunk, so that the vector that you generate is captures that information. If you've got too big of a chunk, then you might have multiple semantic meanings behind that, and then the vector is not able to represent the vector that gets generated to capture that chunk, can't follow along, right? And if the chunk is too small, then it might not have any meaning at all, right? So imagine if my chunk is just one word or one token, then in that case, it has no contextual meaning. Right? I can't understand a lot from that. So there's a whole separate blog on this about choosing chunks that are too large or too small and why this is not a trivial kind of hyperparameter to set. Right? So typically what people do is called fixed size chunking. And so this is from Greg at Data Indie, where you can give it your entire document and you can say, I want chunk sizes of 35 characters or 300 characters. And the important thing here is the chunk overlap, right? This is important because you don't want context to be left off right at the ending point or the starting point of the next chunk. So you want there to be a little bit of overlap so that if 2 chunks that are consecutive are retrieved, you have some information before and after what's happening. So this is basically the starting point of how people get introduced to chunking. I'm going to talk about 2 more options that you can use when you're chunking. Right? One option is called semantic chunking, and this is a relatively simple idea. The idea here is that you can go sentence by sentence, and your job is to identify how similar the previous sentence is to the next sentence. If they're similar enough, you don't create a new chunk, you just append the second sentence to the chunk of the first sentence. And every incremental sentence, you decide whether that sentence is different enough from the previous sentences that are already in the chunk to justify its own chunk, or whether it should just be accumulated into the previously growing chunk. And so this is called semantic chunking because you're trying to understand the meaning of the previous sentence, and you do that by embedding the previous sentence, and you embed the second sentence, and then you calculate the cosine distance between them to get an idea of how similar or dissimilar those 2 sentences are. So when you do this, so this is a graph that's a bit involved, so I'll talk about what you're looking at here. On the x-axis, you've got the sentence index, right? So you might have the 257th sentence, you might have the 7th sentence here. And notice how the chunks are not a fixed size anymore. They're based on the semantics. So the idea here is, this is a Paul Graham essay. And if you read top to bottom, as long as the topic that he's talking about doesn't change, it'll belong in the same chunk. The minute he changes topics, it'll create a new chunk because the semantics change, and now you chunk it right there. So every peak here is one where you're going to chunk, and everywhere the semantics, the cosine distance is lower than that threshold peak, you're going to accumulate in the same chunk, right? So this might be a kind of a quick divergent tangent where he's talking about a topic and then he diverts over to a topic for a couple of sentences. It deserves its own chunk, and then you get back to the same topic or something like that. And so this is semantic chunking, second technique. And a third technique that's quite powerful as well is to use a language model to do chunking for you. The idea behind this is interesting because you take a language model that's trained to create propositions, these semantically isolated and independent sentences for you. You give it your paragraph or your chunk of data, and it will now generate these propositions. And now from that, it will also accumulate these propositions into sentences, and maybe even the sentences into passages, so that now you can retrieve based on these kind of glued together propositions. And this is also quite powerful. And then you can decide whether you want to retrieve based on propositions or combinations of propositions, sentences, or even combinations of sentences called passages. And this comes from a recent paper that we reviewed, and the model is also open source. You can see the link here. If you're interested in following along with these recent developments, we do release Weaviate paper reviews where I cover weekly some of the advancements that are happening in the field, and and they're very digestible 1-2 minute summaries of papers from academia, mainly focused around RAG, information retrieval, that sort of thing. Okay. The other thing that you can also do here is filtering with metadata. This is one of those techniques that is very powerful, and it's very simple, actually. The idea is that you can store metadata along with vectors to choose what's relevant and what's not relevant to a particular query. And so the idea here is you've got your database, and so you've got a metadata that tells you the user, so Alice, Bob, John, and then you've got a vector capturing that data. The query comes in, and the query, notice how it's only relevant to one of these users, only to Alice. So what you can do is filter out irrelevant objects, not based on their vector, but based on their metadata, right? The user name here in this case. And you can do this in two ways. You can either pre-filter before you conduct the vector search, or you can conduct the vector search and post-filter afterwards. But this filtering technique is quite powerful, and it further improves the quality of results that come back from the vector database. And the reason why this is part of indexing is because you have to add this metadata when you're indexing the data, so that later on at query time you can actually filter based on that metadata. And so with Weaviate, this is a simple kind of one-liner where you can add one filter, or you can add compositions of multiple filters across multiple metadata fields directly into your vector database query. If you want to learn more about it, there's a whole kind of explanation page over here at the bottom. Okay, so the next step, two more techniques to do better retrieval, and this has to do particularly with the vector database. The first thing that we're going to talk about is hybrid search. Some other speakers might have talked about this, but the main idea here is that depending on your domain, semantic search, vector search might not be the solution, right? Or it might not be the silver bullet. And so the idea is that in medicine, you've got a lot of abbreviations, right? You've got kind of abbreviations, you've got specific keywords, medication names, disease names, anatomy names, and there, if your machine learning model is not fine-tuned on that particular vertical or that particular domain, as was being said earlier, the embedding model might not be able to differentiate between these concepts. Right? And so here, you don't just want vector search, you don't want just some semantic matching, but you also want to be able to match on the keywords that are being mentioned in the medical domain. And the medical domain has an abundance of those. So what hybrid search does is it allows you to conduct both in parallel, and then you fuse the scores afterwards. Right? So in Weaviate, we natively support hybrid search, where if you perform a hybrid search query, it's going to perform both a vector search and a keyword search, and the algorithm underneath that's being used is a BM25 search. And then you get two lists of ranked results for each object. And then you have some sort of kind of rank fusion algorithm that decides how much importance to give to the vector search results versus the keyword search results. And this is quite powerful. In order to go from pure vector search to a hybrid search, all you have to do is change one line of code where you would go from a vector or a near text query to a hybrid query. And now you're kind of accessing this secondary keyword BM25 based search that's being maintained within Weaviate. And so this is quite a powerful tool, and pretty much everybody that uses RAG in production is using some form of hybrid search, specifically if they're doing text-based retrieval. Another powerful technique that people are starting to use is query rewriting, and more generally query transformation. The idea here is to admit that we don't know the best way to talk to language models or to vector databases. So what we do is we get a language model to rewrite our queries to the vector database, as well as our queries or prompts to the language model. And so there's open source frameworks that allow you to do this. For the language model piece here, there's a framework called DSPY that Weaviate integrates with, and there's a link here that you can look at for all the different ways that you can do this. And for the vector database, there's a open source model that also does query rewriting for you. And the idea behind query rewriting is relatively simple. This is the query that the doctor or the patient might identify as important for the vector database. You give that to a language model to rewrite, and this is the rewritten query. Right? And notice how the rewritten query is kind of isolated, chunked. There's kind of smaller sentences that identify the semantics here. And how this works is this particular stack, right? You take the input, which would be this query here. Instead of going directly to the vector database, this goes to a rewriter model that has been trained to do this. And if you want access to this rewriter model, it's over here behind this link. The query is rewritten, so you get the rewritten query, and then that goes to your retriever. And in this case, that's a vector database. It can be a web search as well. And now the documents that come out of the retriever should be a lot more relevant because the query is optimized and rewritten for that particular retriever. And now the LLM that reads reads these documents can now take advantage of those relevant objects. And for DSPY, this is more of an iterative process of automatic prompt engineering where it'll start off with one prompt and then it'll iteratively improve the prompt until you get the best performance. So here you need to specify an input and an output, and then it'll incrementally change the prompt to get you better and better outputs. Okay, and the last thing that I'll talk about is better generation. And so this also has to do with how you can make the things that you're providing to the language model more and more relevant. And so if you actually give it irrelevant things, and it might hallucinate, it might feel the need to use that irrelevant data, which will mislead the generation portion. So the first thing that you can do is this process called autocut. And this is quite simple here as well, right? Even after you've invested all of this time in choosing the right embedding model, choosing the right vector database, using hybrid search, using all these advanced techniques, you might still get back results that are irrelevant. And so what AutoCut proposes is if you can identify that there is a big drop in relevance score, you automatically just cut off those irrelevant scores and you keep this kind of high quality, high relevant objects, and that's all you pass to your generative model. And so the way we identify these irrelevant objects is by looking at jumps in the relevance score. Right? And so how this works in action is the query goes into the vector database. The vector database retrieves your patient cases. So in this case, I'm only retrieving patient cases, no article IDs, just to simplify. And the vector database is also going to output some form of similarity score. Right? And one thing I want you to notice is that the similarity for the top 4 patients is a lot higher than the similarity for the last 2 patients. And the only reason you get the last 2 patients here is because you asked for 6 patients, right? 6, you did a limit of 6 and you got back 6. So what the AutoCut feature is going to do is identify that there's a big jump between the first 4 and the last 2. And so we automatically cut the last 2 off, even though you asked for 6, and you'll get back this kind of high quality top 4, and it's going to drop out the last 2 there. And so when you want to actually trigger this with Weaviate, it's a simple kind of parameter in your near text query where you say, I want one list of similar objects. If there is a second jump after that one list, you automatically take that off. If this was a 2, then this would now give me this first continuous piece of similar objects and then the second piece as well. And then the last piece that you can also add to your RAG pipeline, this is also going to improve the relevance of the objects that you're going to give to the language model, is a function called re-ranking. And the idea here is that we've got one model here, usually a bi-encoder, that the vector database uses to identify relevance and rank relevance to the query. It pays off to have another much more powerful model look at the query and the objects that are retrieved one at a time and propose whether or not they're actually relevant. And so the idea here is to do another ranking step. That's why it's called a re-ranking step. But now this time using a much more heavier, powerful model that might not be doable across all of your billions or millions of objects, but it is doable over a smaller subset of candidates that the initial search, the vector database, has deemed worthy. And so in this case, what happens is you go to your vector database, you pass the query in, but now you overfetch. You fetch maybe 15, 20, 25 relevant articles, and you ask the vector database how relevant they actually are. Then you give these relevant patient cases to your re-ranker model, and the job of the re-ranker model is to re-rank. Right? So the re-ranker model looks at the query and each patient case on a case-by-case basis, one at a time. It performs inference for each one of these, and then it decides, okay, the first patient case here is not actually that similar. It gets a score that gets demoted down to 3rd place here. Right? The third one is actually much more relevant to this particular query, so it gets promoted up the ranks to 1st place. And it does this re-ranking for each one of these objects one at a time. And now you get this re-ranked score, and now you can take maybe the top 6 or the top 5, and those are guaranteed or most likely to be a lot more relevant because the model is much more powerful and it's trained specifically for this re-ranking phase. And so with Weaviate, to introduce this new pipeline, it's again just another parameter in your near text query where you can configure it to use re-rankers from companies like Cohere, from Gina, re-rankers that are specified on Hugging Face as well. And those are all the techniques that I wanted to cover. On a high level overview, you can improve indexing by doing some of these techniques that I've mentioned, retrieval and generation. And a lot of the techniques that I've mentioned here, I haven't, by no means have I covered all of the techniques. So if you want a more detailed approach, these are some of the papers that that kind of motivated this talk. There's also a 3-part series from O'Reilly on advanced RAG and building production level RAG. So you can read into these resources. And the last thing that I'll talk about is Verba, which is an open source tool that we've built at Weaviate that gives you a kind of a production level RAG app where you can use it to chat with your own documents. And so initially, if you go to verba.weaviate.io, we've indexed all of our documentation, blog posts, podcasts into it, so you can ask it any question about using Weaviate. But the cool thing is that it's fully open source. You can take Verba and you can put your own documents into it. You can reskin it. So I invite people to have a go at that. And give us a follow if you're interested in this. Love to talk further. And if you have any questions, we can take some of those now. And if you want to connect later on, I'm more than happy to have a one-on-one chat or even just connect online. Thank you so much, folks.
Great. Thank you, Zane. We do actually have a question. Somebody has asked, what language is this in?
Yeah, so Weaviate itself is written in Go. All of the examples that I showed in my slides are using the Python client for Weaviate, though.
How many different SDKs can we use to access Weaviate?
There are so many different. So Python is the most popular one. Then we have a TypeScript and JavaScript SDK. There's also a Go SDK. I believe there is a Ruby SDK as well that was community contributed. So if you go online, there's a whole slew of different SDKs that you can use to access the underlying database.
And what about for Verba?
For Verba, Verba is mainly written in Python. So if you want to modify this, you can have a look at this repo, but this is mainly in Python. So if you have a look at this, you'll see it. There's both the front end and the back end that you can use. And we've also added, so one thing that you'll notice is here, a lot of the techniques that I'm talking about here, they're actually on the roadmap to be added into Verba. So if you look at this, a couple months from now, we'll actually have implemented all of these advanced techniques natively into Verba. So when you start using it, you'll have you can take advantage of those techniques.
Cool. Thank you very much, Zane. So if there's no other questions that kind of come in the next 15 seconds that I'm kind of like talking, I'm going to bring up Megan to the stage to introduce our next speaker. And Megan, you are on mute.
Thank you again. Without fail, I always forget. Next up, we have Visual Layer, and Visual Layer is building the next Gen AI tool for your computer vision data, and it is led by a group of visionary technologists, including Dr. Danny Bixen here, who has been working on AI ML with CMU and Apple since 2009. And he's here today to talk to us about the exciting features and innovations that he's working on to expand access to analysis for your computer vision data. Dr. Bixen, I'll let you take the stage.
Hello everyone. So thanks so much for the invitation, Eugene. It's super kind to invite us. And so I hope I'll try to share my screen. I hope it will work. Whoa, that's okay. Yeah, so I'll tell you today about Visual Layer. We are building tools to manage, visualize, and search videos on a large-scale dataset, but you can start for free on your laptop and then go and scale to the cloud. So I'm Danny Bixen. Previously, I had a startup in Seattle. Startup was acquired by Apple, and I joined Apple Deep Learning Research R&D Center in Seattle, growing to 500 people. And I was working with my advisor, Professor Carlos Kestrin, from Stanford, who is now in Stanford. He was our CEO. Before that, I was working at Carnegie Mellon on GraphLab project, which was a popular graph analytics. And in a minute, you'll understand why it's relevant. We have a third co-founder, which is Dr. Amir Alush. She's a very seasoned computer vision researcher in Israel. So that's the joint work of the three of us that I present. And I do apologize. I just got back from CVPR in Seattle, so I lost a little bit my voice. So hopefully it should be fine. So the problem we are tackling is a problem of very large visual datasets that are accumulating, and companies have no clue what to do with them. Basically, they are left unattended, and this is because on a massive scale, when you talk to billions of images and videos, it's super complicated, not enough skill sets are around, and not enough tooling exists, so that's where Visual Layer comes in. We started with the open source approach called FastDo. That's our popular project. 2 days ago or 3 days ago, we got to 400,000 users, which is cool. And what we do the boring things of visual data curation, which means getting, it's kind of ETL for visual data. You get a lot of images and videos. You want to figure out what's inside. So first step, you always want to remove duplicates, outliers, corruptions, wrong labels, and wrong metadata. So that's what we do in FastDo. And under the hood, we have a C++ engine. I'll talk a little bit about what's the main concept behind its work, but it's really old-fashioned due to performance, and we can scale to up to 1 billion images or video frames on a single multi-core machine without any GPU. So that's a nice property of our tool. We have a lot of users, some of them are paying customers, and a lot of also free users that use our open source. I want to share a little bit what are the typical kinds of issues we see on visual dataset, just to set the context. Why do we need our library? So the first thing, and this is all examples from ImageNet, it's a very popular dataset with 30,000 citations, and it's widely used in academia and also in research of companies. So the first annoying problem, we often got duplicates. So just duplicate images that don't contribute much to our knowledge, and we should just reduce them, and there is no additional information in them. Second type of issues that may happen with our images, sometimes images are too dark, and that's also may pose a problem to some model dealing with those side cases. If the model was not trained enough on dark images, the model may fail. Of course, the opposite, we often have also bright images, so that's often the case. And this is an example of blurry images that are also not too high quality, which we may want to filter those out, depends on the task. So besides of understanding the single characteristic types of data we got, we also have a notion of outliers. Outliers are images which are kind of different than the norm of the regular images. So I just pick from ImageNet images that we believe that they are outliers in some sense. Some of them are pretty weird, some of them I'm not sure exactly how to describe them, and some of them are just not common enough that are flagged as outliers. Now the next thing we'd like to understand when approaching a new data set is what's going on with the data distribution. So for here I picked a nice example. So of course dogs and cats are very popular item. Everyone takes photos of their dogs and cats. But here I'm asking interesting questions. How many instances of cats inside toilets we have in ImageNet? And surprisingly, there are a lot of such instances. And using our tooling, it's really easy to find them. I'll show in a second how. The next thing I said, okay, we have cats, so probably people like dogs. So I guess we also have potentially many dogs in our dataset, and indeed there are dogs in toilets, different types of positions in the dataset, which makes sense. But what if I would ask, are there any goats in the dataset inside toilets? So out of 1.3 million images, we were able to find a single goat that the image is taken inside the toilet. So this is a pretty rare event. So I would say the cats in toilets class is kind of, you could find hundreds of examples, but a goat inside a toilet, it's really a very, very corner case in terms of the outliers. This is another funny one that I found. I have no clue what it is, but it looks frightening. So I added it in the toilet category. So some weird people have this kind of toilets. And this is a bit of more artistic. People are doing some arts inside toilets, which is funny. And even they are drawing some pictures of toilets. So this is again another outliers. I wouldn't imagine someone named Sheila Hudson would bother a lot on taking photos of her toilet paper, but it's part of ImageNet. So that's a bit helps me to understand better my data set. Now, everything I showed is kind of properties of visual data sets. And what we're doing on top, we're building a platform which connects to all of those images I showed, and their metadata, their descriptions. We form a graph of relationship, and then we understand better what's inside the data, both for quality reasons, for ruling out corruptions, duplicates, and so on, but also for an analyst to be able to quickly find and filter interesting things on their data set. So this can run on-prem or in the cloud, and can run as an API or as an analyst user that is using the system, and I'll show you exactly how. So let me start with a quick local demo of our new latest and greatest Python package that we just released last week at CVPR. So I'll hop off the here, and I hope you can still hopefully see me. So what I have here, I have a Python console. What I'm doing, I'm calling Python, importing our package fastdup. The next thing I'm doing, I'm pointing to the location of bird images. That's a dataset that I have locally on my laptop. It's a popular Kaggle dataset of 90,000 images. And the next thing I do a run, which is basically drive the analytics out of this dataset. This one I will skip because I did it before the talk. It takes around 2 minutes for 90,000 images. And the next step, I would like to visualize. So what I do, not explore the dataset. So it opens a new window. So you can see we have this popular dataset. It runs on my laptop. It points to the localhost, and I start to see interesting clustering. That's not part of the dataset. It's part of our visual clustering. That we are doing the clustering and able to find similarity across different types of birds. And this relates to the graph engine we're building, which basically starting from a single image, I can look at another image and then start exploring around the other image, and then I can start continuing forever and understanding how my data looks like. So that's a powerful way of unsupervised exploration of the data using our graph technology. The next thing we also do automatic mislabel detection. So assuming there are labels, we can automatically point areas where we think there are mislabels, and mislabels are visual. So if a lot of this bird is most likely mislabeled as crested nuthatch, whatever it means, and the possible correction is titmouse. I don't know which bird it is, but that's more common in the data set in terms of the visuals. So we are pointing mislabels. One last interesting thing about this data set is the ability to flag outliers. So I'll go out of this context. And here we find a surprising find. So there are Trump images and all kinds of January 6th images hidden as an Easter egg in this data set. And of course, they are not birds. If we log into a specific image, we see this image is called loony birds. So someone had a political statement. I'm not American, so I don't really care. You should choose elect the one you believe in. But that's a bit of a funny because, as I mentioned, it's a popular Kaggle dataset with 65,000 downloads, and of course, no one has a clue what's inside. And as I show you, we can find in a few seconds what's unique about these datasets and what are the outliers there. So let me get back to the slides. And now I would like to do a demo that I also did in Seattle last week, which is a demo in the cloud, where in the cloud we have more advanced capabilities since we have more compute power in the cloud. So for the meetup last week, what I did, I just downloaded 70 TikTok videos, all with hashtag Seattle, and I did it very quickly, both because I'm lazy and also because I was at the Amsterdam airport. So I needed to do a quick demo. And this is the winning image, which is a representative in Seattle. But actually, when I started to prepare this data set randomly out of 485 video frames, this dude showed up. So I guess this is less appropriate for a Seattle demo. So we switched the title. So let me show you how our system looks in the cloud. And now I'm switching, instead of the local host, I'm switching to the cloud. And this is our Seattle demo. So what I have here, relative to the previous data set, I have here video input sources, where I just give a folder of video files, and then we do all the magic in order to reduce and select the interesting video frames. We selected out of 75 videos, 485 video frames, and then we do enrichment in order to, and here it's our enrichment, in order to have a better understanding, sorry, what's in the video. So you can see number one popular cluster is skyscrapers. We have some nightclubs. We have, I don't know, food, Ferris wheel, toy shops, and so on. And one of the things that caught my eyes pretty quickly is this weird video. So I really have no clue what it is. But then I asked my fellow Seattle friends, and I found there is a gross gum wall in Seattle where people come and stick gums into the wall after eating them, or maybe vice versa. Maybe they take gums and eat them, I'm not sure. But anyway, that's a bit gross. So as you can see, when I enter a specific video frame, we also have an understanding of the actual objects in the video frame. And we have, in this case, multiple objects that I can start exploring, and that's done part of our enrichment. So if I want to do it more methodically, I can jump to the object scenes, and then here I see all the objects from all the video frames, from all the TikTok videos in Seattle. And then I have, for example, a car is an object inside the video frame, and then I can press a button and start exploring the space of cars. So again, I'm traversing the graph, but in this case, I'm not traversing the direct video frame, I'm traversing something which is more complicated, which are objects inside video frames, but still same look and feel. And given a specific instance, I can start exploring, and assuming, let's say, I like this manga, I can start it as a query, and then start looking for other mangas and so on. So that's the way I traverse. Another thing which is cool in the cloud is the ability to do textual search. So I could do search a car, and then I get different types of cars. But if I'm very pedantic, I may want to bring in a red car. So I have here 2 red cars. Let's see what happened here. Oh, you see, there is a red car. Strangely, 3 was marked, but we have a red car, so we are good. So that's the ability to do complex textual queries, visual queries, and also exploring the graph structure, and also different types of slicing and dicing. So I could look at the label space and understand my data better. So I can look for a blanket, and strangely, this is labeled as blanket. Yeah, so that's the cloud demo. Let me come back to my slides. So I wanted to take a few last minutes in doing a little bit of explanation of what's inside behind our system. So our foundation is built on the work we did on Carnegie Mellon about GraphLab. That was a pretty successful paper. Recently, we won a Test of Time Award with VLDB, which is nice. I mean, it was too late for my academic career, which ended prematurely, going to a startup, but still, it's a nice recognition. And what we did in this work is the ability to explore and interact with billion nodes, graph, and edges already in 2009. So those was my collaborators here. And if we link it back into the visual domain, so basically this is a very, very naive representation showing our famous cats and toilets clusters. So what we have here, we have input images. What we do feature vector embedding of the input image into a short feature vector. Then we build a nearest neighbor model in order to understand relations between distances between images, and images that are has a close distance, which means they have a high similarity, which means they are more or less clustered around certain small regions of the graph. And once we have an object which is common in both those images, our expectation would be that the cats with toilets cluster would be somewhere in the middle between the toilet cluster and the cat cluster, and then we can do some kind of interactive exploration, which gives us very cool results and a much better understanding of our data sets. yeah, so that's what I wanted to share. Thanks for listening or viewing. And anyone who likes to check it out, would love to have you install. Just pip install Fastdoor. As I said, it's a free package, and this is my email. And anyone who wants to outreach, I would love to connect and explore to see if we can help with anything. And I would love to take questions in case there are any questions.
Okay, so this was we're about 12 minutes off from our next scheduled talk, but we'll see if there's any questions in the audience. I have a question for you while the audience kind of like puts together whether or not they have any questions. Could you talk a little bit about like the complexity of the pipeline that goes into taking the data from the raw data format into putting it into something that is able to be accessed and analyzed as you show in FastDo?
Yeah, sure. So that's a good question. So what we do, we typically, our API is super simple. So we assume you have a folder or a bucket with a mix of video and images. That's all we need. If you have metadata like image annotation, that's fine. We support also class labels and bounding boxes. So the first thing that we do once we connect to your bucket, and by the way, we can run on-prem, so it can run close to your data. It doesn't need to, data does not need to ship to us. And so once you connect, we connect to the bucket, what we do a scanning of the data. In case of video files, we do frame extraction. So we have our own way of doing efficient frame extraction. Again, this is done in C++, no GPU, so that's a very efficient step. And the next thing we do after the frame extraction, we do a deduplication step between the frames and the images. So you may have some screenshots of videos, you may have duplicate videos, you may have overlapping videos and so on. And so, sorry, that's we do to reduce the amount of redundancy in your data. The next thing we do also what we call an enrichment, which is the object level and the description understanding of the frames. And that allows us to do also textual queries, which could be combined of a few terms, like description, like a man with a red hat driving a white car, for example. That could be a query. And once we've done the enrichment phase, then we do the clustering in order to group similar objects together. Maybe I can show it really briefly, and then it will be much more clear. Yeah, here it is. So this is, for example, a cool YouTube dataset that we're using, 15,000 videos from YouTube. And I hope you can see my screen. So what we have here different types. After we do the enrichment, we cluster different types of activities. And then what you could do, you can investigate the different types of activities and jump to the specific video where this activity happened. So that's the clustering, which is done after the enrichment step. The final thing, besides of the exploration and visualization, we allow also what we call an extraction. And so that allows you to find interesting things on your data and create downstream data sets. So for example, assume I really like soccer or football, and then I can select a few clusters containing football videos. And then what I can do, I have this type of shopping cart. Oh, sorry, I forgot to move. Let me re-add. Sorry. So I have selected a few clusters. And then I have this shopping cart. And here, what I could do, I can assign a new class, basically. So what I could do, I can press the plus sign, say this is a new soccer, create a new class. The tags were created, and next I could go back to this annotation, look at the user tags into the new soccer class, and then I can pull up whatever information I wanted, and I can also extract it to create high-quality datasets for training. So that's basically the functionality. It's pretty efficient. Largest customer, our latest deployment has 100,000 hours of video. So I guess that positions us on the really large scale side of solutions.
Cool. Thanks for that. One other, I guess, Megan, did you want to ask any questions?
Oh, no. Go ahead, Nijin.
Okay. One other question I wanted to ask before we move on is also like, how do you handle this kind of scaling? Like, what are you doing in the background that makes it possible to scale to these hundreds of thousands of hours of video? Is there any what is the secret sauce behind this? Are you able to tell us what this is?
Yeah, it's an interesting one. So under the hood, we deliberately devised the code in C++. It's a lost art for the elder, I would say, and it also gives us some advantage that we can provide a compiled binary. So it's very small binary. It works very smoothly in Python, but we don't disclose everything in front, basically, because we do want to be a company that eventually charges for something. Although the open source is free, also the cloud version you can sign up for free. So what happens? We do very efficient feature vector extraction. After the video extraction, it's also done in C side. We do a very efficient feature vector extraction. We devise a network that's very lightweight. It's just 2 milliseconds per core. So it doesn't make sense to use GPU because you don't want to copy the images to the GPU and back. It will take more than 2 milliseconds. So that's very efficient. Feature vector representation is pretty short. We can keep it in memory, and that's how we can scale on a relatively beefy machine, but we can scale to 1 billion images on a single machine. And that's just one machine. So we built the nearest neighbor model. We have our own implementation of the graph on the C side. And that's our claim to fame. So we are graph people. So basically the trick is to, instead of working with 1 million pixels per image, we boil down the image into a single graph node, basically. So that becomes very efficient in terms of representation. We don't work with the raw image to show you the cool analytics. We do traverse the graph. It's very condensed representation, so the graph is pretty small. And once we want to scale into more, we can start opening shrouds in order to have subsets of the data. So let's say for, I would say 100,000 hours of video, probably it will be some like 10 shards that will contain 10,000 hours of video. And then so it's a bit of a hierarchy there, and then you can explore them one by one.
Okay, and you guys are using your own embedding models? You guys have your own embedding
Yeah,
models?
we developed our own embedding model. Anyone trying to reverse engineer will see it's called undisclosed fast-hook model. There are a few, let's say, GAM companies that try to reverse engineer, but deliberately we didn't want to share it. So basically, you can use it for free. So if you just want to do embedding, fast-hook supports that, and you do it for free. But we don't give the right network architecture. It's just very lightweight network architecture, but we also support others. So if you have a better network for your own needs, we support out-of-the-box EfficientNet, ResNet, Dino, V2, and many others. But if you have yours, it's pluggable. So we did observe some customers that had very specific needs. So for example, customer growing mosquitoes had mosquitoes with white dot on the tail. And then they would kind of complain, how didn't you find the white dot on the tail? And our embedding model was not designed for such minute detail. But they have their own embedding, which is really, really distinctive across sub-mosquito types. And it's always like that. Like for each type of data set, you have different type of requirements. So we have something that generally works really well for a variety of data sets, but it may be that your embedding could be better for some cases.
Okay, cool. That's really interesting. I don't know if there's any other questions from the audience. I don't see any this time. I think we can move on to our next talk.
Very good. Thanks for the invitation.
Thank you, Danny.
Nice day. Bye-bye.
See ya. Thanks for coming.
All right, Eugene, go ahead.
All right. Thank you. So for our next talk, we're going to get something really exciting. And I think we already all know NVIDIA and how the generative AI wave has really accelerated NVIDIA's rise to become the most valuable company in the world. And so it's just really exciting to see that they're still doing a ton of work and giving back to the open source and developer ecosystems. And today we're going to get to hear from Jay Raj about exactly how NVIDIA is doing that work. So Jay, the stage is yours.
Thank you, Eugene, and thanks for the opportunity. Hi, everyone. Good morning, good afternoon, wherever you're in the world. I'm Jay. I am a developer advocate at NVIDIA, focusing on large language model. And I'm really excited to talk to you about what are the LLM workflows that NVIDIA GPUs can accelerate. And if you already are working on an LLM pipeline, there's tons of stuff that you can use to accelerate it on GPU. So let's get started. So we all know, like, generative AI has been transforming everything that we are doing. It can basically learn and understand any kind of data. And that is also affecting how developers are creating application, introducing a new wave of tools and application and use cases that we never thought could happen. For example, think about chatbots from 5 years back, in the past. The way we used to do chatbots was using BERT or any other transformer, basically understanding what's the intent of the query by using named entity recognition and then doing all kinds of tasks after that. But with LLMs, it has significantly simplified how you can design a workflow for any kind of use case. And at NVIDIA, we are committed to providing a comprehensive platform that helps a developer get the best user experience by making it faster and cheaper. So let's look how NVIDIA has, what options does NVIDIA have? So we provide a full stack accelerating computing platform, which is purpose built for LLM workloads. And this includes a combination of hardware, specifically GPUs, which NVIDIA is well known for, but also software and services designed to help you develop, train, and deploy AI models efficiently. And we constantly work with the open source ecosystem to add support and integrate all the NVIDIA software optimization into those frameworks so that the end developer doesn't have to care about the low level layer that might be for expert developers. So today I'll dive in deeper about what are the layers about which developers can participate or just use. So let's start with the system optimization. So we provide cutting edge hardware such as GPUs, but also we recently introduced Grace CPUs as well. And there's also networking, which we have as InfiniBand, and then DPUs, which is specifically designed to handle AI workloads efficiently. And then to manage and orchestrate these workloads, we also are integrated within Kubernetes and Slurm, which take care of managing and orchestrating these workloads. From NVIDIA side, we also provide base command platform or BCP, which seamlessly offers a streamlined experience for managing AI tasks. And when we go to the library layer, we provide optimization libraries like CUDA, TensorRT LLM, and Transformer Engine, which play a really crucial role in optimizing whatever kind of model you're trying to run, maximizing the performance and scalability. and we keep adding new libraries such as XLA and Ray to get the best performance. Moving up on the model architecture and technique side, we also are integrated within PyTorch and Hugging Face transformers that facilitate the development and deployment of LLMs. And we also enhance these capabilities with our own NEMO framework, which I'll talk in depth about in the later stages. But it offers comprehensive tools for model training, customization, evaluation, and safety. And in terms of model, like ecosystem is really good nowadays. Like there's new foundation model being released or a new update being released every other day or every week, such as Llama 3, Mistral, and they provide range of capabilities for various kind of use cases, and all of them are optimized for NVIDIA GPUs. And we also have some specific models like NEMO models within NEMO umbrella and BioMegatron, which are tailored for specialized domains, ensuring that you have access to the model optimized for your specialized use cases. And at the top layer, which is application, developers can make use of libraries like LangChain, Llama Index to simplify the integration and the management of LLMs within application. And we also have great partners like OpenAI, AWS, Google, and Microsoft who have their managed APIs, which are also using NVIDIA GPUs behind the backend. So this was the overview about the full stack software ecosystem. So developers are free to choose at whatever layer they want to interact. If you are an expert developer, if you care about the maximum performance optimization on NVIDIA GPUs, you can use XLA, CUDA, or TensorRT LLM. But if you just want to make sure that your pipeline works and it's easy to use, then you can interact with LangChain, Llama Index, which also have integration for lower level libraries. So let's switch gears and see, like, if you are building LLM application today, how NVIDIA tools can help you on the training and the inference aspect. And today I will talk about NEMO framework for training and customizing your model, and the inference software that we have, which is TensorRT LLM and NVIDIA Inference Microservices. So NEMO is our framework for building, customizing, and deploying LLM large language model application. And it includes all the bits and pieces that you might require to build your own LLM and deploy that as well. Starting with data processing, we have NEMO Curator, which simplifies the entire data processing workflow, which consists of data extraction, deduplication, and filtering, which ensures high quality data for training. And we also have Customizer, which includes variety of fine-tuning techniques, which I'll talk about later in this slide. Then there's also Retriever, which helps you create a GPU-accelerated RAG pipeline, and guardrails as well to limit and evaluate your responses before delivering it to the end user. And once you are done with model building and adding guardrails, you can deploy that with NIMs or integrate that with NVIDIA Triton, which is an inference serving solution for accurate, low latency, and high throughput inference. So let's talk about the customization part. So if you have a specific use case which the generalized model doesn't help you get specific answer, then you can choose to do some form of customization, and NEMO supports customization in all formats, starting from prompt engineering, where you can use few shot learning and system prompting, which achieves quick result with minimal data and investment, all the way up to SFP, or the popular method currently is parameter efficient fine tuning, or PEF, where you can use tools like adapters and LoRa to target specialized training for peak performance with moderate investment. So depending on your use case, you can choose the right customization path and get the best accuracy for your use case. Once you have customized the model, next step becomes adding guardrails to keep the solution to keep the solution that LLM generates accurate, appropriate, and on topic and secure. And Nemo Guardrails is open source and is accessible to all developers. It's also easy to implement and integrates with all enterprise tools like LangChain, ensuring a powerful yet safe environment for LLMs. So Nemo is also good in terms of ecosystem. We have ton of integration with all the popular libraries or tools that you are using today. And it can be all on GPU. So that's great, which makes sure that you have the least possible latency for your application, which ensures a good user experience. So once the model is trained and you have all the guardrails in place, then it is time to deploy. And deployment has its own challenges because there's new model being released every other day. And it can be sometimes hard to optimize or integrate those new models into your existing pipeline, because those models might have new architecture or they might continue to evolve. So we need a robust, extensible solution for LLM deployments. And the answer to that is TensorRT LLM. It is our open source library that optimizes large language model performance for production deployment. And as an FYI, this is an extension to the deep learning inference SDK called TensorRT, which has been there for, I think, almost 6 to 7 years now. And it is already good at optimizing NLP vision-based model, but this specific extension works on the large language models performance, which provides additional features like state-of-the-art performance by using TensorRT compilation and optimized kernel for your target GPU. And if you have a custom model, you can use the Python API from TensorRT LLM to quickly add new operators that can get accelerated on NVIDIA GPUs. And if you want to have various batching requirements, you can use it with Triton that maximizes the throughput and GPU utilization. So let's look how TensorRT LLM works. So it's mainly three-step process where you load the model. Once you have the model, you create or generate an engine. So the engine building process is basically TensorRT looks at the model graph and tries to see what layers of the model can be fused together so that it can be run faster on NVIDIA GPUs. It also tries to look at what kind of hardware you have. So it tries to see what specific GPU feature it can use. For example, Hopper architecture has FP8 precision. So TensorRT can immediately recognize and try to optimize based on that precision and hardware feature. And once you have the engine file generated, you can then execute that with TensorRT runtime or just load that into Triton Inference Server, which gives you ability to deploy in Python or C++ API. So this is an example of how you would do that in terms of code. So on the right-hand side, first you will install and build TensorRT LLM. And then you download these model checkpoints from model hub of your choice. In this case, it is Hugging Face. And once it is done, you can generate the engine using TRT-LLM -build. And once you have .engine file generated, you can use that with TensorRT runtime or Triton to inference. So in this case, it is using a sample script run.py from the TRT LLM GitHub repository to do one inference. So this was the process to do TensorRT LLM inference optimization. But if you are looking something easier, we recently introduced NVIDIA Inference Microservices, or NIMS in short. We announced this earlier this year at GTC, and this also got a mention in a recent Jensen's keynote at Computex. Computex. So this provides a containerized solution for deploying optimized LLMs with just a single command, which significantly reduces time and engineering resources required for model optimization and deployment. So let's see how it works. So think of NIM as a delivery package optimized for your specific hardware, which makes the model deployment fast and efficient. So it handles your hardware configuration, allowing you to choose and deploy the model you want. And each NIM container is tailored to specific LLM, featuring a base container image and a lightweight model configuration layer, which ensures quick deployment and the best performance on NVIDIA GPUs. So going in depth, so a NIM container features an OpenAI compatible API layer with fast API, which enables seamless integration with your existing code. And the requests are efficiently processed by optimal runtime, which could be either TensorRT LLM or VLLM in the backend. And it can be served back in batch or streaming mode. So the performance using NIM is quite significant. So if you just use Llama 370B instruct model on NVIDIA GPU with NIM on, you can get up to 5x performance boost if you use the same model on NIMs without doing anything, just a single command, which significantly improves the performance, but also lowers the TCO. So to summarize, NVIDIA NIM significantly reduces the time and effort by providing pre-built optimized engine for both NVIDIA and community model. And it also automates the deployment, and we also provide enterprise-grade support if required, which makes it the fastest and most efficient path to AI inference for developers and organizations. So this was training and inference, but there have been so many applications, but RAG has been at the top in terms of real world use cases for large language models because its ability to connect LLMs to up-to-date information and knowledge bases. So NVIDIA also provides an optimized RAG pipeline that includes accelerated embedding, de-ranking, and personalization components. And it integrates seamlessly with popular frameworks like LangChain, Llama Index, as well as popular open source vector databases like Milvus and Redis. So this integration allows developers to build highly accurate and performant RAG application with minimal effort. So yeah, that was for on the training and inference side. We have a ton of tutorials on this. So these are some getting started guide. I would recommend go to the GitHub repository for each of them to get up and running. There's also a dedicated repository called NVIDIA Generative AI Examples, where you can see pre-built POCs or sample reference application built using NVIDIA and open source integration. And it also includes NIM as well, NIM deployment. And we also have Deep Learning Institute or DLI, which can help you get started and ramp up quickly on some of the foundational topics on large language models and generative AI. And you will also get a certification if it is necessary for you. So to summarize, NVIDIA provides a full stack solution for LLM deployment from hardware to application frameworks. It's up to you, whatever you want to choose from the whole layer. Like we are integrated in most of the popular open source frameworks. And on the training and inference side, we have tools like NeMo, TensorRT LLM, and NIMS, which enable developers to build, optimize, and deploy state-of-the-art large language model application efficiently. And we also have ton of ecosystem integration, and we are committed to supporting the developer community with integration for popular libraries and framework as they get launched or used. So that was it from my side. I'm open for questions now.
Thanks, Jay. I have some questions for you. We'll see if the audience has any questions as well.
Sure.
What are you most excited about in this whole like development of LLMs and how it relates to what you've been doing at NVIDIA?
That's a good question. I think we are still at a stage that we haven't. I'm not talking from NVIDIA's perspective, but as a fan of generative AI in general, I feel like we still haven't found out that killer use case. Like we have ChatGPT, we have chatbots, but I think we are still figuring out on how to integrate those tools in our daily life. Being as a software engineer, being as a product manager, like yes, we are using ChatGPT, but I think there will be a time where it will be seamlessly integrated within our workflow that it would be so hard to imagine our life without those. For example, I think Data Copilot could be one of the good use cases. But yeah, I'm excited for what's upcoming.
Very cool. And then like in your time at NVIDIA, so you've been at NVIDIA for a little over 4 years now, right?
Correct. Yeah, that's correct.
Yes. Okay. Yeah, I saw your post on LinkedIn. So what have you been seeing over the maybe like the last like year or two that has been like kind of different? Have you seen anything that's been happening internally that's been different because of the whole generative AI stuff, or I don't even know if you're allowed to tell us about this stuff. What have you been kind of like seeing internally? Is there anything exciting that we should be on the lookout for?
Yeah. So I think in last 1 year, we have been impressed about the community models and how good they are getting. Like every I think every week or every 2 weeks, there's a new model which beats the benchmark of the other model. So it's really good to see, and we are actively work with those partners and model providers to optimize those on NVIDIA GPUs. So I think there's two trends that model sizes are getting smaller and smaller, which also makes it easier for developers to have locally running applications. For example, I think Apple Intelligence, we have optimized the model so good that it can run on our local devices. So RTX AI laptops, we provide features like background blur and reducing noise from your video as well as audio. So it is all happening locally, so you don't have to rely on crappy AI tools from other providers or the tools that you are using. So yeah, so excited about that.
Very cool. What do you think about? Have you had the chance to try out like new like many of the open source models on the NVIDIA GPUs?
So I would like to share my experience with Olama. So Olama is one of the model hub slash. It helps you basically run models locally on your GPUs or CPUs. But I think I try to integrate that with my VS Code using continue.dev extension. So it has been working really well. I can also have my local chat GPT kind of application all running locally thanks to Olama, and the models are optimized. So I think, yeah, I'm excited about that aspect, that having everything local is great because I don't have to worry about sending my data to some cloud server. So yeah, everything happening locally, I think that would be a great step forward. And I think we are trending towards that future, and it would be here, yeah, sometime soon.
So I think one of the things about LLMs and generative AI that makes it difficult for a lot of people, and so I talked about this earlier, is like this ability to access GPUs and how not everybody is able to get access to GPUs because I mean, there's just a limited quantity, right? So, and you were talking about how one of the trends that you're seeing is that some of these models are getting smaller over time. And so one of the things that I would like to ask you about is, how do you see how do you see this in terms of like what you guys are doing, and maybe like the role of what NVIDIA used to build, which I guess you guys still technically build, but like things like the RTX, GTX, like what if you're a gamer, like if you used to play video games, I built my own PC. I used to like to play like video games on my PC, and so I would use these, I guess they call them consumer GPUs now. How do you see like the role of like these different GPUs play out as we move towards different models? Like, do you think there's still going to be room for like these larger models that are going to be doing a lot of stuff as well as smaller models? Like, how do you kind of see this play out?
That's a good question. And I think from my point of view, so all the great GPUs, data center GPUs we have, Hopper and Ampere, and the new one is Blackwell is upcoming. So all the features are being transferred to the consumer level GPUs like GeForce, for example, FP8 precision or the transformer engine. So developers can still use those or get the benefit of those features on GeForce GPUs like 4080, 4090. So you get to use those features, build AI application, as well as you also get to play games which has generative AI inside it. So for example, DLSS, deep learning super sampling technique, which is part of the gaming toolkit that NVIDIA provides to all the developers. You can use that to like use generative AI to improve the frame rate of your game. So it basically generates. So if you have a demanding title, then it might just give you 25 to 30 frames per second without using DLSS. But if you use DLSS at runtime, it will generate the frame in between and make you or boost the frame rate to maybe 60 or 90. So that's also a form of generative AI. So you get to game with a high quality image as well as experience, but you also get to use generative AI in your for productivity tools like not ChatGPT, but VS Code. So I think it's beneficial for those kind of developers who are also gamers. So yeah.
Oh, that's really cool. I this is like my first time hearing about that. I didn't know that you guys were doing work around that as well. And does this work like with like online games or like offline games?
So it's I'm not so sure. So we do have cloud gaming service that NVIDIA offers. I think it might be using DLSS, but for offline or local gaming, it is for sure like you can use it. There's a setting in your game called DLSS off or on, so you can just turn it on. And I think most of the popular games support DLSS, and we keep adding them with time. So
okay, wow, that's really cool. This is like, I love that we're always like get to learn about something new from this. So I don't think the audience has any more questions. I think we can move on to the next talk, unless there's anything else you want to say in the next couple minutes, Jay.
No, I'm really excited about this conference. Thanks to you for organizing this, and also excited what developers feel about NVIDIA software and what's their experience. So do feel free to share with me on LinkedIn or any other platform. We are also on Discord if that's your preference. But yeah, I'm always all ears.
Okay, cool, awesome. Thank you for coming, Jay. I'm going to bring my co-host up to the stage to introduce our next speaker. Megan, you're on mute still.
You got me. Thank you so much, Jay. So our next talk is from Arise. And one of the hardest things about LLM applications is evaluating them appropriately. Aparna, who will be speaking from Arise, and the rest of the Arise team have been working on building LLM evaluations that really work in real-world scenarios. And Aparna, I will bring her up to the stage so that she can talk about how they are doing that. Okay, I think Aparna, you're up on stage, but you're muted.
Hey, can you guys hear me?
Yes.
Awesome. Awesome. Well, hey, everyone. So excited to be here. Well, let me jump in and let's get started on our talk today. Let me go ahead and share my screen. Okay. Can you guys give me a thumbs up if you can see my screen
We can see
right
it.
now? Awesome. Okay. I can't see what I'm sharing, so keep me honest if something freezes up here. So awesome. So today's talk, what we're going to be talking about is building LLM evals that work in the real world. You guys have probably seen this. This is from Greg Brockman from OpenAI, but truly do believe in this. Evals are often all you need, and there's a lot of ambiguity around what are evals, what should I be using, and we've been dropping a lot of research about different approaches. And so I'm going to be giving you guys an overview of kind of the research we've been sharing, as well as best practices around how to use the evals. So first off, I think the word evals is overloaded when there's really two types of evals that we're hearing in the market. There's model evals versus task evals. Model evals are the ones that, if you go to Hugging Face and you look at the OpenLLM leaderboard, or Berkeley Function Calling, the Gorilla team has done one that's around specifically function calling. But they really rank up different foundational model providers and help you decide which model to choose. And all of these use metrics like MMLU or the hella swag, but these are types of metrics that are focused around what model do I actually choose for building my application, and which models might be better at things like RAG or retrieval with generation. And so there's model evals and there's also task evals. If you're an AI engineer, the one you probably care about, if I'm honest, is probably the task evals. You might use the model evals just to help you figure out what model to use, but day in, day out, the one you're going to care about is probably more of the task evals. This is really the ones that are helping you answer, is my application working? So there's metrics like correctness, hallucination, product specific metrics that you might care about way more. As a day in, day out, how do I improve my application? But both are important to different folks. These are slightly more important to folks who are building foundational models or even fine tuning them. These are slightly more important for kind of the folks really building the AI applications. And there's a lot out there on the model eval side to help you pick the right model to use. One of the most popular ones that blew up a couple months ago was really the needle in the haystack approach, which was basically a test on how well different foundational models were at retrieval. So something like this, where I had a long piece of context and I would put a piece, a fact hidden somewhere in the long piece of context. And the goal was for the foundational model to be able to retrieve that piece of context. And the hard thing here was that you could increase the size of the context window. So we had some that were tested when they were really, really small context windows. A lot of the foundational models did well. As you increased it, obviously it got significantly worse. And then it was also placement within the context window. So in this case, it's kind of earlier in the document. And then here in this case, it's kind of 90% of the way down, further into the document. And the goal here was, did placement within the context window actually make it harder for some of the foundational models to retrieve the data? So here, basically, the x-axis is the context length. So how big was the document? And then the y-axis here is actually the placement within the document. And we were testing basically how good was a number of different foundational models. So this was actually Claude 2.1, not the latest one. This is not Opus, but the Claude's 2.1, compared it against GPT-4. And you can see here, this was kind of the previous model, but specifically as you increase the context length and then the kind of further and further down, it went inside of the actual document itself. It had a really hard time retrieving that fact. Green is where it got it, red is where it actually didn't get it, versus GPT-4 did generally good, even as you increase the context length. But there was this kind of consistent, even as we ran multiple tests, consistently at the front of the higher window during higher context lengths where it was challenged. So what it meant was if you put the context or the facts earlier in the context, it almost forgot it before it forgot it and didn't do a great job of using that fact in the actual retrieval. And so these are really helpful just as you're building out your RAG systems to understand, okay, well, which one should I use if I'm trying to have a long context window or a short context window? Where am I placing it in the document? These are helpful ways for you to understand, well, what type of foundational model should I be using? We did another one, which is focused around retrieval, but this time also generation. So after you retrieve the fact, could you do things like generation on top of it? Could you round the numbers? Could you concat them? Simple date mappings or modulo numbers. And we tested this again on a couple different models, GPT-4 Turbo versus Anthropic Claude. This was one actually in the beginning. Claude did significantly better, almost 4 times better than GPT-4 did. And GPT-4, even though it did the right retrieval, it missed the generation part of it versus Claude, despite all the issues on, we were seeing with 2.1 on the retrieval, actually did a fairly decent job at the generation. And actually, after we modified the prompt a bit, we were actually able to improve and fix GPT-4 Turbo's performance almost significantly. And the key thing we just added was just a line that said, please explain yourself and then answer the question. And the reason this is really important is because I don't know if you guys have all felt it or seen it, but the Anthropic Claude models are slightly wordier. We see that in market, slightly wordier than the GPT-4. But in this case, it might actually be a feature, not a bug type of scenario because it was wordier, it was actually checking itself along the way, which got it to do much better than GPT-4's original response. And we had to explicitly ask GPT-4 to do this in order to get a better response. And so if you're using GPT-4 for retrieval with generation, adding these types of things inside of your prompt will actually help you improve the response that you're actually trying to gather. These are just a little snippets of some of the model evals that we've been releasing. Again, probably more important as you're actually picking the model, if you're an AI engineer, helping you decide which ones to worry about. But the key things that we see more people care about is more of the task evals. On the task eval sides, there's predominantly kind of 3 approaches the industry has landed on, which is LLM as a judge. So these are where you're actually using an LLM to, using AI to evaluate AI. There's a number of common metrics we'll go through. There's user feedback. This is things like thumbs up, thumbs down, good, bad, but actually having a human in the loop. And then there's very heuristic code-based approaches that are also really great for things that you need a very, very programmatic approach to be able to do. For those of you who are not familiar with LLM as a judge, I'll just do a quick overview of it. But LLM as a judge is basically you're passing in at your application prompt. This is actually the prompt into the application. You generate a response from it. And then you use basically all of the information that was sent into the prompt or the response, depends on your template. But in this case, for my hallucination template, I'm actually using kind of, is the response that was generated based off of the context that was actually used to answer the question. And so in this case, this was all actually used, passed in as the LLM as judge to evaluate the response. And it kind of came back with, no or yes, it did hallucinate. Really, to use these methods, you want to do benchmarking on the eval templates beforehand. So you want to make sure that the LLM has a pretty decent precision on what you're actually trying to evaluate, and then continuously validating these validators. By the way, great paper by Shreya Shankar. But it's a really important thing to make sure you validate the validators that you're using. Common thing that we recommend and we see people in the ecosystem doing is actually using these evals with explanations. So what we mean by that is not just getting a single label correct, incorrect, hallucinated, not hallucinated, but actually using explanations to surface up if it was incorrect. Why was it incorrect? In this case, it actually tells you, well, it's incorrect because it does not answer the question based on the reference text. And so it actually gives you a next step to go do around, all right, well, what was the reference text that was actually used? Why did it make up information or not use that information? And so they actually give you kind of nuggets on why it made that label, and then how to go fix it in reality. There's a lot of different types of evals out there, some which are focused around, there's different categories of eval types that we see in the market used for task evals. Some are numerical based, categorical, multi-output, just means you're using the eval to run multiple evals at the same time. So things like, is the summary correct? Is the summary concise? Is the tone consistent? Is the tone positive and not negative? So these are all things that where you can have multiple labels coming out of those evals. And there's also, of course, multi-class labels. So give me multiple different categories as outputs. What we're seeing in the ecosystem is actually that we really actually recommend folks not use numerical scores as the only form of eval that you should use for your application. And we'll show you kind of what we've done some research on and some examples. This is a simple application that, is just supposed to judge how good is, how many spelling errors are in a document. So in this case, it's supposed to give you a score between 1 to 10. Tell me how bad the spelling errors are in the document. And we actually corrupted this document with kind of 80% of the document had spelling errors. We also similarly did another document that only had about 11% corruption. So very less compared to this one. For both of these, the eval score, the LLM as a judge gave, was 10. And what made it really difficult was that there's really no sense of granularity between these two different documents. Both of them, when you're doing a numerical score, you get this kind of sense of, okay, there's a gradual as it's worse, the score is higher, as it's less, the score is lower. But we actually didn't see that. And this is it was pretty consistent across a lot of foundational models, where even as we increase the density of the corruptions, we actually saw a pretty binary type of response. It was either a 1 or it was either a 10. But what we really wanted was more of this like gradual, perfect linear range. And that would have signaled more that, okay, LLM as a judge can be used for numerical scores, and it understands the gravity increases as the score increases, but it almost suggests that the scores itself were coming back binary. It was really suggesting for us using it, you should kind of use it more as categorical binary labels instead of numerical ones. I think we have a good 10 minutes here. So what I'm going to actually do, hopefully that was helpful. This is all kind of cool research you've been sharing on Twitter about what we're seeing in the ecosystem. I'm going to jump actually into what we're seeing with customers and what we're seeing in the real world as people are building these task evals. There's really a workflow here that we're seeing across the life cycle of building these evals. There's a phase when you're actually benchmarking the evals. So this is as you're building your eval templates, you're building the golden data sets, you're using them to actually understand how much should I trust this LLM as a judge template? And not all templates are going to be right for your use case. So there's definitely a benchmarking on your own golden data set for your own domain specific application that needs to be done. Once you're actually done benchmarking that eval template, as you're actually iterating and developing your application, we see folks using those evals in development as well as in production. And that line can get really blurry. They start to iterate on the prompt. They start to iterate on their, swap out the model, swap out what you're doing for the retriever. And every time they make modifications, they want to rerun those evals to make sure that that experiment did better or worse than prior. And then they want to use those same evals when the model or the application is actually deployed into production to be able to run that in a production application and monitor the performance of the number of hallucinations that's happening in production. So these evals are actually, you want to use the same templates and often for folks the same frameworks to be able to run offline, but then also run them online in production. And this can be for really simple applications, but applications can also get really, really complex. This is, I almost call this a little, the agentic or pre-agentic type of workflows where folks are actually using routers to determine what is my user intent, and then all sorts of different paths that the user can go down. So everything from product comparisons, product search, if you're doing something like an e-commerce bot. And so these applications can get more and more complex with LLM, internal API calls, code, and being able to evaluate these type of router-based applications require really levels to these evals, is what we're seeing in real data in the real world. And so what I might actually do is jump in and show you guys a demo of how this actually looks in a real system. So let me actually show you guys Phoenix and demo and show you guys how we think about evaluations. So, oops, let me go back home and pull it up. Give me 1 second here to pull it up. Can you guys all still hear me and see my screen?
We can hear you, yes, but we cannot see your screen.
Okay, awesome. Give me 1 second just to pull it up, and then I'll go ahead and share my screen again. 1 second here. Okay. This might take a second to load, so let me give it a second to load, and if it doesn't, then we'll just rerun it so that we can, oh, perfect, okay. It is running. Okay, awesome. Let me go ahead and share my screen here. Okay. All right, sounds like I'm sharing again. Okay, so basically this is the e-commerce bot that I was kind of showing beforehand in this view over here. This is actually a really common type of use case we're seeing folks build. What the use case is basically someone as a user comes in, they might be, asking a question, and the question should route to a couple different paths. Help me compare products, help me search products, help me maybe route me to customer support. And so under the hood, what's actually happening, this is, let me show you an example. Users come in and ask, hey, is there some way to apply a discount code to my recent purchase? And what it does, oh, I think I really need to rerun this application here. Give me a second. Maybe while that's loading up, let me just show you guys in the application here. Behind the scenes, what's actually happening is a function call. So there's a router that is actually routing to which execution branch to really go through. And what you want it to do is basically, from a router perspective, route to the right execution branch. You don't want, when the user is asking or if there's a product support question, have it go and recommend products to you. And so there's levels to this evals where at first you want the router eval to actually work and get what the user intent is. And then post that, you want it to actually go down the right execution branch and make sure that it actually answered the user's question in that execution branch. And then each execution branch itself might have multiple different components. So if you're doing something like a product comparison workflow, you want to make sure that every single component where it queries what products from maybe the vector store or from the catalogs, it actually queries that, gets that information correctly before it shows it to the user. And so this is a really common type of, call it application, that we're seeing in the ecosystem, where it's called router-based architectures. And for these router-based architectures, basically there's typically a function call. And the function call is what, first determining based off of what the user asked, what should I even call? In this case, this is a asking for specifications on the product. And so it should call a product details function call. This one's asking for differences between two products, and so it actually should be a function call around, a product comparison. So it got the function call wrong. In this case, it's actually asking about recommendations. So you want it to, again, go back and do a product search. And so there's first the level, which is just, did it call the right function? And the next level of this is, if it calls the right function, did it actually get the parameters for that function correct? So if you're doing things like, in this case, you're asking for a specific product, you get the product ID, that's the right parameter. In this case, there's actually two parameters. And one of them is the actual query, and then what category of products are you asking it to search? And I'm not sure if laptop probably fits into office supplies. Maybe they expected it to be more in electronics. And so this is one where it actually got the parameter for the function call wrong. And so you might want actually multiple levels of evals on what function did it first call, and then did it actually extract the right parameters for that function eval in the right way. And each one of these, you can actually do LLM as a judge. You can track things like the precision and the recall of these different types of applications. And we're seeing this as a very common framework that folks are doing to actually route some more complex applications like this to the right experience for the user in the real world. Another common type of experience here is if you have multiple back and forths with the user. So something like a session, you also have the session with, the user talks to the bot, and then the user comes back and asks follow-up questions. Then you can actually do things like, across multiple messages, was the tone consistent? And then within each individual message, did it actually answer the question that the user had just asked? And then, of course, within this individual kind of back and forth messaging, there's also a lot of sub-steps or spans that could have happened. So to answer maybe even in a single question, there's a retrieval step that needed to have happened to answer that. And so there's just levels to these evals. And I think when we often talk about evals as a high-level concept, we think it's maybe just one at the end of an application. But in the real world, these applications are often really complex, can be really, really multi-step. And so it's really important for the owners of those applications and the builders to know what's important to evaluate and what's important to actually track when there's failures in the application. I'm going to go ahead and see if I can get the thing pulled up one more time so I can show you guys. Let's see, live demos. Okay, awesome. I think I have a good example here to show you guys. Okay, let me go ahead and pull this up. Okay, awesome. So for those of you who aren't familiar actually with us, this is Arise Phoenix. You can go check it out if you just go to docs.arise.com with Phoenix. It's completely open source evaluation and observability framework. You can use it for things like first off, tracing your application, so actually seeing what's happening under the hood, but then also, of course, applying things like evaluations to every single step of your application. So in this example here, this is kind of the one I was sharing of where the user asked a question. So the user asked something like, I ordered a device. I'm not sure if it was this. Can you help me track it? And in this case, what it does is there's actually a function call. So the function call is actually deciding what specific call to make. And so if I go over and I can see in this case, it did a product comparison function call. The ones it has access to is product comparison, there's product search, it has access to customer support, of course, track package. And so these are all the ones that it actually has access to, and it can decide across those different, so similar to what we're showing over here, all of these different execution branches that it can actually go under, and then deciding which one should it actually use to go down the path of. And what you can do is apply evals to see where did it get it right and where did it not get it right. So I'm gonna actually go into one where there's an incorrect function call, and we can all take a look at that. So in this case, someone's asked a question, is there any current promotions for the Samsung smartphone? Let's go into the evaluations, and it looks like it said it made an incorrect function call. It actually made a product search function call here, but the user was specifically asking about promotions. So if I look here, it gives me kind of the function calls incorrect. The user's questions asking about promotions, but the generated function call is for product search, which may not specifically address promotions. A more appropriate function might be the one that directly queries promotions or discounts. And so having the traces first helps you see in these slightly more complex router-based applications, or if you're using agents, essentially, did it go down the right path even? And then if it didn't go down the right path, where did it mess up? And we have teams that then look into, well, should I be adding more things to user, either the descriptions of the functions or adding data, adding into the prompt templates to make sure that it routes to the right function call. But if it doesn't get this step correct, it's not going to get the rest of the flow correct. And so definitely making sure as best as you can that you have things like function calling evals, having the ability to go do the right parameter extraction is really important to give it all of the data it needs to be able to choose the right path. One last thing I'll just showcase here, and we can see if this gives you guys a little bit of view into it. But when you do have basically, and again, this is Phoenix, you can kind of use it to trace your application, run your evals, apply it onto it. But what you can do is actually add these types of bad or incorrect examples into data sets. So if I wanted to, I can actually add it to things like data sets that I can then go use to iterate and improve on my application. So in this case, I've actually already created a couple different data sets, but I can go in and just add this if I wanted to an existing data set. And what these data sets essentially allow me to do is then run experiments. So I can run experiments where I'm doing things like iterating on the prompt template on those bad examples, or iterating on the function calls, however you want to make those changes. And then you can compare side by side against what was the generated output versus what was the actual reference output. And these end up being great because, like we were going back to talking about it, evals are not just used in production. They're definitely helpful as you're developing. And so having these evals to iterate on your experiments and improve the application, ultimately make it better. I think I'm getting close on time, so I'm gonna actually stop share here. Hopefully that was, a lot of information that it's helpful for folks out there who are building and are actually trying to build these applications. If I could leave you with a couple of takeaways, the key ones would just be, first, know the difference between model evals and task evals. That's really critical. Second, for task-specific evals, depending on how complex your application might be, you're going to need, don't assume it's just a single eval. You might need evals at different steps of your application. So figure out what those should be. And then third, as you're building these task evals, generally recommend don't use or don't just rely on the numerics for evals. Make sure you're actually benchmarking them and testing them to give you the right types of evals for your use case. Awesome. Well, let me know if there's any questions or any other notes.
Thank you, Aparna. Eugen, I think you asked a question. Was that for Aparna?
Yes. So actually, I think we've got two things for you, Aparna. So yes, what is pressure testing? I saw that in the slides, and I was like, I don't know what this is.
Yes. Okay. So pressure testing is basically, I hope I'm not on mute, but pressure testing is basically, I probably said it when we were showing some of the model evals that we were doing in the market. So we were pressure testing basically how good Anthropic Claude 2.1 was against GPT-4 on Needle in the Haystack. So we were testing it on basically how good was it. We placed the fact, and then we tested it across different context lengths, different fact depths within the document. And I mean, we think about it basically, the parallel I would say is like if you're profiling code to figure out where it's really slow. In this case, we were basically profiling for specifically retrieval where retrieval was really poor for these two different types of foundational models.
Okay, very cool. There is one other question.
Has your research included evals where the user is prompted for what the inferred parameters are, i.e., so you are interested in promotions?
Yeah, that's a great question, actually. So basically just assuming kind of this is what you're asking, but basically in this case, the words that might be used, like in the question, such as, are you interested in promotions? If the user specifically asked for that, well, then why not just go to that function call? Why are we kind of making the LLM decide what function call it actually should? This is actually something that could be covered in the parameter evals, the James skin, I guess. This is actually some of the templates that, let me go over to the deck here, but like I was mentioning that there's a couple different types of, even within a function call, there's like the eval on the function call, but then there's also the eval on the parameter extraction. So did it actually get the right inputs to go into the function from the user input itself? It just depends on, some of these function calls can have similar parameters. So not always just, like in this case, we actually had one where it was product details and then also track package might have had something like the same, they might both have like an ID field. And so just the difference in those parameters doesn't always make a difference. And then you have to know first what content in the user question should actually be the right thing that's pulled in as the parameter. So it's actually a lot of places where this can go wrong. And so it's kind of hard just to test it based off of, keywords or something like that. I don't know if that answered your question, but hopefully it was helpful.
All right. I think that was it. Thank you so much, Aparna. We are perfectly good on time. And so now we have our break. And so we will take a 15-minute break. And we will, Eugen, bring some slides up during that time, unless you want to stay on for questions.
Yes, I can bring up some slides. That's a good idea.
Thank you, Aparna.
Yes, and here's a Rise slide about my talk with Rise Observe. So these slides will just play during the break. If you have any questions, I'll kind of be hanging around, but I'll probably be. I'm gonna take a quick break as well, and then we'll have 2 more talks at the end. So we have one more talk, which I'm really excited for, which is going to be about matrix multiplication free LLMs. And that is really cutting edge research. And that's from Jason Estragian from UC Santa Cruz. And then we'll have one more about combining graph and vector data from Vishaka from Aperture Data. So for now, I'm going to go off screen. And if you guys have any questions, please do feel free to drop them in the chat. And we'll get to them in a couple minutes at the latest.
See you guys soon.
All right. Hello, everyone. I'm going to stop sharing the screen. We're going to, we have 2 minutes until we officially start a talk with Jason. But he's already here, so I figure we might as well get started. So Jason, I'm going to bring you up to the stage. I'm going to introduce you. So first of all, I want to say thank you, everyone, for being on for us so long for this mega stream. We've been on for almost 5 hours now. And I'm really, really excited for this talk. So I looked at this paper a while ago, Jason, and when I saw what you guys had published, I was like, this is crazy. This is going to be awesome. So you guys, today you've heard a lot about LLMs and making LLMs accessible and all of these different things. Well, I think you're about to hear one of the most interesting research pieces of research to come out this year. And the most compute-heavy piece of transform models like LLMs is the number of matrix multiplications that have to go into each call. And this is a huge blocker to LLM adoption across the board, whether you're going to be doing edge compute, whether that's GPU availability, or simply through raw power consumption. And so that's why I'm super excited to have Jason Eshragian here today to talk about new research that could be a breakthrough for this kind of LLM adoption. Jason, I'm going to take your slides to the stage and you can take it away.
Awesome. How's the audio? Can you hear me all good?
I can hear you just fine.
No, well, yeah, no, thanks for the invitation. Yeah, I appreciate you having me out to talk about these matrix multiply free LLMs. For a bit of context, I remember seeing Jan LeCun tweeting about how we need to divest, or academia needs to divest away from advancing LLMs because industry's got it covered with a hell of a lot more compute. So it was pretty cool when we kind of came across this, what I feel like is a bit of a big breakthrough, because we're able to get some seriously solid performance with very limited compute. Of course, more compute is always nice. It's always nice to be able to take these techniques that do work with limited compute and just seeing how far they can be pushed. So that's where we're at the moment. But without further ado, let's dive into this preprint and see what it's all about. So for context, it's the first billion parameter scale matrix multiply free model to achieve language generation. This is a very high level overview of, I guess, self-attention on the top left, the operators required for the matrix multiply free approach on the right. And so we're going to break this down very briefly in order to get a sense of what's going on. At a kind of an arm's length view, the things that we did were threefold. So firstly, we took that bitnet approach. You might be familiar with Microsoft's work in ternarizing all of the parameters in an LLM and still getting really nice performance. Ternarize as in setting or constraining your weights to +1, -1, and 0. And in that case, your multiplication just becomes assigned accumulation, right? That makes sense, right? If you multiply some activation by +1, it's just the same activation. If you multiply it by -1, then it's just the negation of that activation. And in custom hardware, you would just kind of bit flip the leading bit to represent that. And if it's a 0, then it's a 0, right? Which just blast away all of the bits of your activation, replace them all with 0. So the point is, in hardware, you're able to implement ternarized operations as just signed accumulations. You no longer need a multiplier to be instantiated. Then the second thing that we did here was replace the attention map. So historically, self-attention is used to do some sort of token mixing in order to understand the relationship between words or syllables, or more generally tokens, and how they relate to each other across long sequences. That is a big part of why language models have been able to achieve the performance that they have been able to achieve, and why they can remember something you said at the start of a paragraph several pages later, or many pages later in the case of Gemini. So yeah, with BitNet, they did this ternarized approach, but the outputs of their what they call bit linear operations, or bit linear layers, still requires some outer products and matrix multiplication with non-ternary parameters. So while they're able to do some really good stuff with the amount of high-level memory or DDR access that they might need there, there is still a matrix multiplication, and for reasons I'm going to show you in a moment, that requires a significant chunk of low-level memory or caching. So we went ahead and replaced that with some other matrix multiply-free approach. So we just replaced it with a linear gated recurrent unit, and things worked pretty well. Now, where BitNet left us was with this kind of theoretical model, which unfortunately wasn't released, but hopefully we've kind of compensated for the absence of BitNet being open source in this work. But they left off with a call to action and said, hey, this model doesn't work as efficiently as it could otherwise on a GPU versus some custom hardware implementation. So we call on the hardware engineers of the world to go ahead and optimize low bit width operations and more lightweight LLMs. So yeah, we kind of took that upon ourselves and built our own FPGA implementation of this model as well. And as a result, we were able to run this model at 13 watts with human readable throughput. So just to kind of like wrap this up, these first two things are what enabled this matrix multiply free language model, and the custom FPGA implementation actually makes it useful, right? Granted, it is of course useful to still be able to have the knowledge that a ternary LLM is going to work effectively, but actually deploying it is something else entirely, and gives you something really concrete to work with in silicon. So with that being said, let's just kind of take a very high level view of what self-attention is. It basically just involves, yep, excellent, you can see my cursor. It involves passing this token embedding. It splits off into 3 parallel dense layers, which generates your QKV outputs, your query key and value outputs. Your query and keys are going to be mixed together and then somehow used with your V matrix or V vector. And as a result of that, you ultimately generate one single output. Now, in the background of all of this, you need to store the outputs of your key and values, or you need to store your key and values because they're going to be used in your next step, right? So once the next token gets passed to your model, so we'll denote this as x of t equals 1. This could be x of t equals 2, where the top part of our operations are going to be operating on the first token, then bottom row is operating on our second token. Then we need to be able to do the exact same operations, but we need to keep a perfect history of our k and v values. And then so that's called the KV cache. And the KV cache is going to increase with an increasing context window. So that's a result of having to do matrix multiplication. This is just a more sequential way to execute mat mult. Now, on the other hand, and so yeah, you just keep doing this until you've exhausted all of your inputs. So on the other hand, this matrix multiply free approach is quite different. There are some parallels here, but let's break it down. It starts off seemingly the same way. We have our input embedding. We're going to take our input vector, embeddings, tokens, whatever. We'll pass them through a linear layer, but this time it's a ternary linear layer. And as a result of being ternarized, any linear layer or any linear dense operation is just, like I said, converted into a signed accumulation. So replacing vector matrix multiplication with signed accumulation. So from a software standpoint, if you were to code this up in Python, it might feel like there is no difference. From a hardware viewpoint, you can get rid of all of your multipliers. So again, you probably want custom hardware to be able to exploit something like this. So you end up with a set of outputs from these ternarized operations. And then what you do is the following part, the way that this is all color coded, hopefully to make things make a little more sense. we're doing a couple of sigmoids and this tau operation, which represents a silu. We're going to end up operating on these using this linear gated recurrent unit, which is visualized here. I should mention, so this GLU, it's basically doing token mixing in the way that self-attention is meant to as well, just with cheaper ops. We tested a variety of token mixes, including Raku4's token mixer. It just so happened that this worked the best. And as a matter of interest, the Raku4 token mixer, which we report this in our appendix kind of as a negative result to hopefully avoid the research community from wasting compute resources doing experiments that we've already run and didn't end up working as well. The Raku4 token mixer has a series of exponential operations, some divisions, basically a bunch of transcendental functions. So given that added complexity, you'd think it would work better. It did not. So this is what we used. After a set of these Hadamard products and sigmoid operators, all we need to do now is cache a single hidden state. That hidden state here does not grow with context length. We're not doing any map molt. We're not doing vector matrix molt. This hidden state doesn't need to grow. It just kind of gets projected to your next sequence step, and you just do the operation again. And so we've seen that this linear GRU can do really well up to context windows of 2K and thereabouts. And going beyond that, as far as I'm aware, it remains to be seen how well it can handle longer context windows. So we're very interested in kind of extending these experiments and seeing what needs to be done to keep pushing, I guess, these state space class of models or linear attention-based models towards those ridiculously long context windows. So of course, there is probably going to be some level of trade-off by discarding that KV cache and doing something far cheaper. As of now, as of the 1K, 2K context, we're still good. We seem to still be getting performance on par with self-attention, so that's nice. So I don't know, a logical next question could very simply be, all right, we went through all of this effort to ternarize or to build this matrix multiply free LLM. Why don't we just ternarize a bunch of things that already exist, right? Can't we just ternarize pre-existing LLMs and get similar performance? No, the short answer is no. We see on the y-axis loss and on the x-axis the number of tokens that have been trained. We use Transformer++ in the blue line as a baseline for comparison. For a few reasons, it's the backbone of a lot of state-of-the-art models, including Llama 2, Llama 3, Mistral, and a few others. Of course, they extend it and do some more fancy tricks and whatnot to make it more effective. But it is still the backbone. And much of the recent literature on linear transformers, so we're talking Mamba and GLA, they've also used Transformer++ as the baseline for comparison, so we kind of followed that mantra. So with that being said, what have we actually done? I've been alluding to how perhaps this model is only good for custom hardware implementations, but we still have to train this. And I should mention this caveat that this matrix multiply free approach is during inference only. For training, we still have to do matrix multiplies and whatnot. We're operating with BrainFloat 16 numerical formats. So we still have vector matrix multiplication during training. Of course, I think that is still valuable because you train a very solid foundation model once, and then you have a billion requests per day that only need to run inference on that model. So I would argue that inference is probably the more the thing that is going to cost you more when you have such large scale demand. Now, having said that, we still ran a set of optimizations for GPU. And as a matter of interest, so what we did was we fused a set of the kernels to accelerate training throughput. This was actually done out of necessity, and it's the only reason why we met the Nurix deadline. I think we finished our 2.7 billion scale parameter model training run several hours before the submission deadline, and it was basically because we were forced to do some CUDA level optimizations to actually enhance training. But as a result of doing that, we were able to use 2x less VRAM and accelerate training by this factor. So 25% less training time. These plots here are just kind of showing you what a vanilla bit linear layer looks like and what this fused bit linear layer looks like. So just a bit more context, fusing the ternary linear layer along with the root mean square norm, which just kind of normalizes the output vector of the ternary operations. So on the left, this plot represents time versus batch size, and on the right, memory versus batch size. The fused approach is in orange and naturally does considerably better in both cases as your batch size increases. Then secondly, we also wrote our own custom CUDA kernel to accelerate inference, basically to just better leverage the ternary weights that we're using along with 8-bit integer activations. In doing that, we then also get GPU benefits for inference. And so we were able to get 10x less VRAM during inference. So this plot here is comparing the VRAM that uses Transformer++ against that with matmul-free. So that's on the left y-axis, and on the right y-axis, we just have the same thing with latency. So in this case, lower is better, lower memory, less latency, so all is good. The x-axis sweeps across a variety of model sizes. We've gone up to 13 billion. Of course, I should mention this 13 billion relies on randomly initialized weights. So this has not been trained. We're just running the model, assuming that we are able to scale up to that parameter size. So then following that, the question kind of becomes how scalable is this, right? Something's got to give whenever you're winning performance or efficiency. It's, I don't know, there's always something that we can do better, or there's always something that you're going to lose. So let me break this down for you. This top graphic here is taken from a preprint from scaling laws for neural language models from OpenAI. Let's start with this plot in the middle. It shows the test loss almost linearly decreases with an increasing dataset size. They've given this curve fit as well. I guess if 0.095 was 0, then it would be, I guess, perfectly linear. The plot on the right shows something similar, but instead of the number of training tokens on the x-axis, the number of training tokens is fixed, and instead the number of parameters in the model is increased. And then the plot on the left is kind of like the product of these two things, the product of the data set size and parameters, and that gives you PF days, which is petaflop days. So it's more about how test loss drops with increasing compute. Of course, crank up your model size, you need more compute. Crank up the number of training tokens, you need more compute. So what is noted here is that for optimal performance, all three factors need to be scaled up in tandem. So empirical performance has this power law relationship with each individual factor when it's not bottlenecked by the other two. So inspired by that, we explored how this scaling law functions with our model. So down on the bottom here, we see the y-axis, we have loss, and on the x-axis, we have flops. Floating point operations per second. And you'll notice that these dashed lines kind of come in clusters of two. So one of these is our model, the other is just going back to the Transformer++ that is not turnerized, so a BrainFlow 16 implementation of Transformer++ that we retrained ourselves. The lowest two curves are the smallest model, the 370 million parameter versions of Transformer++ and matmul-free. And then the largest two, as you kind of move to the right, which requires more flops to train, are our 2.7 billion parameter models. So you'll notice that in all cases, these two models, these pairs of curves, are really quite close to each other, and they get closer and closer as the model scale goes up. And so then you keep training. The dark line is what we actually trained, and then the faded transparent line is our scaling law projection. So once you hit this region between 10 to the 22 or 10 to the 23 flops, then the two are expected to converge. So that's all well and good. A valid concern could very well be that this linear extrapolation of the scaling law doesn't account for potentially saturating losses, right? So perhaps this just tapers off and doesn't hit this star point. And hey, that is a legitimate concern, but we have seen Transformer++ go up to 70 billion parameter scales. That's Llama 2. So we're hopeful that this will kind of keep going up. Right now, we are talking to a few people to try and get more resources, get more GPUs to make this happen, because yeah, we're a relatively small academic lab that are very much GPU limited. Another thing that is worth noting is that flops, the nomenclature of flops is true for the Transformer++ case, but we're counting ternary operations in our approach as a flop as well. So in a way, each unit of computation that our model reports is already a lot cheaper than what Transformer++ can achieve here. So I mean, if you were to normalize this to like energy for a flop or a ternary operation, then that would kind of set our map-mol-free LM approach far more to the left. So we'd get far smaller losses for far less compute. So that's what I want to say about the scaling law. With that being said, let's go into some of the results that we achieved. On this side, we see the zero-shot accuracy of our model versus Transformer++ on a set of benchmark data sets. I guess as your model scale gets larger, so in the top cluster, we have the 370 million parameter model. On the bottom cluster, we have the 2.7 billion parameter model. We list out the number of training tokens, the number of blocks, and the embedding dimensions. And as the parameter scale increases, as I mentioned before from the scaling law, we're now quantitatively seeing the gap between Transformer++ and map-mol-free also decreasing. Some things worth noticing here, I guess, is that this WGE Winogrand, this is a binary choice question, and the ARC challenge is a 4-choice question. So in those cases, in those two benchmarks, it's kind of like a coin flip or a 4-sided coin flip anyway, and doesn't quite reflect what I'm saying here, but we included it anyway because it is a standard benchmark. I also want to flag, if you were to screenshot this and go ahead and compare it against other similarly sized models, one thing that you need to account for is how many training tokens were used. So Gemma, for example, that was trained on 6 trillion tokens. Llama 3 was on 15 trillion tokens. Again, our resources in a small academic lab limited us to far, far smaller tokens, to 100 billion tokens. So if we wanted to scale up to 15 trillion, I will more than gladly accept donations for $1 million to make that happen. Now, we're relying on GPUs to train these models. Of course, there's a set of gradient operations that need to be overridden, in that if I was to ternarize a full precision weight, then I need some sort of quantization-aware training using straight-through estimators. So I'm not going to go into the low-level detail of the non-differentiability of ternary operators, but so ultimately, you need GPUs to train these models. But then inference can go GPU-free. And if we want to test out something that really milks ternary operations, then what do you want to look at? Custom hardware. And so if we want to meet the NeurIPS deadline, then we have 3 weeks to make this happen. We wrote this all up in System Verilog RTL, so it's thoroughly, all the results that were in the preprint are thoroughly unoptimized. There's no DSP, so we're not milking the kind of tailored acceleration components on an FPGA, where there's no DDR bursting, there's no pipelining. We wrote a custom assembler for our custom instruction set, which was used to convert assembly files into an instruction ROM. And that instruction set included all the ternary operations that we needed. So if I was to kind of test performance across different embedding dimensions, so sweeping across D for different model sizes, then perhaps in a more interpretable set of numbers. So I mean, we've got runtime and projected runtime. If we were to access more values from DDR, and energy power estimates from power profiling tools, in in a more interpretable set of numbers, what we're getting is 23.8 tokens per second at 13 watts. In contrast, the brain operates at 5 to 15 tokens per second at approximately 20 watts. That's what it takes for me to talk about matmul-free through StreamYard. Again, there's no pipelining, no batching, so there is a lot of room for improvement here. I really want to stress that this is thoroughly unoptimized. And so next, we also evaluated resource utilization. We tested the use of various core counts. And what I want to highlight here is the latency. So if you consider this latency of the core itself versus DDR, so we're showing that memory access is not the bottleneck, which is typically going to be the bottleneck in most of your neural network workloads. So at the moment, it turns out that the 3 required ternary accumulations, and in the paper we do call it a ternary matmul, those instructions take up nearly all of the total execution time. So in future work, if we were to introduce parallelism and caching to improve the ternary matmul execution time, then that could lead to a huge change in the balance between core and DDR latency. With all of that being said, I'm just going to kind of fly through a bit of a future vision of where I hope these models are going to go. But let's say that I have conventional self-attention on some hardware where we've got inputs streaming into some accelerator, and then we've got outputs coming in. Given the large KV cache that is needed, so I mean, how many H100 GPUs do I need to serve one single user at 8-bit floating point at a throughput that matches human reading speed? So a semi-wiki estimate was 256 GPUs. Now, how many daily visits does ChatGPT get? There was some number that said 1.75 billion at its peak. Of course, that disaggregates somewhat. Now, this kind of darkening of the inference fabric just indicates that you're fully utilizing all of the hardware that you have available to you, right? Now, if instead we go into the direction of alternative models, so the precursor to this matmul-free paper was this Spike GPT model, which had some temporal sparsity and used state space approaches, etc. We released it about a year before our matmul-free work. Now, if I was to take some sort of temporally sparse, time-varying self-attention mechanism, and the idea is this. I mean, if you have sparsity in weights or in your data flow, then you might not need to have to fully utilize all of your hardware. So you can kind of run parallel workloads concurrently. You can basically do this multi-tenanting where many users can execute on the same hardware. So SNNs refers to spiking neural networks. It's a big part of the work that we do in our lab, where you just have neural networks with a high level of temporal activation sparsity. In that case, you're only accessing data that needs to be accessed, so you have less data movement but low utilization. And hardware engineers and silicon guys, they hate to see low utilization. They don't want things there that aren't being used. So if we combine that with some sort of vertical cache or some memory that's stacked on top, then you're able to concurrently access all of your data that needs to be accessed. And so you end up getting energy benefits that are massive as a result of this parallelism. So with that being said, I kind of see that matmul-free could enable huge concurrency on the same hardware, especially if we were to push this towards some sort of temporally sparse neural network. This work was led by Mid Year Zoo over in the back here. He did an incredible job kind of seeing this to fruition, and a lot of sleepless nights. There's a fantastic quote that the next greatest advance in neural networks is not going to be from some large, incredibly well-funded company, but rather from a grad student. And so I don't know, I couldn't help but think of that quote when Mid Year was blasting out these results. It's yeah, really quite cool to see in doing so well. And of course, got to say thank you to the lab that actually makes this work possible. So with that being said, thanks very much. Forgive my 17th of June typo. And the wrong title. I'm clearly sleep deprived on this, but yeah, thanks a lot.
Oh, wow. That was like really interesting. At least for me. And I had a bunch of questions I wanted to ask, but like primarily I want to know, like, you mentioned a lot of custom hardware stuff. Is it possible to leverage like not generic, kind of doesn't really make sense, but is it possible to leverage like other NVIDIA type hardware, AMD type like GPUs, or is this something that's going to be kind of limited in terms of distribution because it needs some sort of like custom hardware implementation?
Yeah, no, that's a really important question. In terms of training, no, we're stuck with GPUs. This is, of course, a model that's targeting inference. Now, for inference, if you want to be able to exploit GPU acceleration, now the limits of what we've really done here is fusing the operations at the CUDA or Triton level in order to accelerate inference. Now, if you want to push that a little bit further, then we would be relying on ternary kernels. And I believe that they might exist. I'm not sure if they exist. When I kind of looked it up, they seemed a little primitive and a bit janky, and I couldn't really figure out how to take advantage of it myself. But if you start seeing more mature ternary kernels that can take advantage of 8-bit widths, 8-bit addresses and whatnot, then you're able to take more advantage of GPUs. I would say that the advantage that you can take of GPUs, even with ternary kernels, is going to kind of be, there is going to be a ceiling on that custom hardware can blast through. Technically, a ternary bit still needs 2 bits, right? So you're kind of not using, if you have 3 levels, then you need 2 bits. You need 4 levels to store that. So you're not taking full advantage of, I guess, your SRAM or whatever memory that you're using. So custom hardware does have some opportunity to just push past what GPUs can do. That is not to say GPUs are useless here. They are still very much able to take advantage of this.
Okay. What about CPUs?
Oof. I guess so, yeah. They just do it far slower. So I think everything I said does generalize to CPUs. It'd just be like taking something super slow and making it slow.
Okay, cool. Thank you, Jason. We have one more talk today, everyone. I'm going to let Megan come to the stage and introduce our final speaker.
Thank you, Jason. Thank you, Eugen. I remembered to unmute myself this time. Last but not least, we have Vishaka from Aperture Data, and I will introduce him shortly, but with years of research experience, Vishaka has led the building of a new type of database storage system that's really come to be important in the last couple of years. And Aperture Data is a system that combines 2 of the most important search functionalities for generative AI, graphs and vector search. So today she's here to share more information about how this system is especially important in Gen AI use cases. So let me bring up Vishaka. Awesome.
Hi, Megan.
Hello. The best for last. So I will hand the stage over to you.
It's either best for last or it's like everyone is tuned out and I have a lot of work to do.
Definitely best for last.
All right. Hopefully everyone can hear me and see my slides. The best case, please keep it interactive. I can go deeper into any of the points that I make here. It'll be great if it's driven by your questions. So post your questions on YouTube or the Discord chats. Some of my teammates are online, and Eugene and Megan are here to pull those up too. Let's get started. So a few weeks back, when I presented during the LinkedIn Live session that Eugene does, I covered some use cases and examples around machine learning, large language models, retrieval augmented generation, and all the talks throughout the day today. They basically gave all the details there, so I don't really need to go there. But what I want to highlight there is how different modalities of data are so valuable everywhere, and that too in an exceedingly competitive and fast-paced AI market. I mean, think about it. If you did not do anything for 6 months, there'd be like 3 different versions of GPT by then. And all of this, I mean, if you go from the perspective of companies, they are doing all of this with the intention of driving up both operational efficiencies and customer growth. However, after conversations with hundreds of people on the ground across companies of various sizes and working on different use cases with different types of data, Despite all these advances in AI and in all these models and techniques that we have heard all day today, the moment it comes back to actually deploying and getting these things to work in production, we keep hearing the same set of challenges. If they really want to get the most out of these AI techniques, the dream expectations or requirements from the data layer, because they need to incorporate their own data, sometimes fine-tune for end results, sometimes combine it in a way that gives them the results that actually match more of the human sort of expectations. And so what that invariably leads to is this set of requirements where could we have all our data be accessible from one backend instead of going to multiple different places? Could we search that data through multiple modalities? Could we make it easy maybe to do data set management? Because sometimes we have to create different versions of data sets. They come from different sources. There might be overlaps. How can we efficiently do this? Then, of course, if you're fine-tuning your models with certain data sets, you want to maintain a correlation. Maybe you had to modify the data along the way. How did it change? Who made that change? When you go in a production environment, that governance information becomes really important. And last but not the least, throughout this process, you want your data layer to keep working with all the machine learning tools that you already use or are planning to use. Now, these really, I call them dream set of requirements. Why? Because with data coming in from so many sources, it can also be very much scattered across various databases, cloud buckets, their local machines, which they write scripts and use processing libraries to bring that data together. So it's not really shocking when people lose track of what their data means, where it all lives, and how it impacts their searches and model development. In fact, it can get the real cost is the inefficiencies introduced when you try to tie multiple of these systems up together. And more than that, it's the lost opportunity cost. Like I was saying, if you took six months to put these pieces of data infrastructure together, and that's being optimistic, you've really missed certain generations of updates that happen to the models and techniques in that time. So what can we do about it? We solve this problem with a database. We are, my co-founder and I, very much systems and infrastructure people. We looked at machine learning as an application, and we thought, what can we do to make data and metadata access easy for every stage of machine learning and analytics pipeline? So we came up with this option of building a database that not only understood the complexity of multimodal data management, but also had this understanding of how this data was going to be used by AI teams. And so we could make it easy for them to adopt and deploy in production. And the result was ApertureDB. It's a purpose-built database for multimodal AI. And what do I mean by that? There are three important pieces, actually four. The first one, we natively built in support in our store and query APIs for the database to manage multimodal data like documents, audios, images, videos. We originally started out with computer vision data. So we have a lot more advanced interfaces to manage images and videos. So you can actually query ApertureDB to return videos, let's say at 1 frame per second, even if you had stored them at 30 frames per second. Or you can say, give me images in a resized and rotated format, and it'll do it on the fly. Then the next really important piece of this, especially as more and more people, especially as some of you have been improving RAG stacks, are realizing the value of metadata, particularly as entities and relationships between them. We analyzed a lot of applications when we were getting started, and the data model invariably matched with a graph database much better, with the graph data model much better. Which is why we started out with graph databases, and now it's actually, with all the work around knowledge graphs, it's a perfect fit because we manage application metadata in a memory optimized graph database so that it helps you build that knowledge graph as you capture the entities that are important in the documents or multimodal data that you're dealing with. And the relationships help you traverse complex relationships and find what you're looking for. And one of the aspects is because we were always thinking about machine learning and we started out with computer vision data, we also built in a lot of support for annotations. You have bounding boxes, video clips and frames, and you can do simple annotations on your on text information as well. Then another, and we've heard and Eugene covered the whole vector database space here. Now embeddings since embeddings from PDFs, images, or videos make it possible to find similar things. So we also offer vector search and classification through our inbuilt vector database. You can index any dimensional feature vectors coming from any of your source data, and we'll help you search it. And I think when Eugene presented, he talked about how we blend the vector and graph together. It's because the vector embeddings in our database have a representation in the graph, which means they're connected to the rest of your application context. And it'll become clearer when I walk you through an example. Now, one of the important goals for us when we were building was to keep it simple for our users. These three systems sound like three completely different systems, kind of similar to what people have to do today. But then we have our, this query engine or orchestrator that we built on top of it, which essentially combines these things behind the scene. The users just query ApertureDB with a unified API, and internally we take care of redirecting the user queries to the right components and combining the results to give users a coherent response. And this is the interface at which the users of machine learning pipelines can interact with ApertureDB. So that's what we offer with Aperture. It offers a unified interface to store, search, and access all of users' documents, images, videos, application metadata, annotations, and embeddings. Now, of course, databases live together with other components in your pipeline. So as we saw earlier, ApertureDB can take care of managing metadata and data, and it horizontally scales. So you can scale, you can go to a pretty large scale that I'll cover later. We are also, ApertureDB is cloud agnostic. So it's possible to deploy it on any of your cloud providers or on-prem if needed. And ApertureDB we can basically store and access the data from the different cloud buckets or storage managed by the server itself. And of course, we provide a good set of client tools, primarily Python and C++ right now. And as our users require, we can introduce other client interfaces for ApertureDB. We have a good set of additional tools because, of course, you got to ingest the data, you need to query it. So we have parallel loaders. You essentially give it comma-separated value files, and we can ingest the data in parallel, and we'll take care of batching and pipelining it to the database. We also have different ways in which you can query the data that you ingest. We've recently been adding integrations to other frameworks like LangChain, but you can also directly do vector search, graph search, and get your data back from ApertureDB. We also end up working on the training and inference side with, with machine learning teams that are preparing the models. So we have integrations with tooling like PyTorch, TensorFlow to make that easier, and then Label Studio and labeling sort of tools like Label Studio. And then we have our own front end, so you can easily look at the data that you have. And of course, if you are thinking about how would you scale this into production, how will you answer questions around data security and privacy, we already have built-in authentication, a role-based access control, logging and monitoring support when you deploy ApertureDB. Now, what sort of impact does it have when you make certain design choices, or you combine certain ways, or you acknowledge the way your data is going to be used? So now imagine if you could create your data sets 35 times faster. And this was an old paper with the older version of our database, and now it scales a lot more. So the numbers only get better, but they're not published outside. So I use the one that's published, and you can actually read about them. There there was a result that at the beginning kind of surprised us, but then we realized, of course, it makes sense, is the reduction in network transfer. And you might wonder why, especially if you're thinking about image video type of data. Very often, you reduce it in, you resize it down, or you're doing a thumbnail display of things, or you resize it for your model requirement. Because ApertureDB API allows you to apply those operations on the fly near the data, when you transfer this data, it's typically much smaller. 63% was one of the applications. For one of the other applications we measured, it was 6x savings because it was high resolution image, but they only cared about the regions of interest in that image, which is something we could give them through our interface. For vector databases, we have some numbers from our customer implementation, and we can be 2 to 4 times faster compared to some popular open source vector database. There's always, especially when you're thinking about multimodal data in production or deploying this on large scale, and how quickly can you do it, the biggest thing that appeals to our customers particularly is the fact that they can get started so much faster. And they can simplify their infrastructure so significantly. But not only that, we can actually scale to a fairly large data size, and we don't even know what the upper limit is because we keep testing up every time we get a new ceiling to achieve. So far, we know we can scale to over 1 billion entities in our graph, over 300 million images, and over millions of 4K dimension embeddings. So these are all well and good. It always helps to see something in action. So did we, by combining all these things and thinking so much about the API, did we really simplify the life of data scientists and engineers with our multimodal AI database? So let's see how maybe we could build a simple document search example. Before I do that, are there any questions? I'll keep going, and I'll just think Eugene will come online if he sees questions. So let's go see an example. Now, the first thing for any database is loading data into it. And I'll use a very simple toy example to show you how easy it is to build an application dealing with different data modalities in ApertureDB. Our client, you can very easily install it with pip. You can do pip install ApertureDB. Before I go into showing you a data loading example, I want to come back to the graph. Because for any application, the very first thing we do is understand the queries. We understand what are the data types on which we are going to run those queries. So here, what I want to build is take paragraphs from our documentation, extract embeddings from them, and then do a vector search. And so just for that part, let's say I want to create a schema in a graph. Now, a graph database, particularly the one we implement, it's a property graph model where you have nodes connected by edges. The nodes can be grouped together by tags or classes, and they have key value properties. You can have any number of key value properties in any number of nodes. You can introduce new key value properties whenever you want. That's the best part. It can evolve as your application grows. So you're not tied into a schema, which is very valuable, which was one of the big reasons why we chose a graph database model when we started. So here, for example, I made a schema, and this can be whatever your application requires. And if you were thinking from the perspective of, you've been in the SQL world, how does it map? In the SQL world, there would be a paragraphs table if you wanted to create this sort of a schema, and each row would represent a different paragraph. Here, each node represents a paragraph. You can have multiple paragraph nodes, and then they can have key value properties, for example, the actual text of the paragraph. Where does it start on the page? But I also wanted to connect it to the document where it came from. So I introduced a document entity or node in the graph, and I connect it with a paragraph. And I extract descriptor or embedding, and I used, let's say, descriptor set in ApertureDB is what we call a collection, is what I've heard some of the other terms. This is your search space for vector embeddings of the same dimension and extracted from the same model and representing the same search space. So let's say we want to create, we want to do vector search. So we create the collection, and we start adding descriptors per paragraph. Now, what I also want to do is if there are any images connected to the paragraph, when I search for the right paragraph, I also want to see those images. So I introduce images in my property graph. Maybe later on I realize I want to track these images in a data set because I'm going to query them by data sets and see what changed. Maybe because I want to train different models on the images that are there in my documentation because they help me understand what's going on and if someone asks a question. So this is the toy example that we want to create, and this is how the graph can evolve. And the best part is it can be anything adapted to your application. So we have used the same sort of logic to work with an e-commerce vendor, with a retail vendor, with a biotech vendor. So we can apply it in different use case situations. Now, how do I create this graph? So let me take a toy example. So this is just our comma-separated value files. You can find them on our documentation, much easier to read them there. But I define my paragraph, and then I have certain properties about the paragraph. The same way I have images that I'm going to ingest, and I'm going to connect those two together. So it's as simple as getting those CSV files and just running these commands, as you can see, ADB ingest from CSV, and then provide the ingestion type. So the first file is entities in the graph. The second one is a specially recognized entity in our database because we recognize images. So you can do ingest type images with the CSV file. And then I connect those two. I define which paragraph connects to which image. The same way, I can ingest descriptors for the paragraphs, and they'll get connected to, after a few steps, they'll get connected to where they come from. In fact, it can be as easy as applying embedding a transformation on the fly on this command line, so you can ingest additional information alongside the data. But I won't go into it right now. Let's go see, once I ingested the data, can I actually go see it? So we have front end, which lets you look at the data. So what I did, I have this metadata property on my images, and I did a search, and I wanted to see the properties. These are the images that I showed ingestion for. My database has other things which if I applied some other filters here, I would see images that match those filters. Another thing I want to show you from the dashboard is that you can see all the different objects and connections that are in the database. And as I mentioned, my demo database has all kinds of mixed data sets. So you'll see patients, you'll see products, you'll see cameras, all sorts of things. And you can see counts of how many of everything is present. This is a great way when you have separate data engineering or data science teams to look at the common view of their data. What is ingested? What are the property names? What are their types? Are they indexed or not? This is that one view where everyone can know what their Aperture DB data looks like. And of course, you can execute a similar thing on Jupyter Notebooks as well. So that was just, we ingested the data, we were able to see it. If I go along the pipeline, we often get questions about integrations with, labeling or curation tools. While we can work with different tools, we can work with different curation tools like Visual Layer, the talk we heard earlier, or with labeling, we work with Label Studio right now. It's mainly driven by whatever our customers ask us to integrate with. But the more interesting aspect is querying the data. Most of the times, to answer questions. So if you are building an LLM and RAG stack for your application, for a chatbot, say, how would you query that data? So I showed you a toy example. Let's continue with that toy example. Now, here what I'm doing is essentially, I'm shifting now to the Jupyter Notebook just to show the examples on how I can connect to the database, establish that everything is fine. So here I basically just connected to the database. This was the schema we discussed earlier on how to build it. I already ingested the data. So now if I ran with the search term, let's say Badger Technologies, I look for matching paragraphs. And what that code looks like, if I go into the helper function, it essentially is doing find descriptor is essentially find matching embedding. Embeddings are in our query API called descriptors. And you can say, this is the search space. I want 5 neighbors. And I want the connected entities with them. Now, this is where we are traversing the graph. And then you just return examples, which is where it shows you these were the 2 paragraphs that matched when you did a similarity search. Now, let's say I wanted to look at the connected images. If I look at the function, find connected images in the actual implementation, I again did a vector search. I found the paragraph, and then I went over to the images that we just connected through the CSV examples I showed. So it was a really easy way to show you how you were in the same database. You first did a vector search, and then you could actually use the graph to get to other data types. In this case, image. It could be a PDF. You could also apply additional filters that you only want images that are high resolution. The possibilities are enormous. Now, this is a toy example, but what we did was index Wikipedia data, which actually has 600. We took the 600 paragraph wiki data with Cohere embeddings that was already there on Hugging Face, and we indexed that. In fact, you can go on our website where you can go to the try free option, choose any of these, and the last one is the one I'm showing you right now, and run this yourself. This is our integration with LangChain to build a RAG, to show you a RAG and non-RAG example. So we build the chain for both. We use the ApertureDB vector store integration and the retrieval integration with LangChain. And what we do is we have some questions that you can ask this. So let's say I want to ask, you get a non-RAG answer, and you can get a RAG answer to it with references to the document. But we also tried to ask it questions around ApertureDB. But the model we used and the vectors that we had indexed, they didn't have really good answers to what we were looking for to answer questions about ApertureDB. So what we also did is crawl our own documentation and website. I think it's similar to the example, one of the examples we saw earlier. And we essentially here, if we come, I can ask questions around how do I store audio files in ApertureDB with our data now indexed, and you get a much better answer with pointers to the right documentation. In fact, that's really what we recently launched on our documentation. Go ahead and try it out and ask it questions. This chatbot is powered by ApertureDB Vector Search and by the example that you saw in that demo. Some of the other things that have come up is how do we deal with multimodal embeddings? So here, this example, essentially, we index clip embeddings. So we used the embeddings that come out of clip models that combine text and images. And when you give it a search term, pizza with friends, it goes and searches and finds images that correspond to that search term. And it was a very easy ingestion to just specify the COCO dataset images along with a clip embedding extractor together when we were loading on that ADB command line. And after that, you could just query using the multimodal embeddings. And where does the combination, how do we exploit the combination of graph and vectors? And this is yet another example of demo that you can use with celebrity faces. And here is where we not only find similar faces, but what we can restrict them is by metadata properties. You search with a set name, find similar images, and then restrict them by some metadata you care about. So I encourage you to go ahead and try these things, try these demos out. I can't cover a lot of things today, but hopefully that gives you an overview of all the different things you can do with Aperture. This is essentially like, we built some set of integrations to work in our customer pipeline. But the key part is if you choose the right database so that your data preparation time cuts down significantly, you really can shift your focus back to improving the models that you've been working on. I do get questions occasionally around, how do we compare with other vector databases, other graph databases, or just traditional databases. So we look at it as the right data layer for the overall pipeline, which means you want all these different properties that are not present in some of the other tools that we work with. So if you want something that unifies all the data and metadata access for the various stages of the work that you're doing, ApertureDB is built to support that. I am happy to answer any questions. We would love to hear from you. If you scan the barcode, or the QR code, it'll take you to all the relevant links. But the easiest, you can just write an email to us. And we're also on the Discord channel today. I will pause here now if there are any questions.
Okay, thank you, Vishaka. I don't see any extra questions popping up in the chat. Megan, did you have anything to say here?
You're on
You
mute.
were on mute.
Continuing the theme.
Yes. I said, Eugen, you asked a bunch of questions.
Oh, yes. Oh, no, I asked a bunch of questions in the chat earlier.
Oh, okay. I see this little +1. I was like, what is that?
Oh, +1. Yes, I was giving a thumbs up to one of the things. I don't remember what you were saying when I gave this thumbs up, but I was giving a thumbs up to one of the things you were saying, Vishaka. Actually, I think
got to ask a lot of questions when we did our 1-hour conversation. So
yes, I've asked you a lot of questions about this already. And so if you're in the audience now, you can go back and listen to that set as well. I did have one question for this specific talk that you just gave, which was can you go back to your integrations slide?
1 second.
How or why did you choose to do some of the integrations that you've done here? Why does it make sense to do BigQuery and Postgres and PyTorch and TensorFlow and Vertex?
As they're customer driven. That's the simplest answer. It's basically if they were migrating their data from some examples, what were they migrating from? And what were they going to use for querying, or what were they using as their labeling tool or their training frameworks? So it was where do we get the most ROI? The usual startup equation.
Okay, I see. Yes. Okay, that makes perfect sense. Okay, I didn't have any other questions pertaining to this specific slide or the specific presentation, but I did have a bunch of presentations before. We are over on time now. As there's no questions popping up in the chat, I think we can wrap this up.
Yeah, thanks a lot for inviting me. And it was a great learning experience today. Thank you, both of you.
Thank you, Vishaka.
Yes. Thank you for coming, Vishaka. Thanks for being such a great closer.
Tried.
Oh, sorry, I cut her off. Thank you.
Okay. Yeah, thank you guys all for coming today. I hope you all learned a lot today. Thank you for helping me host this, Megan.
Of course. Thanks for everybody's questions.
Yes, also for the people who are here and who haven't yet met Megan, she is one of the best data influencers, period. Just all around. Your Instagram growth has also been insane. So I really appreciate you being on here and helping out with some of the stuff.
No, I love this community, and I was super happy to contribute to it, and looking forward to future events that Eugen will be hosting based on the lively conversations that were happening today. So thank you guys for contributing to that conversation.
And thank you, Jenny, for the very kind words. So we are over on time. It has been about 6 hours of streaming. I'm sure you're very tired. I'm very tired. Thank you, everyone who has stayed, and I hope you have all learned a lot from the stream. And I will see you guys all. If you're in Seattle, I will see you on the 9th. If you are online, I will see you online on these workshops. So peace, everyone.